Hi and welcome to this Go course. My name is Maximilian Schwarzmuller and I will be your instructor teaching you Go from the ground up, step by step and in great depth. Not just in theory, but instead also by building multiple demo projects, both smaller and more complex projects, like for example that main course project where we will build an entire REST API with Go, including authentication and all these fun things from the ground up, step by step. To get there, we'll of course learn about all the essentials and then about the more advanced concepts that make up Go. And all you need for that course is some basic programming knowledge in general, no matter with which language. You don't need to be an expert, but it helps if you have worked with some other programming language. You of course don't need to know anything about Go though. And therefore, enough of the words, let's get started, and let's start with the most important question. What exactly is Go and why is it such a popular and awesome language? So, what is Go and why would you use it? Well, it's a programming language, and to be precise, it's an open source programming language developed and published by Google. It's a relatively new programming language. It was developed in 2007 and made public in 2009. And it's an extremely popular programming language because of its focus on simplicity, clarity, and scalability, because it offers great performance and has a strong focus on concurrency, so on running multiple tasks simultaneously, because it comes with batteries included, so with a lot of important features built in so that you don't need to reach for a bunch of third-party libraries to perform basic tasks, and because it's a statically typed language, giving you extra type safety and allowing you as a developer to catch and fix many errors pretty early during development instead of whilst testing your application and catching errors at runtime. And you'll see these benefits in action throughout the course, of course. Now, because of these advantages, Go is pretty popular for developing network applications and APIs, microservice applications, and also CLI tools, command line interface tools. And we'll actually build a bunch of demo applications from some of these areas throughout this course. Now, in order to write and run Go code, you need to install Go on your system. To be precise, you need to install the Go compiler because Go is a compiled language, which means the code must be translated to machine code before it is executed. And for that, you need to install that compiler. Now, this compiler is available for all major operating systems, and you can simply visit go.dev and click download there to choose the version for your operating system. Now, if you don't want to install this compiler, or if you're on a system where you can't download and install software, for example on some machine where you don't have admin permissions, you can also use the attached Code Sandbox web-based environment to follow along, and you'll find links to starting projects, so to such Go projects throughout this course so that you can follow along with each section without installing Go locally on your system. So you're not required to install anything on your system and you'll still be able to follow along with this course. If you do want to install and run Go locally on your system though, you should download that installer. Here I'm on macOS, but again, it exists for all operating systems and you can follow along with this course no matter which operating system you're using, and you can then simply go through that installer. Once the installation succeeded, you're ready to run Go code. So you installed this Go compiler, or you're following along in this browser-based environment I mentioned in the previous lecture, and you're therefore now ready to write and run Go code. Therefore, As a next step, you can create an empty folder somewhere on your system and open that with your favorite code editor. I'm using Visual Studio Code, an amazing code editor which you can use for free on all major operating systems. It's a very extensible, fast, and really awesome code editor, but you can use any code editor you want, open that empty folder you created, and add a new file in there. For example, app.go, though the file name is up to you. Now here, VS Code is then automatically asking me whether I want to install the Go extension. Because as mentioned, VS Code is an extensible code editor, and there are plenty of extensions for all kinds of things to get better support when writing code, and therefore there also is a Go extension. If you're not getting that pop-up here, you can search for it manually in the extensions area by entering Go there. And then it's this first result from the official Go team. And I strongly recommend installing that Go extension and also any other tools this extension might need, like this tool for which I'm prompted here, because this extension will make your life easier, show many errors in your code earlier, and simply therefore speed up your Go development process. So with that extension installed, you're then ready to write some Go code in that app.go file. And in that file, just so that we see something on the screen, you should write package main as a first instruction, and I'll explain what this code does in just a second. Then write func main followed by a pair of opening and closing parentheses, followed by a pair of opening and closing curly braces. And between those curly braces, type fmt print hello world, with hello world enclosed by double quotes. Not single quotes, but double quotes. In addition, between this package main line of code and this func main line of code, you should add this code. Import fmt, where fmt is also enclosed by double quotes. And this code then gives you a basic Go application which you can execute. So you can now save this code, open your terminal, your default system terminal. If you open it here in Visual Studio Code, it's your default terminal, just automatically navigated into this project folder that contains this code file. And in here, you can run go run and then your file name, for example, app.go in my case. And you should see hello world here. On Code Sandbox, you can also go to the terminal, open a new terminal, and also run that same command. And with that, you wrote and executed your first Go program. In the next section, we'll now explore what exactly this code is all about and which essential core features Go has to offer in general. Now, before we'll dive into Go and learn all about Go, I want to give you an overview of what you can expect from this course. We're almost done getting started at this point, and in the next section, which will be a pretty big section, I'll then walk you through the core essential Go concepts you must know no matter which Go project you'll be working on. We'll explore the key elements that make up the Go programming language, and we're going to write a lot of code. But Go has more to offer than just those essentials. Therefore, thereafter, after that big essentials section, you'll find many other sections where we'll then dive deeper and deeper into Go and explore more crucial features step by step. So that after all those sections, you'll have a very solid understanding of the Go programming language. Well, and therefore, thereafter, we'll build the main project of this course, a REST API, so a REST web service, which we're going to build together step by step from the ground up. And of course, whilst building that, we'll therefore then apply and use many of those crucial concepts you learned throughout this course. Now this, of course, is a big course, and I therefore want to make sure that you get the most out of it. And that starts at meeting the course prerequisites. As you can see on the course landing page, for this course, basic programming knowledge with any language of your choice is strongly recommended. You can also take this course if you haven't worked with any other programming language, but it will be harder. So my recommendation is that you take this course after you learned at least the basics of some other programming language. By no means do you have to be an expert in programming or in any specific language, but you should have some basics. Well, and then it's of course all about watching the videos, because this is a video-based course, but watch them at your pace. Use those video player controls to slow me down if I'm going too fast, or speed me up if I'm going too slow for your taste. Also feel free to pause and rewind, or repeat entire sections if something's not clear immediately. It's a video on demand course, so use that as an advantage. You can watch the videos whenever you want and as often as you want. But watching the videos will only get you this far. You should also practice what you learned. And in this course, I will give you some practice projects and some exercises, but for the most part, I do want to encourage you that you also pause the videos frequently and that you practice on your own. That you simply try out the next steps on your own before watching the rest of the video. Or that you come back to a section you already completed and you again try building the demo project that we built in that section from the ground up on your own, because only practice makes perfect. Of course, also simply build your own dummy demo projects. So come up with your own project ideas and try building those with the knowledge you gained in this course. Because that then allows you to apply that knowledge and ultimately master Go. And of course, you also might get stuck. And the great thing is that I do provide code attachments, so that if you're following along with the code and you're getting some error, which I'm not getting in the videos, you can take a look at my code attachments. You find a link to them attached to this lecture, and you can compare my code to yours to find out where your code differs and what might be causing this problem. In addition, you can of course also ask and answer in the Q&A section, though please really also answer there. Don't just ask, because you'll learn much more if you do answer, because if you're forced to think about a problem and come up with a solution, you're also forced to apply your knowledge, and this simply is a great practice opportunity. Last but not least, attached you also find a link to a page that allows you to join our Discord channel, where you can find like-minded developers so that you can learn and grow together. Now that we got started with this course, and now that we wrote a first basic Go program, it's time to dive deeper and explore these crucial Go essentials, the core concepts you'll always need no matter which Go application you're going to build. And for that, in this section, we'll take a look at the key components, you could say, the key components you'll have in every Go program. We'll then explore the concept of values and types, which is a crucial concept, as you'll see. And along the way, we'll also explore variables and constants. We'll also take a look at functions, how you can create functions, how you can execute functions, and what the idea behind functions is to begin with. And we'll also take a first look at control structures, because these are important, as you will see, for controlling how your code executes and which code executes at which point of time. So plenty of concepts to cover. Let's dive in. And we will start by taking a look at the key components, you could say, that make up a Go program. And for that, we can take a look at the program we wrote in the first section. It's a basic program, but it contains these key components. which I guess makes sense since I said that they would be part of every Go program. And of course, if we take a look at this code, there are a couple of key components. For example, this package instruction here is an important thing, and I will get back to that, just as I will come back to this import thing here. But I want to start with this main func and this line of code here. What are we doing here? Well, in the end here, we're calling a so-called function. Print is a so-called function, which you can simply think of as a command that we're executing. So we're calling a function, we're executing a command, and in this case, if we hover over print, we're executing a command that print formats using the default formats for its operands and writes to standard output. Okay, that's absolutely not clear. Well, that's in the end a complicated way of saying that this command here is printing, is outputting this text here to the standard output, which turns out to be the command line. Because this Go program here is one which we have to run from the command line with go run app go, as we did it before, for example. And if we do that, this print command here, this print function, is responsible for outputting this text in that command line. That's what this command does. Now, this print command is in the end a built-in command, you could say, provided by that FMT thing, by that FMT package, as you will later learn. Now, this package is part of Go itself. You don't need to download it to have it available. It's built into Go, and it's simply one of many built-in packages, as you will see, that gives you access to helpful functions, helpful commands like this. Now, the thing we're passing to print is called a value, and specifically it's a so-called string value, which in the end just means that it's text. In Go, you can work with many values, as in basically all programming languages, and as you will see throughout the course, and strings, so text, are just one possible value type. You create such a string value in Go by using double quotes. And that's different from other languages like, for example, JavaScript, where you could also use single quotes. In Go, that's not allowed. It must be double quotes, or actually, as you will also see later, backticks, which is a different character than the single quote. But double quotes are the common choice. This main thing here is then also a function, but now a function we're defining ourselves. So a command we're defining ourselves. And this command can then also be executed, though in case of the main function, it will be executed by Go. But I will get back to that. For the moment, that's all we need to know about this code. Let's therefore now come back to this package thing here and take a closer look at that. So this code here is important, but another key element of any Go program is this package thing here, this package clause, as it's also called, at the top of the file. Because as you'll see, every Go code file needs such a package instruction inside of it. If you would remove this, you would get an error if you have the Go extension installed in VS Code. You get an error that it expected a package clause but found import, so that it found the import statement as a first statement in a file when it actually expected the package statement. So we have to bring it back. But why does this matter? What's the idea behind this package instruction here? Well, when writing Go code, you split your code across packages. You must have at least one package per application, per Go program, but you can have multiple packages. And a single package can also be split across multiple files. So here I could add another Go file, which also belongs to the main package. That's possible. You can have multiple files that make up one package, and you can have multiple packages in one Go project. And the idea behind these packages simply is to organize your code. And later in this course, you'll also see applications where we do work with multiple files for a single package and with multiple packages in a project. But we need these packages because once we work with multiple packages, we can use features from package B in package A, for example. So we can export and import features across our files so that the individual files stay rather lean. And that's what we're already doing here with this import statement, by the way. Here we're importing a package, the FMT package in this case. Now that's not a package written by us. Instead, this FMT package is part of Go's standard library. As I mentioned in the first course section, Go comes with a huge standard library of built-in packages. So packages that are installed together with Go, you could say, that are part of the Go compiler, if you want to say it like this. Packages you can use in every Go program. And attached you find a link to this standard library page, and here you find a list of all the packages that come together with Go. And on this page you can, for example, search for FMT to find this FMT package which we're currently importing, and you can click on that package to learn about the features it exposes. Now you don't need to do that here. Instead, here we can see that this package in the end exposes such a print function, as it's called. Something we can execute to output some text on the screen. So that's a package not written by us, which we're importing, so that here we can use a feature from that package, the print feature, the print function. And that's the idea behind packages and why we also need to use packages ourselves. It simply is a requirement by Go. Your code must be organized into packages. But why did I choose main as a name here? So why is this package named main? Why not app or hello or anything like that? Well, indeed you can theoretically use any name you want, because as mentioned, many Go projects, especially bigger projects of course, typically use multiple packages, and these packages then need different names. For example, this FMT package here is named FMT, not main. So why did I choose main as a name, and why did I tell you that you should use main as a name here? Because main is a special package name that tells Go that this package will be the main entry point of the application we're building. And this matters because you'll not always run your code as we did it before. You'll not always use go run and point at the file that should be executed. That is convenient during development, but that's not the only way of executing the code, and that's definitely not how the code will be executed once you build it for production and make it available for other people. Because those people might not even have Go installed on their system, so they will definitely not use this command. Instead, you typically run go build in your Go project folder, and this will then tell Go to in the end create an executable file that could also be executed on systems that don't have Go installed. Here, however, when I try to run go build, I'm getting an error that it fails to find a main module. So what's this error message about now? So in order to see why this package here should be called main, we have to deal with this error, which complains about a missing main module. Now you might say, we have a main module, we have this main thing here, but that's a package, not a module. And that differentiation is important because Go does not just know packages, but also modules. And the idea simply is that one module consists of multiple packages. So in many cases, a module is simply a Go project. The project we're working on here, which at the moment consists of only one Go file, could be considered a module. It at the moment has only one package, but that may change over time. Now, in order to tell Go that this should be considered a module, we have to run a specific command, which thankfully is mentioned here in this error message I got. We have to run go mod init, and this will turn this project into a module. However, as you see here, I'm getting another error that it cannot determine the module path. And again, thankfully, it shows an example usage down there. Because you must give your module a name or a path at where it can be found. This can, for example, be a GitHub URL where you plan to host your module later, if you plan to expose it as a third-party library to the world. You can simply use some dummy path right now, though, like example.com first-app. That would be a valid module name. And if you now hit enter, Go indeed goes ahead and creates that module. To be precise, it added this Go mod file. And whenever you have such a file in your project, you have a Go module. So this file tells Go that the folder in which this file is stored and all its subfolders belong to a module of this name or path, to be precise. So now we created a module with a name or path, and with that created, we can now try this go build command again. And as you see now, this succeeds and I'm not getting any error. And as a result of running this, we're getting this first app thing here. If you run go build on Windows, you'll get a firstapp.exe, an executable file. And you can simply run that file by double-clicking on it. On macOS or Linux, you'll get an executable like this without a file extension, and you can run it from inside the terminal by typing // and then the name of that file. And you must be navigated into this folder where this file is. And if you now do that and you hit enter, your Go program executes and you get the same output as we got before when we ran this file with go run. But now we get this executable which can be executed without having Go installed. And that's of course in the end what we want to build if we want to share our application with other people. Because we can't force everyone to install Go on their system just to run our program. And that's why we need a module and why we need this main package. Because if I would now change this package name from main to app, let's say, and I then save this, if I now run go build, I get no file as an output. Because Go doesn't find a main entry point for our application. So it doesn't know where the application should start to execute when executed, and therefore it doesn't produce any executable. That's why you need to name this main, because this is basically a reserved package name that tells Go where execution should start. So with that name changed back to main, if I run go build again, I get this executable again. So that was a lot of talking about packages, modules, and why this must be named main. But these are crucial fundamentals which you must understand. However, this package is not the only thing that's named main. We also have this func thing here, which is named main. And this also must be named main. This is a so-called function, a block of code that can be executed by calling that function, and we'll get back to the idea of functions later again. And it is a function that must be named main because Go will call and execute that function, and therefore the code in that function, when the program starts. And just as the package must be named main so that Go knows where our application starts, at which files it should take a look, This function must be named main so that Go knows which code to execute when the application starts. Unlike other languages, like for example JavaScript, Go doesn't simply start at the top of some file and then execute it from top to bottom, so that you could, for example, have your code directly in the file like this. Instead, the main application code, like this, must be wrapped into such a function. You are allowed and actually forced to have this package and this import instruction in this file like this, not wrapped into a function. And as you will see later, there also are a couple of other things that can be outside of a function, but most of your code must be in functions like this, and you must have such a main function therefore, so that Go knows where your program starts and which code should be executed first. Therefore, you must also only have one main function. If you had a second Go file, which also belongs to the main package, which is allowed, that file must not contain another main function, because now we would have two main functions across two files that belong to the same package. And therefore, thankfully, I'm indeed getting an error here by that Go extension, which tells me that main is redeclared in this block, so that we basically declared it more than once in these two files here. And that's not allowed because there must be exactly one main function, not two. And this main function is therefore the other key component you'll find in any Go program that should be executable. If you're just building a third-party library that exposes some utility functions, so if you're building a package like this FMT package here, you don't need to have such a main function. If you take a look at the index of functions that are included in this package, you won't find a main function here. But the reason for that is that this package is not intended to be executed as a program. Instead, you just import it into another application, into another Go module, into another Go project, so that you can use functions from that package, in your program. But if you're building a program that should be executable, you need such a main function in such a main package. So that was a lot of talking about packages, modules, and this main function, but it is of course important to understand these key components that make up Go programs and how these different concepts work together. But now it's time to continue and take a look at values and types, and also variables and constants in Go programs. And it's time to write a bit of a more useful program than what we have thus far. Therefore, let's build a program that calculates the future value of an investment based on some input that's collected from the user. To be precise, I want to build a program that asks the user for the amount that should be invested, for the expected annual return rate, and for the investment horizon, so how long that investment should be held. And then, as a result, I want to get the future value of that investment based on that input. Now for that, I'll continue in that application we built thus far. I'll just rename my file name here from appgo to investment_calculator.go to be a bit more descriptive of what its purpose is. And I'll rename my module here inside that Go mod file to investment calculator like this. Now a brief note regarding that file name here. It's generally up to you how you want to name your files. For example, if you have a long file name like this, you could also name it investment-calculator.go, but it's a bit more common to use underscores for separating multiple words if you have long file names. You should not use blanks though. Instead, go for underscores, or if you absolutely prefer it, dashes. Now, when it comes to this module path, it's common to structure and write it like a URL, and therefore here it's not uncommon to have dashes in the name. So that's my renamed file. Let's now add some code. Now, of course, the goal of this application is to fetch input from the user. But to get started, we'll hard code some values here and will then later adjust this program to actually get values from the user. Now, in this program we want to build here, we'll need to deal with multiple different values. The principal, so the investment amount, the expected annual return, and the investment horizon. And for readability and understandability purposes, it makes sense to store these values in so-called variables, in data containers, you could say. A feature that exists in basically every programming language, which helps us store values in some container and then reference that container to use that value from any point in our code. And in Go, you create such a variable with help of the var keyword. Then you give it any name of your choice, for example, investment amount. And here, the naming convention, which is commonly used in Go programs, is this camel case notation here, where you start with a lowercase character, and if you then have a name that consists of multiple words, the subwords start with uppercase characters. And the goal is to pick a name that describes the value that will be stored in that variable, so in that data container. You then assign a value with an equal sign, and then here the value could, for example, be 1,000. If we plan to invest $1,000 or whichever currency you might want to assume for your program. Now with that, you see I'm getting an error here that investment amount is declared but not used. And that's of course correct. At the moment, I'm storing a value here in this container, in this variable, but I'm then never using that variable and therefore that value. But that will of course change soon. First, let's store a couple of values. So we can create a second variable here, which could be our expected return rate. And that could be 5.5, for example, if we're expecting an annual return rate of 5.5%. Last but not least, I'll add a years variable, which should store the number of years for which we want to hold this investment. And that could be 10. For example. So with that, we have the three values that we'll need to calculate the future value of this investment. And as mentioned, later we'll get this from user input. At the moment, it's hard-coded here in the program. And therefore now as a next step, we can calculate that future value, which we can also store in a variable. Future value would be a fitting name. But here, I now don't want to hard code some value, but instead, I want to store the result of a calculation. So what is the calculation that should be performed here to get that future value? Well, the formula for getting the future value of an investment is to multiply that invested amount with 1 plus our expected return rate to the power of years for which we want to hold that investment. So therefore here in our code, we want to multiply the 1,000, though not hard-coded like this. Instead, the idea behind storing it in a variable like this is to then take that variable and use that here, and multiply that by using the asterisk character, which is the multiplication operator in Go, as it is in many other programming languages. So multiply that investment amount with 1 plus that expected return rate, though here at least I stored it as a value that must be divided by 100 to be usable in that calculation, because otherwise 1 plus 5.5 gives me 6.5, and therefore here I want to use my expected return rate, so this variable here, and divide it with that division operator, this forward slash, which you also see in many other programming languages, by 100. Now we'll need to add some parentheses here, just as we do in normal math, to make sure that this code is executed in the right order. Because I of course want to multiply my investment amount with the result of this calculation. So we have to wrap this here with parentheses. In addition, you see that I'm getting an error here, and if you hover over this here, you see that the error is that I'm mismatching types int and float 64. So what's this about now? As mentioned in the first course section, Go is a statically typed language, so types are important in Go. And types refers to the types of values, because every value in your Go programs is of a specific type. And when storing values in variables, as we're doing it here, you can see the type of a value if you hover over the variable that stores it. And it's then here where you can see that type that was stored. For example, investment amount is of type int. So this value here is of type int. And int simply stands for integer, which describes a number that has no decimal places, no fractions. On the other hand, expected return rate is of type float 64, which is a number with decimal places. As you can clearly see here, this number has a decimal separator here. And these types matter, for example, in the calculation we have down here, because you can't just mix and match those types as we're doing it here. That I'm using investment amount, which is of type integer, in a calculation where I then also use this float 64 type. Now, one possible solution here is to convert this integer to a float when we need to use it in that calculation. And this can be achieved by using float 64 like a function built into Go, and wrapping it around investment amount. As you can see here now, the error now went away. Because this conversion function, which again is built into Go, converts this integer to such a float 64 value for this calculation. So the variable still contains the integer, but for this calculation, it's converted to such a float value. It still, of course, is 1000, but in this calculation, it's now 1000.0, you could say. So it's treated as a floating point number. And that's a requirement by Go. Now I'll show you an alternative solution in the next lectures, but for the moment, let's stick to this solution here. However, we're not done with this calculation yet, because at the moment I'm just multiplying my investment amount with 1 plus the expected return rate. But as I mentioned before, the formula is that we must take this here to the power of the years over which we want to hold that investment. Now in Go, unlike in some other languages, there is no built-in power of operator. But there is a package in the standard library that helps us here. It's the math package. So we have to import math here to use that package. And then we can use it down here in our calculation to access math.pow for power. And then we have to pass two values to this POW function here. As you can also see if you hover over it. Here you see the general definition of that function, and you, for example, see here between those parentheses that it needs two input values. Now the first value that should be inserted here is the value that should be taken to the power of something. In this case, 1 plus the expected rate of return divided by 100. And we can now get rid of this pair of parentheses since we're now inside this list of arguments here anyways. Then, separated by a comma, we have to specify the second input, the exponent here in this case. And that should be years for this function. Now, as you see, I'm getting an error here because years is actually an int, and this function here, if you hover over it, actually wants a float 64 value. So again, one solution here is to convert this int to such a float 64 value by wrapping it with float 64. And with that, it's not just the error that goes away, but instead we now also finished our formula here. This is the formula we can execute here in Go to calculate the future value of our investment. And this future value is then stored in this future value variable, which is inferred to be of type float64 by Go, because we're only using float64 values and operations in here. Therefore now, as a last and final step, we might want to output that future value. So we used some variables in a calculation, and we got started with working with types, and we had to perform some type conversions. Now it's time to output this future value. And of course, we already saw how we can output values. We can import that FMT package again, and then use it down here to call the print function to output something to the console. Though here I'll actually use the println function, which will also output something to the console, to the terminal where we invoke this program, but it will start a new line after outputting the value, which will simply make the output a bit easier to read. And it's then this future value that should be output here. With that, you should have no more errors in your code, and you can save this code. Now, as you see here, when I pressed save with that Go extension installed, my imports here got changed. Instead of having two import statements like this, I now have one import statement with parentheses and then one package per line. And that's the recommended and common import syntax when working with Go if you're importing more than one package. The other code here also would work, but that's what you'll commonly use. So split your imports across multiple lines, wrap them with parentheses, and import them like this. Important, there is no comma or semicolon after every import. Instead, you just list them like this. And with that, we can now invoke this program, for which we of course can open that command line again. Now we could again build that program and then run it, but of course during development you don't typically do that, because it is an extra step you would have to go through. Instead, you typically use go run during development to execute a file, and you could then target that file as we did it before, or if you have a module, as we do here, you can also just type go run dot. And this will execute this module, so the main package and the main function of that module. So if I hit enter here, you see I'm getting this output. And this seems to be the future value of that investment. Now, to verify whether this is correct or not, I opened up some future value calculator on the internet and entered the same data as we used it in our program. And if I press calculate here, I do get this future value, which is the same amount we got here in our program. So that works, and that's how you work with variables, types, and operators. So we wrote our first, slightly more useful program, and we got started with variables, values, types, and operators. Now, as you can see, this formula here is rather long. Well, I guess it could be more complex, but it is rather long because we have these type conversions in here, because Go doesn't allow us to mix different types. Even though we're just dealing with numbers here, as you saw for Go, numbers are not necessarily of the same type. Instead, we have integers and floats. And by the way, that's something you'll see in other programming languages as well. That's why we had to convert these integers. But of course, the conversions here unnecessarily bloat our calculation. So is there something else we could do? Yes, there is. If we know that we need to use these values, the investment amount and the years, in calculations that want floats, we can tell Go that these values should be stored as floats in these variables to begin with. Because what Go does here for investment amount is that it infers the type of value that is stored in that variable. It simply takes a look at that value and sees that this here, the 1000, is a value without a decimal place, and therefore it infers that it should be of type int, and it creates a variable of type int therefore. But of course this would be a problem if we would have an expected return rate of 5. Now it's also assumed to be an int, because this number has no decimal place, but of course the return rate should be able to accept all kinds of values where only some values are without decimal places. Most values will have one. So the inferred type is not always the type you want. Thankfully, you can override Go's inferred value though. You can add an explicit type annotation, a type assignment here, after the variable name. For example here, we could add float 64, which is one of the built-in types Go supports. You see all basic built-in types here, and we'll see some of them throughout the course. Float 64 is one of them. When assigning a type explicitly like this, you override the inferred value, as you see here, and you can still store a number that does not have a decimal place, as you see here, but internally, by Go, it will be stored and treated differently. And we can do the same here for the years, and also set this to float 64. And when doing that, since those numbers now will be stored and treated differently internally, we can get rid of these type conversions down here, because now we're already dealing with float 64 values, and we can therefore shorten this formula. Now it's much more readable, I'd argue. And with that, if we save this and we open our terminal, we can again run this program, and of course we get the same result as before, but now we don't have to deal with these type conversions. Now, of course, that will not always be an option though. Sometimes you might have a number that's an integer that should be used as an integer in some calculations and as a float in other calculations. And in such cases, you'll need to do some type conversions. But here, where we only use these numbers in this one formula, which wants floats, we can simply explicitly set our types of values. Now you might recall that in the first course section, I mentioned that Go has this focus on simplicity, clarity, and scalability. And that's indeed the case. But this code here is actually not as simple as it could be, because Go indeed offers a couple of features which allow you to write more concise code, of which we can use one here in this program to make the code a bit more concise at least. Because at the moment in this code, I'm declaring all my variables here with the var keyword. And in general, that is indeed how you can declare, so how you can introduce, you could say, a variable in a program. But if you have a variable assignment like this, where you don't set an explicit type, as we do it here, where we do set an explicit type. If we don't do that, like here, we can actually omit that var keyword and use a special assignment operator so that instead of that equal sign, we use colon equal sign. And this is basically a shortcut offered by Go, which you should use as often as possible. That's the convention and the recommendation, to declare and assign a variable where the type should be inferred by Go. So you can't add a type assignment here then. This would give you an error. But if you don't need one because you're happy with the inferred type, which in this case is float64, that's the recommended shorter way of assigning a variable. And we can also use this approach down here. We don't need to explicitly set a type for a future value, therefore we can also use the shortcut here. Now, one other variable related thing you can do in Go is that you can declare and also define multiple variables in the same line. For example, here, where investment amount and years have the same type, I could add a comma after investment amount and add years here, and then add a comma after 1000 and specify the value for years here, and then get rid of that variable down there. So now here, 1000 would be used as a value for investment amount, and 10 would be used as a value for years. You can also omit the type assignment. In that case, it would be inferred again. And you could then also specify multiple values of different types in the same line. And Go would now infer that investment amount is of type int, whereas years is of type string. If you do explicitly assign a type though, all variables in that line must be of that type because the type comes last. You can't add multiple type assignments one after each variable. This is not allowed, this is. But now of course we must also assign proper values of that type. We could of course now also shorten this even further here and get rid of that type assignment and of var if we want to use this shortcut here, which also works with multiple values in one line, in which case we just have to make sure though that these values are inferred as floats, which we can enforce by adding a decimal place. So we can of course simply add .0 here, and with that Go will infer that these values will be of type float64. And we could have done that before with that longer syntax as well, of course. But now this allows us to use the shorter syntax, and therefore now we can of course also move this variable into this line and also initialize it there, separated by a comma. So now all variables are declared and defined in one single line. But I will also say that it's up to you whether you want to use this super short notation here or not. I personally find that it can make programs a bit harder to understand, since I now have to take a closer look to find out which value refers to which variable. Therefore, I personally prefer to split this up across multiple lines, like this. And I'll also bring back that type annotation here, which means we can't use this short assignment operator anymore and instead have to use var, just so that we also see this syntax here for comparison again. Ultimately, it is of course up to you which approach and style you prefer. I just want to show you these options so that you are able to write short and concise Go code. So now that we have this basic program here, I want to enhance it by now also considering inflation. Because of course our real future value will depend on the rate of inflation we'll have every year. For example, if the inflation rate would be higher than the expected return rate, we would end up with less money after all these years than we had at the beginning. At least after considering inflation, of course, so the real value of that money. So how can we consider inflation here? Well, we can add a second line here, and create a new variable that we could name future real value, which should be the inflation adjusted value. And here I want to divide my future value by 1 plus the inflation rate to the power of years. We could also merge it all into one formula, but here I'll split it up so that we'll have two values, which we then could also compare. Now in this program here, I eventually want to allow the user to enter values for the investment amount, the years, and the expected return rate. But I don't want to allow that for the inflation. Therefore, we could of course add the inflation as another variable here, but we could now also add it as a so-called constant by using the const keyword instead of var. With const, you still create a data container just as with var, but unlike with var, you'll not be able to ever change the value stored in that container. Now we're actually never changing any of these values here either, so we could have used const here as well, but that will change in the future. So therefore here I'll add a new data container with const to create such a constant and name that constant inflation rate. And then, just as with a variable, we should store a value in there. And here I'll choose 2.5, let's say, 2.5% per year. And you can of course choose any value you want. If you choose a value that has no decimal place though, you might want to explicitly set this type to float 64 so that this inflation rate can be used in calculations without issues. Here I'll choose a value with a decimal place though. So with that we got that inflation rate. Now we can use it here in this formula by again using math pow here and then passing 1 plus inflation rate divided by 100 as a first value to this POW function. So the same conversion we did with the expected return rate, I'll do it here with the inflation rate. And then pass years as a second value. And with that we'll get our future real value. And that's all. That's one way of considering inflation. And with that we can then of course also output that by adding another print line statement here. And here I want to output the future real value. With that, if we save this code, we can of course again run this application with go run dot. And as a result, I now get two values here, where the second value is the value adjusted for inflation. And as I mentioned, if we now would assume an inflation rate of let's say 6.5, which is higher than my expected return rate in this case, and I save this, and I then run this program, our inflation adjusted value would indeed even be lower than the starting value we had at the beginning. And that's how we can incorporate inflation here and how we can work with constants. Now at this point here, it's not super obvious what the real difference between constants and variables is, because we're basically using this constant as we're using these variables. But the key difference is that variables can be reassigned. We could, for example, set investment amount to 2,000 here, so that it's 1,000 initially, and then later in our program, we set it to 2,000. Now, of course, in this program, that doesn't make too much sense though. We could have just set it to 2,000 right away here. But this will make sense in other programs where values can indeed change. For example, here in this program, once we start fetching user input. So let's now finally make this program a bit more helpful by also fetching user input. To be precise, I want to allow users of this application to enter their own values for the investment amount, for the number of years, and the expected return rate. Now, thankfully in Go, getting a value from a user is pretty straightforward because this fmt package, which we're already importing, does actually not just provide us functions for outputting something to the terminal, but also functions to get input from the terminal, so to allow the user to enter values into the terminal. And the function we can use for that is the scan function, so that we scan the terminal for input, you could say. Now, the scan function works such that we have to pass one or more, I'll get back to this notation later in the course, one or more variables, you could say, to scan, and scan will then populate those variables with data entered by the user. Scan then actually also produces some values we could use, but we can ignore them for now. We did see a function that produces a value in the past already. The power function provided by the math package produced the result of taking this value to the power of this value, and we used that result in our calculation. Here for a scan, we're not interested in the result of calling that function. Instead, we just have to pass a variable to it so that it's populated with some value. So for example, if we want to get the investment amount, we could pass the investment amount variable to scan. However, if we would do it like this, it actually wouldn't work. Instead, you need to pass a so-called pointer to this variable to scan, and you do that by adding the ampersand symbol in front of that variable name. So this symbol here, it must be added in front of this variable name. Now, pointers are a super important topic in Go, but they're also a bit of a more advanced topic, which is why we'll explore them in depth later in the course. For the moment, you just need to know that you need to pass such a pointer to scan and that you create one by adding this ampersand symbol in front of that variable. That then allows scan to populate that variable with a value, and therefore, after executing this line of code, investment amount will be whichever value we entered into the terminal. So we can therefore save that code, open that terminal again, and again run our application. And as you'll see, the application now seems to get stuck. We don't get a response, we don't get any output here. And it's getting stuck because of this line of code. This now waits for some user input, and that's why the application got stuck down there. Indeed, we now have to enter a value here, for example, 2000. And if you then hit enter, the application will continue, and now the future and the real value will be based on that investment amount. And that's how easy it is to fetch user input. And here you now also see the idea behind using variables. This investment amount variable here has an initial value, but this value then gets overwritten by whatever the user enters here. Therefore, since we always fetch input from the user here, we can of course also get rid of that initial value, which you can do when using the var keyword and declaring a variable like this. Now we just declare the variable, so we just make Go aware of the fact that this variable exists, but we don't assign an initial value. We don't define the variable as it's called. Instead, we wait for that user input so that we then have a value for that variable. And this now, for example, would not work with a constant. If I would try to pass inflation rate here, I would get an error that this is an invalid operation, basically because it's a constant. And constants can only be set once and can never change thereafter, no matter if you assign an initial value or not. And indeed, with constants, you have to assign an initial value since they can never be changed. Therefore, they always need an initial value. Variables, on the other hand, don't. And that's why variables are an important concept in Go, but actually in programming in general, no matter which language you're using. So now that we explored the first set of crucial, fundamental core concepts, it's time to practice what you learned, because of course, as always, only practice makes perfect. And I want you to build a profit calculator, a command line tool built with Go, of course, that asks users for revenue, expenses, and tax rate input, and that then calculates earnings before tax and earnings after tax, as well as the ratio between these two values, and that then outputs these three values. So that we got such a profit calculator that we can use to calculate any profit based on these three input values. Now for that, you can create a brand new Go project. Attached, you also find a brand new Code Sandbox project snapshot so that you can use that as well if you don't want to follow along locally. In the next lecture, I'll show you my solution, but definitely give it a try on your own first. So, did you succeed? Let's build this profit calculator application together. Now for that, in that brand new project here, I'll start by turning this into a Go module so that I could build it and create a standalone executable. Now, if you did not do that, that's fine. It was not explicitly stated in the task description, but here I'll do it with help of Go mod init, and then any path of your choice. For example, here I'll use example Go basics-practice. The name, of course, is up to you. This creates this Go mod file here, and with that created, I'll then, as a next step, add a new file. And here I'll name this profit_calculator.go. Now in this file, you should of course start by adding this package clause, so by marking this as a package, and here we should use the name main because that is our main entry point, and at the moment also the only package we need. As a next step, I then will add this main function, which, as you learned, contains the code that will be executed whenever this application starts. Well, and with that, here, for this task, we'll then need three different input values, and therefore I'll create three different variables here with help of this var keyword. Because we'll need the revenue from the user. And we could set this to int here or to float 64 to accept values with decimal places. But I'll start with int to see whether that will become a problem or not. We then also need the expenses, and I'll also set those to be of type int. And then the tax rate, which definitely should be a float, because the tax rate should be something like 25.8 or something like that. It could also, of course, just be a flat number like this, but it most likely would be some number that has a decimal place. So that's the first step. Now, of course, we have to ask the user for values for these variables. And you learned how you can do that with help of the FMT package, which exposes this scan function you can call. Now scan, as you learned, needs a variable as an input, or to be precise, a pointer to a variable, which is created with that ampersand symbol, and then, for example, revenue, so that the user is able to enter a value for the revenue. Now, to give the user some information for which kind of value we're waiting here, I'll also print something to the terminal with print, not println, so that we don't enter a new line. And here we could simply say revenue, like this. And then we can repeat this step and also ask for the expenses here and populate expenses by using an expenses pointer. And then one last time to also ask for the tax rate like this and populate the tax rate. So with that, we're fetching all that data from the user. Now we can use it in a calculation to get the different values we want to get, which were earnings before tax, after tax, and then the ratio of these two values. So the earnings before tax, the EBT, would be the revenue minus the expenses. So we can create a new variable EBT. We could do it with the var keyword, but we can also use the shorter notation here with colon equal sign, since we'll immediately store a value in there, and that value will be the result of revenue minus expenses, using the minus operator to deduct a number from another number. And this operator works with integers here, as you see, so we got no problem regarding that, and EBT is now inferred to be an integer. Now, of course, that's not all we need. Instead, we also want the profit, so the earnings after tax, and we can get that by adding a new variable, which we set equal to EBT times 1 minus our tax rate. So minus this tax rate. Now in my case here, I expect to get a tax rate that is something like this, and I instead need a value that looks like this. So 25.8, for example, should be translated to this value. And we can achieve this by dividing this tax rate by 100, so that here we have tax rate divided by 100. But now we of course again get a problem because we got mismatched types here. We're mixing an integer with a float 64 in the same calculation, and as you learned before, Go doesn't really like that. Now as a solution, we can of course convert EBT, which is that integer, to a float, and the error goes away. Alternatively, we can of course also change the types of the revenue and expenses variables and change them from int to float 64 here and here. That also has the advantage that we allow the user to enter revenue data like this, for example, which otherwise would not be possible if we're waiting for an int. So we gain more flexibility by expecting a float value here for these values. And we don't have to convert any types then. So with that, we then also got the profit. Now we also need the ratio of EBT and profit. So EBT divided by profit. And for that we can add another new variable, ratio, which is EBT divided by profit, just like this. And with that we got the three values that we need, and we can now output them. With the format package again, and now println, so that we do enter a new line after every print statement, and we therefore output every value on a new line. And we can then output EBT, and then profit, and then also, of course, the ratio. And that's now all. With that, if I save this, we should have all the code we need. So if we open the terminal here and we run this application, I'm asked for the revenue, let's say 10,000. Then my expenses, let's say 7,500. Then my tax rate, let's say this is 30%. And as a result, I get my EBT, so the earnings before tax, which is 10,000 minus 7,500, this value here. Then the profit after deducting the tax rate, and then the ratio of these two values. And that's therefore now my solution for this exercise. So I'm back in our investment calculator here, because we can still improve that code base here, refactor the code, and dive into more important Go features. Now, one small problem you maybe saw in the previous exercise where we built this profit calculator, which you can also see in this application here, is that when we're outputting these values here, so if we run this application and we enter our values here, we get that output, but it's not really that helpful. We basically have to know the code to know which value is what. We got no extra information in that output. And it would of course also be nice if these numbers would be rounded or something like that. So when it comes to outputting values, so to formatting text, strings as it's called in Go, in general, it's again this FMT package that can help us. For example, one easy way of quickly adding some extra information to this output here is to simply pass multiple values, multiple arguments, as it's called, to this println function. For example, if we want to share the information that this is the future value in the output we're showing in the terminal, we can add an additional string, an additional text here, and then separate this with a comma from the second value that's passed to println, and then here, for example, output future value colon. And thanks to how println works, it will now output both values in the same line, separated by a blank. So therefore, if we save this and we then run go run dot, we get asked all these questions, of course, so that we have to answer them, but then here you see that we now got an output where we get this extra future value text. So that's one easy way of adding more information to the output we're showing in the terminal. And we could of course also do that for the second line here and say future value adjusted for inflation or something like this. And unsurprisingly, when running this, we now also see this information in the terminal here. So that's a relatively easy way of outputting multiple string values or values in general in the console. But it's not the only way of formatting strings. Because, for example, it would also be nice if this future value number here would be formatted in a more readable way. I mean, we don't really care about all these extra numbers here. For us, it would probably be enough to have 2 digits of precision here, or maybe no decimal digits at all, so that we just output this number. And that's thankfully also pretty easy to do, again with help of the FMT package. Now for this, I'll comment it out by adding 2 forward slashes. That's how you add a comment in Go, and comments are then ignored by the Go compiler and runtime, so they're just there for you as a developer. And you can use this feature to add extra helpful text, like outputs information, that explains your code. But you can also use this comments feature, as I'm using it here, to comment out code which we want to keep around, but which we don't want to execute at the moment, so that we could still bring it back in the future if we want to go back to that code, but we don't use it right now. Because now I do want to output my content differently. Again, as mentioned, with the FMT package, but now not with println, but instead with printf, which stands for print the text in a formatted way, you could say. And you see the description of this function here, that it will output text with a certain format, which we can specify. Now, to learn about all the formatting options, you can dive into the official documentation of the FMT package in the official standard library documentation. There, if you search for FMT, you can dive into that documentation, and there you find some information on how you can format text, or which placeholders you can use in your print functions, or in your printf function to be precise, to format some values that are output in that text. For example here, if I want to output future value, colon, and then the value, we could of course separate it with commas with help of println, but when using printf, we can also use a special placeholder, the $V placeholder, which is the placeholder for outputting a value of a variable or constant. And then you have to pass a second argument to printf, which contains the value of that placeholder. So in this case, the future value, like this. If I do that and I run the application again, you'll see that now I also still get my future value, but now without using println. Therefore, it's now also not adding a line break, because we're not using println again, but you can manually add that with \n, which is another special identifier, you could say, which you can add in this text here. And you can actually add this in any string, and as many of those as you want, to add line breaks there. This would then, for example, also allow you to now also add this text in the same printf text here, and also output the future real value by again using this %v placeholder and commenting out this code, since we're now outputting everything in this one line. And then here we can refer to the future real value. So you have to add as many arguments after this initial text here as you have placeholders in this text. And you have to add them in the order in which they should be used for those placeholders. So with that, again, if we run this application, we now get this spread across two lines because of this line break identifier we added here. And we got the same output as before, but now with one printf statement. And of course, that's now arguably a bit harder to read, and you therefore could stick to the approach we used before, but of course I now want to introduce you to how you can use printf to format text. Because outputting the values is not all you can do here. Besides outputting the values of variables in text with help of printf, you can also output other information. If you take a look at the official FMT package documentation, you see that besides using %f as a placeholder to output the value, you could, for example, also use %T to output the name of the type of a value, if you're interested in that. By the way, if you want to output a percentage sign, you would simply add 2 percentage signs, and that would output 1. Because one percentage sign standalone would be interpreted as your approach of outputting some placeholder, since they all start with percentage signs. But that's still not all you can output. Instead, you got many different placeholders for outputting different kinds of values and formats. For example, also this %f placeholder, which can be used to output a decimal number. And as it turns out, you can also use this to control how many decimal places you want to output. And you can learn more about that if you scroll down, because here you now find some information on how you can use %f with different additions to control how that decimal number will be output. Now let's start simple, and let's just use %f instead of %v for both values. And let's see what that gives us if we execute that code. As you can see, it gives us a slightly different output than before, because these numbers are now a bit shorter. But they're not short enough for me, because we can make them much shorter if we add .0 between the percentage sign and the f. The number after this dot simply controls how many decimal places you want to output. And with .0 will of course output none. Therefore, if we run this again, you see that now we get the rounded numbers without any decimal places. Now, if we instead want to have one decimal place, we can use .1f. And with that, if I enter my values, I get one decimal place. And that's why printf is a pretty powerful function provided by the FMT package, because it gives you a lot of options for outputting and formatting different values in your text. So we're fetching user input here, but of course at the moment, if we run our application, we're not really providing a great user experience here. It's not obvious for which kind of input we're waiting here, or that we're waiting for any kind of input actually, because we're not telling the user of this application about our intentions. Therefore, here we can improve this code by not just waiting for user input, but by showing some helpful message before we scan. And for that, we can use the print function, not println, but just print, to output some text without starting a new line thereafter, so that to the user it looks like as if they enter their value in the same line as this info text. And here we could say investment amount, colon, and then a white space to have some space between this info text and then the value that will be entered by the user. With that, if we now save this and we run our application again, we get this useful text here, and now it's much clearer which kind of value I'm entering here and that some value is expected from me in the first place. With that, the program still works as before, but is more user-friendly. And we can therefore now, of course, also fetch these other values. And you can definitely try this on your own first. We'll do it together after a short pause, which I give you, so that you can pause the video and try adding the code for fetching the years and the expected return rate on your own. Thereafter, we'll do it together. Did you succeed? Let's now fetch that input together. Of course, we again use scan to get the input, and then we populate the years again by also adding the ampersand in front of years, since you need to pass such a pointer to scan, as mentioned. Again, it would also be nice to have a little info message here, so therefore I'll copy this code here and also use it here and ask for the years or investment horizon, whatever you want. Here I'll just use years. And of course I also want the expected return rate, so I'll copy that and actually ask for that before I ask for the years, but that's of course optional. And ask for the expected return rate like this, and then by populating expected return rate like this. So that should work. Now you could of course now try to remove the initial values, since we don't really need them here for years and expected return rate either. But if you do that, you'll get an error, because you can't declare variables like this. That's too short. Go doesn't really know what you're trying to do here. Instead, if you're not assigning an initial value, you always need the var keyword. And you then also always have to explicitly define and set the type of value that will eventually be stored in that variable. Because in Go, every variable must have a clear assigned type, because Go is a statically typed language, which in a nutshell simply means that every place where a value is stored or used must have a type that's clearly defined. And therefore here we must let Go know about the type of value that will eventually be stored in years. And here it of course can't infer that because we have no initial value. If we had a default value, we would not need to do that, but here we need to set a type. Now we could also migrate the expected return rate to this notation now, but we could of course also say that we maybe want a default value for the expected return rate here. So we could also keep it like this, and here I will keep this syntax and this alternative way of creating a variable so that we also still see it in comparison. With that though, we're now defining all these variables and we're fetching all that input, and that should therefore be it. If we now save that and we open the terminal again, we can run our application and then enter those different values and enter a value for the investment amount, for the expected return rate, and for the number of years for which we want to hold this investment. And as a result, we'll get this output here. Now, the FMT package does not just offer println and printf though. Sometimes you don't want to output a text in the console, or maybe at least not immediately, but you instead want to format it, change it, and store it in a variable. And printf and println and all these functions that start with print wouldn't allow you to do that because those functions will always immediately output the text in the console. If you instead want to generate a new string, which you can store in a variable, you can use an almost equally named function called sprint or sprintf if you want to use these formatting features, or println if you don't want to format the text but you want to add a line break after the text. So for example here we could use sprintf to create a new text value, a new string that will be returned when you call sprintf. That here is the return value of that function, so the value this function generates when you execute it. And you can then store that value in a variable. For example, formatted fv. Now this is a new variable, and I use this short syntax for declaring and defining it. And then we could grab this text here from down there, paste that here, but now here I only want to store the formatted future value, so I'll get rid of this adjusted value. I'll keep the line break at the end though. And then here we can pass, and we have to pass, future value as a second argument, so that this will be used for this placeholder. And now we could repeat that to also have our formatted RFV, the real future value, where we also call fmt sprintf to generate a new string. And we now can, again, copy this, I guess. Make sure we only have one pair of double quotes. And now keep just that future value adjusted for inflation text, and also add a line break there at the end. And then pass that real future value as a second argument. And with that, we can now, of course, also comment out this code here, and instead now use fmt print again, which does not add line breaks and which does not support formatting, and just output formatted fv and formatted rfv. And since the line breaks are already included in those strings, we'll have them, and the same is the case for the formatting, because these strings now already contain the formatted line broken strings, and here we then just print those already finished strings to the console. So if we save this now, and we run the application one more time, we get this output here. Now actually I got the line break placed incorrectly here for this adjusted future value, because of course it shouldn't be added here. It should be here after the number. But with this now, if we execute this, everything's looking good. So there is a lot you can do with strings, with text, as you can tell, but there's one additional thing you should know about strings, which I also want to show you here. Let's say we don't want to use this approach, which we added in the last lecture, but instead this code here, where we output everything in one line, but in a formatted way. Now, of course, this line here is rather long. What you could do in such a case is split that text across multiple lines. Though, as you see, here I'm getting an error. The reason for that is that you can't split a string across multiple lines if you're using double quotes. Instead, you have to replace the double quote with the backtick character. So that's not a single quote here. Instead, that's the backtick character, which is a special character on your keyboard. You'll find it somewhere, and you can use that for opening and terminating the string. And when using this character here for enclosing the string, you can add line breaks there, as many as you want. Now, if we run this code now, you see that this, of course, might look a bit strange because of all those line breaks we added here. You also see that this line break placeholder here, which we used before, is now no longer treated to break the lines. Instead, it's now treated as regular text. Because we're using these backticks and their line breaks are simply added as visual line breaks in your editor, you could say, as actual line breaks therefore. And therefore this has no longer any effect. And whilst I won't use this here, because I prefer the other approach, where we have these standalone formatted strings, it is something you should know, because sometimes, of course, you'll be working on Go programs where you might have some longer text, which should be all in one string, and which should be broken across multiple lines. And in that case, this backtick character and this way of creating strings can be helpful. So now that we learned a lot about packages and how to import packages, values, types, variables, constants, how to get user input, and how to output content, as well as how to format text, and how we can perform calculations and use operators like the multiplication, plus, or division operators. Now that we learned all those things, it's time for the next important main Go feature you must know. And that would be functions. So what is a function? Well, we already have one here. This main function. And I sometimes like to call functions code-on-demand blocks. Because the idea behind a function like this main function is that you define some code which is only executed at the point of time where this function is called. Now, the main function is actually a special case, as you already learned, because the main function, of course, is invoked by Go when the Go program starts. But we see other examples for calling functions here, for example, where we call the print and scan functions that are exposed by the FMT package. So these also are functions, just not functions defined by us, instead functions already built into Go. But here we're calling functions on our own, and therefore then those functions do their thing and execute the code that has been defined for them. And you can actually see that code because in the official standard library documentation, if you take a look at a specific package, like this FMT package, you'll find a repository link in there, which you can click to be taken off the code repository of the Go language itself. Because all the code behind Go and the standard library is publicly available. And here in this repository, you can dive into the src folder to find subfolders for all these standard library packages, like the FMT package here. And you can then, of course, take a look at that code and, for example, there, take a look at the print.go file. And in here, you'll find all the code that is related to printing, so to outputting and working with text. And in there, in this file, you will, for example, if you search for it, find the printf function. Here it is. And that is now Go code for defining a function that can be executed to perform a certain task. And it can, by the way, be interesting to explore the official Go code to get ideas and inspiration on how you could write your own code, and of course also to understand how some of these built-in functions work. But that's the idea behind functions. It's code on demand which is only executed when the function is called, which in case of the main function is the case immediately when the app starts, but which in case of print and scan, for example, only happens when you call these functions. Now, of course, as a Go developer, you're not limited to using built-in functions like print and scan or defining this special main function. Instead, you can also build additional functions. And typically that's done below the main function here, so that you can, for example, create a new function by using the func keyword. That is how you do define a new function, with help of that func keyword. And then you can give this function any name of your choice. Now let's say here we want to create a utility function that wraps this code. Now we can argue how useful such a function actually is, but for practice purposes we can build it. So we could build our own function that could be called print or maybe output text, something like this. So that's how you give your function a name. And then when defining a function, after the function name, you have to add a pair of parentheses, which can be used to define any input parameters this function should take. And I'll get back to this in just a second. Then, after these parentheses, you add curly braces, opening and closing. With this, you create the so-called function body. So between those curly braces, you put the code that should be executed when this function is called. Now, since this should be a utility function for outputting text, we could use the format package in there to call print, like this. So that's how we define a function, that's how we call a function. And therefore this basic first function here is simply a wrapper, you could say, around the print function exposed by the FMT package. But of course, at the moment, this function isn't actually too useful. Now, to be more useful, this function here should accept some input arguments, or at least one input argument. So one input value that has to be passed into this function from the place where the function will be called in the future. And to accept such an input argument, you go to these parentheses and then simply add any name of your choice, like for example text. That's now the name of the parameter this function expects. Now, when adding parameters to functions, you also always must give them a value type by simply adding the type after the parameter name, like string here. And of course here you could accept any type of value you want. But here it's a string. You can also accept multiple parameters, for example a second text, by separating them with a comma here. And you can add as many as your function needs. Now, if your parameters happen to be of the same type, you can also shorten this notation and just have your parameter names here, and then thereafter the type of the values that should be accepted for these parameters. When using this notation, all parameters must accept the same type though. If you add the type after each parameter, you can instead also accept mixed types. And you can also go for this notation if you want to be very clear about which parameter receives which type. Here, however, I only need one parameter, so I'll get rid of the second one. And now you can use these parameters inside of this function body and only there, like any other constant or variable. So if you want to output the value stored in text, so the value received on that text parameter, you can simply use it like this here. And with that, we can now use our custom function in all the places where we want to output text, a single piece of text to be precise, because we only accept one text parameter. So I, for example, at the moment can't use it here because here I actually want to output 2 pieces of text. We could of course accept 2 parameters, but here I just want to accept 1, so therefore we can use it, for example, for those outputs here, for those print statements. So instead of using fmt print here, we can use our own custom output text function and then pass the text that should be output as an argument here. And as you can see, if I don't provide a value for this argument, I actually do get an error that I'm not passing in enough arguments to output text, that I pass none, but it actually wants 1, which is of type string. So these error messages are really helpful, of course, and help you find and fix errors quickly. So therefore here, I will add this text, and we can now repeat this here, where we also output expected return rate, and then also here to output this year's text. And that's how we can define and also use a custom function. So that's how we can define and then also call functions. Now, functions can do more than accept a couple of parameters and then do something. For one, they of course don't have to accept any parameters at all if you don't need any input values, but this function, for example, needs some. But they can also, in addition, produce values and return values, so that you can call a function, get back a value, and then use that value in your other code. And that's, for example, what this math_pow function does. It calculates a new value based on these 2 inputs, these 2 arguments that have to be passed to the function. And then this POW function generates a new value and returns that value, which is then used here in that place where that function is used. So that we multiply investment amount with the return value of this function. And of course, we can also build our own function that returns a value. And we could, for example, do that to outsource this calculation logic into separate functions. So we can add another new function, which could be called calculate future value. And this then should be a function that performs this calculation. So of course, we can copy that code, that operation here, that calculation code, and paste that in here. And then you can add the return keyword in front of that, which is a built-in special keyword recognized by Go, which will tell Go that this value should be returned as a result by this function. Now in Go, unlike in many other programming languages, you can actually pretty easily return multiple values, simply by separating them with a comma here. So we could, for example, name this calculate future values to be a bit more descriptive for what it should do, because then in addition, we could return this inflation adjusted future value. So we can copy this and then add this after this comma as a second returned value. So now this function returns 2 values. Now, since this is a bit hard to read, if this is all in one line, we can then of course also create some variables in here and get our future value, which I'll just name fv here, which stores the result of this first calculation here. And then our real future value, rfv, which stores this result. And then we can just return fv, rfv. But as you see, I'm also getting some errors here, because I'm now referring to some variables in here which are not defined inside of that function. Investment amount, expected return rate, and so on are not defined in here. Instead, they are defined inside the main function, and therefore they are scoped to that function. Because in Go, as in many other programming languages, any variables or constants that are declared in a function are scoped to that function and are only available in that function. Now what you could do is, for example, you could grab that inflation rate constant, cut that from the main function, and then either add it to this calculate future values function, or if you maybe need it in another function as well in the future, you instead put it on a higher level in your code, outside of any function, right into the code file like this. Now this does not work with all code. For example, we can't call a function here. This does not work. This has to go into another function instead. But you can add constant and variable declarations outside of any functions right into the code file like this. And when you do that, that constant or variable is scoped to the entire code file instead of a specific function, and is therefore available in all the functions of that file. So now inflation rate, for example, is available down there, and we're no longer getting an error for it down here. Now we could therefore do that with all these variables and also move those outside of any functions, though as you see here, you then can't use this shortcut for defining a variable. Instead, you'll now have to do that with the var keyword, like this. And with that, all these variables would be scoped to the entire file. However, that's not what I want to do here. I'll do that for that constant, since that will never change, but I'll not do it for the other variables. Because instead, I'll add these variables here because they will be defined, they will be set in that main function. So I want to keep them close to that place instead of declaring them as global variables, because if we would actually declare them outside of main like this, we could theoretically execute this code here where we use these variables before they have been set. Keep in mind that investment amount and years initially have no values, so they have a default null value, which in case of floats is the number 0, but they don't have the value we need for this program. Therefore, to make sure that under no circumstances I'm accidentally calling this function here without the proper values being set for those variables, I'll move that code back into the main function, and we can then also go back to this shorter notation if we want to. And I'll instead get those values into calculate future values by accepting some parameters here, just as we did it with output text. So here in calculate future values, we can now expect the investment amount, which should be a float 64 value. Then as a second parameter, this expected return rate, which should be a float 64 value. And then also the years, which should be a float 64 value. Since we have the same type of value for all three parameters, we can then also shorten this, as you learned. And with that, most of our errors down here went away. Now we have one more error here, because I'm referring to future value, but I now named it FV, so we should use this name here as well. And once I do that, all the errors in these two lines went away. But now we got new errors here. And the problem down here is that now we actually return too many values. Because we actually do return 2 floats here, when we shouldn't return any. But wait a second, why shouldn't we return any values? We do have that return keyword here, and I mentioned that you can return values in your Go functions. Well, you can, but since it's a statically typed, type-safe language, you have to define your intention regarding which kind of values you plan to return in a function when you start defining that function. Here in this line, you don't just have to give this function a name and define any parameters needed, but instead, you also must add the return types here before you open the curly braces, but after your normal parentheses. And here you would add float 64 if you would return one float64 value, or if you return two, you have to wrap that with parentheses, separate it with a comma, and add a second float64 type. Or whichever types your functions return. Here it's twice float64. If you had a function that returns float64 and an int, you would write it like this. But again, here we need float64. And with that, the error now did go away. Now we can use this newly added calculate future values function and call it in our main function. By adding parentheses like this, that's how you call a function, and by then passing our input values to that function. And here, if we hover over this again, we can see that as a first argument, we need to pass in the investment amount, as a second argument, the return rate, and as a last argument, the years. So let's do that. Investment amount, expected return rate, and years. And that's how we call this function. But since this function now also returns two values, we of course should use these values somehow. And here I want to use them by storing them in new variables, to be precise in these two variables, which we then use in the code thereafter. And indeed, if a function returns a value, you can simply store that value in a variable. So here I'll store it in future value. If a function returns two values, you have to define multiple variables separated by a comma, so that I also have my future real value here. And then the first returned value will be stored in the first variable, and the second returned value, as you might guess, in the second variable. And that's how we can outsource these calculations into a function. Of course, alternatively, we could have also created two functions, one for each calculation, but since I wanted to show you this feature of returning multiple values, I went for one function here. Now, when creating a function that returns values, no matter if it's one or multiple values, there also is an alternative syntax you could use for returning these values. Instead of having your return keyword and then a list of all the values or variables that hold values that should be returned, you could go to the place where you define your return value types and give those return values names here. For example, FV and RFV. So the same names I'm using here in my code then. That will then actually tell Go to already create variables of that name, FV and RFV, and you can then use these variables here. Therefore, you don't have to declare them, instead they already exist, so you don't need this colon equals sign operator here, which creates and initializes a variable, but instead just the equal sign. Since the variable was already created, therefore you just need to assign a value. And then you could continue to return the values like this, but alternatively, you can also just type return. And Go will automatically return these variables, so these two values. Therefore, if you save that code and you run the application, you'll get the same result as before, but now with this alternative notation. But I personally actually prefer explicitly stating what I return, because especially if your functions get more complex and longer, it can become confusing if you just have the return keyword there. Because you then have to go back here and see which variables were specified here and find them in the code. And I personally don't like that, but of course you can go for that shorter style if you want to. I will keep these variable declarations here in place though, because it can indeed make a function a bit easier to understand if you give your return values names here, but I then explicitly return them like this. Again, it's up to you which approach you personally prefer. So now that we also learned about functions, I want to give you another opportunity to practice what you learned. And for this, I'm back here in this profit calculator, which we built in an earlier exercise. And attached, you find my code snapshot here, so that you can use that if you did not do that past exercise. And my task for you here in this profit calculator is now that you replace this code here with a custom function that should output some text and then wait for the user to enter some text and then return that entered value. And then in the main function, you should call that new function that gets user input and store the result in one of these variables. And then you should also outsource these calculations into a single standalone function that should perform all three calculations and return all three values. Now, definitely try this on your own first. Thereafter, we'll do this together. So, did you succeed? Let's do this together now. And I will start with a function that gets the user input for different values, so for different text. For that, we can define a new function here, and I'll name it getUserInput. Though, of course, the name is up to you. It just should be descriptive and describe what this function will do, so which kind of operation will be performed. And then in here, I want to execute this code. So I'll copy that code and use that in here. Now that text, of course, should be dynamic. Every time this function gets called, this text will be different, since I'll fetch different pieces of user input. And therefore, I'll accept the parameter here, which I'll name infoText. The name, of course, is up to you, but it should be of type string. And I'll then print this infoText here. Now, regarding getting that user input, we need that special pointer value. But that's not a big problem because we can simply create a variable here. Let's say a user input variable, which should be of type float64 because that's what we'll need later. So here I'll set this to float64. And then it's this user input variable, which I'll use instead of revenue here. So that user input will be set by scan. And therefore here, after calling scan, we can return that fetched user input, which is a float64 value. Now, as you learned, you need to let go know about your intentions though, and if I plan to return a float64 value as I do here, I therefore have to add float64 here as a return type annotation after this parameter list and name. But with that, we can now call this function and replace this code here with our function call, and here I then pass the revenue info text to get user input. Now the way we wrote this function will then get back that user input as a value, and therefore we can then store that in this revenue variable, which I declared here. Alternatively, we can now also use this short declaration and assignment form here and get rid of that separate declaration here. And now this can be repeated for expenses and tax rate. So here I'll actually comment out expenses and instead set expenses here equal to get user input with expenses passed as an info text to this function. And then I'll do the same for the tax rate and set tax rate equal to get user input asking for the tax rate here. And with that, we can also get rid of this code here. So with that, we got these variables, and actually we can also get rid of this code here to make this even more concise. And we can now work on that second function you should create, a function that performs these calculations. So for that, I'll add another function here, and it doesn't matter if I do that before or after get user input. Here, to have it all on the same screen, I'll do it before get user input, and I'll name this function calculate financials because we'll calculate multiple numbers here. To be precise, these financials here. Therefore, we can actually cut that code and paste that in here, and then make sure that the required data, revenue, expenses, and tax rate, is received in here. So therefore we have to accept parameters, revenue, expenses, and tax rate, and since they will all be of the same value type, I'll simply separate them by commas with that and add the type once after that list. In this case, float 64. With that, we calculate all these values. Now we can return them. So as a first step, we should let go know about the fact that we'll return multiple float values here, and therefore I'll add a pair of parentheses after this parameter list here and add 3 times float 64 in there. Now, as you learned, we could also give the return values names here, but here in this exercise I won't do it. If you did it, that's of course absolutely fine. Here I'll just specify the types, and then we can return EBT, profit, and ratio like this. The order is up to you, but you should of course keep that order in mind when you then call this function and you use the returned values. Which I'll do now, here in the main function. I'll call calculate financials, pass my revenue, expenses, and tax rate to this function, and as a result, we'll get back the EBT, profit, and that ratio. And since these are all new variables here, because of scoping, we're not using these ones, but we're creating new ones here in the main function, we have to declare them, and here I'll therefore use this declaration and assignment shortcut. And that's it. That should give us a Go program that can be executed that now uses some custom functions. So therefore here, if we now run this application, this program here, we can enter some revenue, our expenses here, and a tax rate, and we'll get back our result here. Now, as a little bonus, we can also work on the formatting of that number here, even though that was not a task of this exercise. You can of course still do it now and pause the video. Here, I will make sure that the output is properly formatted by not using println, but instead printf, about which you also learned. And then here, I'll output the value for the EBT. Though, since it's a float, we could actually also output this in a formatted way, and for example, make sure that we have at most one decimal place that's being output. And I'll do the same here for the profit with %.1f, and then referring to the profit, and also the ratio. Here, however, I don't just want to output one decimal sign, but instead, let's say 3 or something like that. And with that little bonus added here, if we run this application again, we can enter our data here, and we get that output. Now the line breaks are missing, so we should add them by adding this special \n line break identifier. And with that, we can re-execute this, enter our data, and now we got this all nicely formatted according to our rules here. Now this has already been a pretty long and comprehensive section because we covered a lot of crucial Go concepts. Now to come to an end for this section, there is one last important concept that also belongs to the Go essentials, you could say. And that would be the concept of working with control structures, which are things you can use in your code that allow you to control which code executes under which circumstances. Now, to learn about this control structures feature here, I'm in a brand new project, an empty folder, and as a first step, I'll therefore run go mod init and give this a path like example.com bank, because we'll build a dummy, simple banking application that will allow us to explore this control structures feature. So with that executed, we can then add a file here, and I'll name it bank.go. Now in here, we'll start by adding this to the main package and by adding this main function, which we always need, as you learned. And now my idea here is to build an application that asks the user in the command line which operation they want to perform. Check their balance, deposit money, or withdraw money. And then once the user chooses an action, we might ask for further input and then perform that action. And this then runs in an infinite loop, basically, so that the user can continue interacting with this application until they're done and they choose exit. We'll also make sure to check for invalid inputs. For example, if they try to withdraw a negative amount, or if they try to withdraw more money than they have on their account. So that's the dummy application we'll build here. And therefore, as a first step, we can get started here by using some of the things we already learned about. Like, for example, importing the FMT package so that we can show some text on the screen. Because of course we want to welcome the user and ask them what they want to do. So we can, in the main function, use FMT to print a new line where we, for example, say, "Welcome to GoBank." Something like this. And then thereafter, we can print another new line where we say, "What do you want to do?" And then thereafter, I want to show them their options. So we'll print more new lines here. And for example, give them their first option, which is to check the balance. Then I'll give them a second option, which is to deposit money. A third option, which is to withdraw money. And a fourth and last option, which is to exit this application. So that's the text that should be shown on the screen when the application starts. Therefore, of course, if we save this and we run this application, we get that output. Thereafter, the application exits though at the moment. This code does not run in an infinite loop. We don't continue showing this to the user. And we'll make sure that this is the case later. At the moment, it of course exits because we're done after going through all these lines of code here. But we'll now change this. And we'll start by getting the user input and then taking a look at that input to perform different actions depending on which choice the user made. So to get that user input, we can add a new variable, which could be called choice, and which could be of type int, because it should be 1, 2, 3, or 4, no float or anything like that. And we can then use FMT scan, as you learned, and pass a pointer to choice to that, so that choice is populated with the number the user entered. And then for the moment, just to see that this works, we can of course output a new line where we say your choice, and then thereafter we output choice. With that, we can run the code, of course. Now it waits for us to enter something. So here, for example, I can type 1 and hit enter, and I see your choice 1. Now, of course, though, it would be nice if we had some info text when it waits for our input that tells us what we have to do. And therefore, here, before getting that user input, I'll actually use print, not println, so that we stay on the same line. And I'll say your choice, colon, so that we show this text to the user when we're asking for their input. So that's the basic code. Now we, of course, have to do different things based on the input entered by the user. So we're already at a point here in this simple demo application where we need a control structure, a feature built into Go that allows us to run different code based on different circumstances. In this case, based on the choice made by the user. We want to add some code here where we, for example, output the current balance if the choice was 1, or where we ask for further input and then increase the balance if the choice was 2, and so on. And we can therefore add an if statement here with the special built-in if keyword. And the idea behind this if statement is that you now add a condition after this if keyword, and you then define the code that should be executed if that condition is met. For example, here we can check if choice is equal to 1. And what's important here is that you use this operator here, the two equal signs, because one equal sign is used to assign a value to a variable like this. When having a condition and you want to check for equality, you need two equal signs. You need this operator. Now, if you had a second condition that should be met, you could add two ampersands here and then add your second condition. Though, of course, here, for example, I would have two contradicting conditions, which could never be met both at the same time. But you can also check for two alternative conditions by using two pipe symbols here. This means that either choice should be 1 or it should be 2. But in this case, it's pretty simple. We just need one condition here. And therefore then, as a next step, we add the body of the if statement by adding curly braces, opening and closing, just as we did it with a function, but now with an if statement. And now the code inside of this body, so between those curly braces, will only be executed if this condition here is met, if it produces true as a value. Because the result of such a condition will actually be a value of type Boolean. And you could therefore actually also outsource this into a separate variable if you wanted. For example, once check balance could be a name, and the value would then be the result of this calculation, of this operation, this expression here, where we have this check. If you now hover over once check balance, you see that the type is bool, which stands for Boolean, which is one of the built-in types Go offers, which is a very simple type that's just either true or false. So where strings can be any kind of text, int can be any kind of integer number, bool can only be true or false. And you could now simply use that here as your condition, so that if this is true, if it contains true as a value, which is only the case if this condition is met, otherwise the value is false, but if it's true, this code will be executed. Now, typically for short conditions like this, you would add them in line with the if statement, and you would not use a separate variable, but I still wanted to add this here so that you do know that you can store the result of such checks in variables and that you will get a value of type Boolean. But with that, we have this if check, and we can therefore now tell the user what their current account balance is. So let's tell users what their account balance is. For this dummy application, I'll add a new variable here at the top of the main function, let's say, which we can name account balance. And let's say initially that's 1000, because it's a dummy application. It's a demo application to learn about control structures, so let's say this is our account balance. Now this is now inferred to be of type int, because this is an integer number, and that might not actually be what we want. Because I do also want to allow users to withdraw or deposit amounts like 5.5. Therefore, we should either override this inferred type by adding the type we want, float64, after account balance, or by adding .0 here, so that the inferred value is float64. And that's the approach I'll go for. Now with that, we can then go back here to this if check, and if the choice was 1. So if we want to check our balance, I want to output our current balance. So we can print this here in a new line and say your balance is, and then output account balance. With that, if we now save that, we can run this application and now choose 1, for example, because that's the only option we support at the moment, and I therefore get this output. So that works. And if I now choose another option, let's say 2, we don't get that. And that's how if statements work. But that's not all we can do with them. Of course, in this application here, we don't just have one option. Instead, we have 4. So one if statement alone is not enough. Instead, the choice could also be 2. What you can therefore do is add a second if statement and check if the choice is 2. But alternatively, since you could also argue that it's kind of related to this check, you could also add it to this first if statement by adding else if here. The result in this case here will be the same, but it's not always the same, depending on your conditions. If you have 2 separate if statements, this here will always be evaluated after this has been evaluated and executed. If you merge it into one if statement with an else if block here, this condition, and therefore this entire branch of the if statement, will only be evaluated if this condition here was not met. Which means that if the choice was 1, this second block will not be evaluated when using else if, but would be evaluated when specifying it as an extra if statement. Now here, since we know that we don't need to evaluate this if the choice was 1, because it then won't be 2, we can of course merge this into one else if statement. And now here we can run the code we want to run if the choice is 2. Which, since the choice is to deposit money, means that we need to get the information how much money should be deposited, and that we then need to update the account balance. Therefore here in this else if block, we might want to output some question for the user. How much do you want to deposit? Or maybe a bit shorter, simply your deposit, colon. And then again, we need to get that input. And for that, we can create a new variable here, deposit amount, which should be a float 64 value, and then use fmt scan to pass a pointer at deposit amount to that to populate that variable with the value entered by the user. By the way, this variable now would be scoped to this if branch. It would not be available anywhere else in this Go code, but that's fine because I only need it in there. After the user did enter a value here, we can then update the account balance. So we can set account balance equal to account balance plus deposit amount. Though if you have scenarios like this, where you want to update an existing value by adding a new value to that existing value, Go actually also gives you a shortcut you can use. You can use the plus equal operator here, which will do the same thing. So it's the same as setting account balance equal to account balance plus deposit amount. That would be the longer version. This here is the shorter version. You also have a minus equal operator if you would want to deduct the amount, but here it's plus equal. With that, we updated the account balance, and we therefore might want to output the new balance thereafter. So that we output print ln here and say balance updated, new amount, and then we output this account balance here. And with that, of course, if you save this and you run this application, if we choose 2, we're asked for the deposit amount, let's say 120.5, and if we hit enter, we therefore get this new amount output here. We can also remove this white space here, since println will add one automatically. Now, as a little exercise, you can try to implement the code for the third option on your own before we then, in the next lecture, implement the code for the fourth option. Here's a short pause for you to pause the video and try this on your own. Thereafter, after this pause, we'll implement the code together. So, Did you succeed? Let's add the code for the third option together. Now this option is to withdraw money, so therefore as a first step, we can add another else if branch here and check if choice is equal to 3. And then here it's pretty similar to what we did when we deposited money, so I'll copy that code. But of course now we're not looking for a deposit, but instead for the withdrawal amount. And I'll name it withdrawal amount here. And then populate that value and deduct that value with that minus equal operator I already mentioned in the last lecture. And then we still output the updated balance. And that should actually be all. That's how we check for that choice and update the account balance. So let's quickly check if that works. If I choose the third option and I withdraw 200, I got 800. The old balance, which we updated in the last lecture, was not stored because the program ended in between. We exited the program, and therefore all the old state and all the old stored data was lost. We would have to store it in a file or in a database to save it between executions, and that is something we will explore later, but here it's lost. But for this demo app, that's also no problem. Now, in the next lecture, let's work on that last option here. So let's make sure users can also choose 4. Now, at the moment, if our only goal is to end the program, we could actually not add any code at all, and therefore if they choose 4, indeed the program does end. And actually, it does end for any value they enter. If they enter something invalid, that's treated as 0, as you can tell. It's converted to 0 because it can't be converted to any other number, and therefore the program ends. But we want to end a bit more elegantly here, let's say. And therefore we of course might want to check the case that the choice was 4. However, since that's our only remaining choice here, we can actually also get rid of that condition and that if keyword here and just define an else block. Because every if condition can have exactly one else block. You can have as many else ifs as you need, but only one else block, which, as you might guess, will execute if no other condition of any if or else if statement is met. And therefore here, indeed, we could then output goodbye or something like this. And now also get rid of that dummy code at the end here. And that's how you can add such an else branch. And therefore with that added, you'll see that if you save everything and you run that program, if you choose 4, we see goodbye here. And we, for example, don't see that if we run that and check the balance. There, the program then also ends thereafter, because at the moment we have no logic for keeping it running, but it ends without the goodbye message, because that's only shown if the choice is anything but 1, 2, or 3. So now at this point, we learned about using if. Let's now use this knowledge to add more if statements. Because here in this application, when the user chooses deposit or withdrawal, we might want to validate the value that has been entered by the user. We, for example, might want to make sure that no negative amount is deposited or withdrawn. And for that, we can go to the place where we have that deposit code. And then after getting that user input, before updating the account balance, we could insert another nested if statement here. Nested because it's inside of another else if statement. And here we could check if the deposit amount is maybe smaller or equal than 0. So that's another operator you can use in such conditions. You already saw the equality operator. You also have the inequality operator, which we didn't use yet, but which would be this operator. And you also have the smaller than, greater than, and smaller than or greater than or equal operators. And here I want to check if the chosen amount is smaller than or equal to 0. which means that it's an invalid amount. And in that case here, we might want to output an error message with println, where we say invalid amount must be greater than 0. Something like this. I now also want to make sure that this code thereafter doesn't execute though. So at the moment, where we always end the application after performing the chosen task, we can simply return here. Now I'm not returning a value here, instead I just have an empty return keyword here without any value thereafter. And the main function indeed does not return any values. We have not defined any return types here. But you can always add a naked return keyword like this, because that will then simply make sure that no other code thereafter gets executed. Because that's the special thing about return. It stops the execution of the function where it's used, and no other code thereafter is executed. So this code here won't execute because we return here. And we only do that if the deposit amount is invalid. Therefore here, with this extra if check added, we can run this application again, choose deposit money, and now let's say we want to deposit -10, which does make a lot of sense. If we enter this, we get our error message here, and the program ends, as intended. So just as we're checking for an invalid amount here when the user wants to deposit something, we can also do that here if the user wants to withdraw an amount. So again, after getting the user input, before updating the balance, we can add this check and check the withdrawal amount, like this. But in case of withdrawing, we also might want to perform a second check in addition to this check. So not with else if, so not as an alternative to this check, but in addition. And here we could now check if the withdrawal amount is maybe greater than the account balance, which would mean that we're trying to withdraw more than we have in our account. And that, of course, shouldn't be allowed. In that case, we could then output println invalid amount, you can't withdraw more than you have. And I also want to return thereafter, so that again, no other code executes if we make it into this if statement. And therefore with this added here, with these two if statements added here, we can again run this code, choose withdraw money, and if I choose a negative amount, I get this error message regarding my invalid amount. If I instead choose an amount that's higher than my account balance, like 2000, I get that other error message. But of course, if I do enter a valid amount like 200, it works and the balance is updated, as you can see here. So that all works as intended. Now at this point, this application doesn't look too bad. I mean, it is quite some code, but it works the way it should. But of course, there's one thing that doesn't really work the way it should. At the moment, this application always ends after we chose one action, and that's not how it should work. Instead, it should keep on going. And we can achieve this by using another control structure offered by Go. We can add a loop to our code, so that some code is executed over and over again until a certain condition is met or something like this. And we can achieve this by using the for keyword. This creates a loop. And unlike in other programming languages, this is also the only kind of loop you can create in Go. In other languages, you might have a while loop or something like this. Here you just have for. But for in Go is pretty flexible, as you'll also see throughout this course. You can, for example, use for to then define a helper variable that will only be used for that loop, typically named I, which starts at some value, typically an integer with a starting value of 0. Then you add a semicolon, not a comma, but a semicolon, and a condition. a condition that, as long as it's met, keeps that loop running. For example, that I should be smaller than 2, let's say. And then you add another semicolon, and then some code that should be executed after every loop iteration. For example, that I should be incremented, which you can do with that shortcut. It's the same as saying I plus 1. This is just a shorter version. So this will add 1 to I after every loop iteration. And then, just as with a function or an if statement, you add curly braces to define the for loop body. So now the code inside of these curly braces will be executed twice in this case. So as long as I is smaller than 2, which is the case for exactly 2 iterations, since we start at 0 and then add 1 to it after every iteration. And we could now grab all that code here, so all the if-else blocks and this initial output, and move that here into this for loop. So that this is nested inside the for loop, and therefore our main function now basically consists of only that for loop that contains all this code. And therefore this code will now be executed twice, which is not the final result I want, but better than what we had before. Because now with that change made, we can run this application again, and we get that output we saw before, and we can, for example, check our balance. But now, unlike before, the application then does not stop, but instead we get this output again. And we can now choose to deposit money, for example, and deposit 100. And then it ends, because now we had 2 iterations. But as you see, that's how we can keep our application running, or how we can keep that code running. Now, of course, we want to keep it running for longer here. And therefore, of course, we could choose a very high value for I here in the condition. Now it would keep on running for 200 iterations. That might be enough for this dummy demo app here, but it's of course not what you would want if this would be a more realistic app. You don't want to limit the user to 200 executions. Instead, what you would want would be an infinite loop. And that's what we'll work on in the next lecture. Now, I did mention that in Go, you don't have different kinds of loops, instead you only have the for loop. But I did also mention that it would be quite flexible. And it is. Because you can define a condition like this if you know that you want to execute a loop a certain amount of times. But if you need an infinite loop, if you want to keep that application running forever, you can simply get rid of all that code and define the loop like this. Now all the code in there will keep on executing and executing and executing. And I'll show you how to get out of the application soon. For the moment, I'll just outsource this here and move that out of the loop because I don't always want to welcome the user again. I only want to do this once in this application, and it's just this code and all the if code that should keep on running. But with that, if we save this, if we run this application, indeed, we can now make our choices and the application keeps on running, even if we choose exit at the moment. So therefore, at the moment, if you do want to exit, you have to force close the application by pressing Ctrl+C in your command line. But that's of course not how we want to exit it. A better way of exiting it would be to go to that else block and return here. Because return will go back out of the function in which you are, so out of the main function, and since this is the main function that runs the program, this will also close the program here. So that's one way of exiting. With that, if we run this again, we can choose all these options, but if we choose 4, we can see goodbye here, and indeed, the program exited thereafter. Now that's one way, but maybe you don't want to return from the function. Let's say we also have another output here outside of that loop, just as we output the welcome message here outside of the loop, where we want to say, thanks for choosing our bank. Now, of course, we could put this into this else branch, but for demo purposes, I'll keep it outside there. Now, as you see, it's grayed out and I got a warning here. Because indeed, Go and my IDE understands that this code is unreachable. It will never be executed. Because we have an infinite loop in front of that code. And the only ways of getting out of that loop are to get out of the function. So this can never execute. And that might not be what we want. Therefore, instead of returning here, we can use another special keyword which can only be used if you're inside of a for loop. And that's the break keyword. This, you could say, breaks out of the loop. It makes sure that the loop is ended, and therefore then the next code outside of the loop would be executed. And therefore with break added here, if we again run this application, and we choose for, you see we get this thanks for choosing our bank message, and then the program exits again, because we got out of the loop. Now, just as we have break for getting out of a loop, we also have another keyword that can only be used inside of a loop. And that would be the continue keyword. Now, to understand it, let's go to these nested if checks here. Here, we currently return if the user enters an invalid amount. Now, that's a bit harsh, because that means that at the moment, if I choose an invalid amount, the application closes. It would of course be nicer if we would get another try. So if the application would continue running and we could simply make the same choices again. Therefore, instead of using return here, we could of course try break, but that would get us out of the loop and essentially achieve the same result as return, therefore. Instead, it's this continue keyword I mentioned, which simply tells Go to skip the rest of the current loop iteration and continue with the next. So this code here won't be executed if you call continue here, but it will restart with the first line inside of the loop thereafter. And that's exactly what I want here. So with continue added here, if we now run this and we try to deposit an invalid amount, we can make choices again. And we can, for example, choose to deposit a valid amount. And that's therefore another pretty important keyword, which, just like break, can sometimes be exactly what you need when working with loops. Now, when you find yourself building long if-else-if statements, as we're doing it here with multiple else-if and a final else branch, there is an alternative structure, an alternative feature you could use in Go. Because instead of writing such a if-else-if statement, you could use the built-in switch statement. And the main idea behind such a switch statement is still that you can execute different pieces of code for different conditions. And it works like this. You type switch, and then after this switch keyword, you add the value which you want to evaluate. In my case here, the choice, because that's the value I'm comparing to a couple of other values. So you would write switch choice, and then you have opening and closing curly braces. This is then the switch statement body. In that body, you then define multiple cases with the case keyword. And here you now define the different values for which you want to check. For example, case 1. Then you add a colon, and then in a new line, the code that should be executed for that case. And you can also have multiple lines of code for a single case. For example here, for case 1, so that choice is equal to 1, I would execute this code here. And we can move on to the next case. In this case, that choice is equal to 2. And then it would be all this code here that should be executed. So I can copy that here into my case 2 block. And so on. The next step therefore is to specify case 3, so that choice is equal to 3, and it would then be this code here that should be executed if that's the case. So it's this code, which I'll paste below case 3. And then I'm always pressing the format document shortcut here in VS Code to make sure that the code is nicely formatted. And then of course we also have case 4, but In the if-else-if statement, we actually did not have else if choice equals 4, but just a else statement to basically cover all other values. So if the user entered something invalid or any number other than 1, 2, or 3, we would end up in this else block. And I'd like to get the same result now here for my switch statement. And this can be achieved by not specifying another case here, but instead by adding the default keyword. So by specifying the default case, which will become active if no other case becomes active. And then again, we can copy this code from the else branch and then paste that here into the default case. And with that, we can get rid of that if-else-if statement here and instead use that switch statement. I also now want to replace return here with continue, by the way. I didn't do that earlier, but of course here I also don't want to return, but instead continue if we are in one of these if blocks. Now, one important thing to note, which is the reason for why I'm getting a warning again down here, is that if you are using such a switch statement, the break keyword has a special meaning. It now no longer breaks out of the closest surrounding loop, but instead out of the switch statement, which actually isn't a feature you normally need, because the switch case statement in Go works such that only one case can become active anyways. In other languages, you need to add break at the end of each case to make sure that no other case gets triggered, and that's not needed when working with Go, but still the break keyword has this different meaning when used inside of a switch block. Therefore here, when using this switch statement, we actually can't use break to get out of the loop anymore. Instead, we have to use return to end the entire application, which is also fine though, here in this default case, and therefore move this line of code into the default case. So if you have some code, if you have an application where you must be able to break out of some loop, this switch case statement is the wrong solution, and you instead should stick to the if-else-if statement you saw before. Otherwise, you can use this switch statement as an alternative to such a if-else-if statement. Now, to finally conclude this section here, there's just one last main feature and one last language concept I want to introduce and I want to add to this dummy banking app. And the feature I'd like to add to this app here is that we don't store this account balance just as a number in a variable and therefore in memory as long as the application runs and we lose it thereafter, but that we instead store it in a file so that we can reuse it every time the application starts, and we can therefore persist the account balance across multiple application executions. And thankfully, that's not too difficult to do in Go. And therefore, to implement this feature, I'll start by adding a new function that should handle writing to a file, because I want to add that logic in a new function so that we don't have to add it somewhere in this already existing pretty long code. So I will add a new function here, which we could name write balance to file. Name, of course, is up to you, but should describe what the function does. This function then should accept an input, a parameter, which could be named balance and should be float 64. Because of course I want to get the value, the balance value that should be written to a file as an input here. So to write data to a file, we can import another package from the Go standard library, and that is the OS package. And this OS package now offers a bunch of functions that allow us, for example, to interact with the file system. For example, OS has a write file function. which, as you can see, wants the name of the file to which data should be written. And it creates that file if necessary, so if the file does not exist yet. And then it wants the data that should be written to that file. And that's a strange type. We'll get back to what exactly that type is later in the course with those strange square brackets. But in the end, that's a collection of bytes, you could say. So it wants such a collection of bytes and then a description of the permissions that should be added to that file. So let's start with the file name, which should be a string. Of course, that name is up to you. Here, I'll name it balance.txt. So that's the file that should be created and where the data should be stored. Next, we need this collection of bytes. Now, one way of creating that is to use the format package and then the sprint function to generate a new string and pass the balance, this float, to it. This gives us a string then. And we could store that in a variable called balance text or something like this. And a string can then easily be converted to such a byte collection by using square brackets and then after them the word byte, and then opening and closing parentheses, which might look a bit weird, but that's the code you need here. And then you pass your text that should be converted to such a byte collection, so to say, between those parentheses to this byte thing here. That will then turn this string into a byte collection, and therefore, since that string contains the float, it's that float that will have been turned into such a collection. Now, last but not least, we must assign the permissions that should be added to this file, and here you can add 0644 as a value, which might look super weird, but that's basically a file permissions notation you will encounter from time to time in programming and when working with operating systems, especially Linux, because this is a way of encoding file permissions. And this set of permissions basically means that the owner of the file will be able to read and write the file, whereas other users that might access the file can only read it. And attached you find a link that allows you to learn more about this way of defining file permissions and how that works. It's not Go specific, but as mentioned, a general way of defining file permissions. But with that, we now got the code we need to store the balance in a file. And to see whether that works, we can now use this function and call it whenever we change the balance. So for example, here, when we deposit something, we can go down here where we updated the account balance and then call write balance to file and pass that updated account balance as a value to this function. And we can and should do the same thing here after withdrawing an amount. And with that, we can give this a try. If you run go run dot, you should be able to check the balance and you should be able to, for example, deposit money. If you do that, you hopefully get no error. And if you then exit this and you take a look at your file system, you should have a new balance.txt file in your project. And if you take a look at that file, you should find your balance number in there. And that's how you can store data in files. As a next step, let's make sure we can also read it. So now that we're able to write data to a file and store data in a file, as a next step, I want to make sure we can also extract data from a file and read it from there. And to do that, I'll add another new function, which I'll call getBalanceFromFile. And here I don't need any input because I'm not writing anything to a file. Instead, I just want to write the function like this. And we can now again use the OS package and now the read file function to read data from a file. And as you see, we'll need to pass in the name of the file that we want to read, which I guess makes sense. And we will get back 2 return values. Now I'll get back to this error thing, in one of the next lectures. For now, it's this byte collection, which again is interesting. You might remember it from before. So here I pass the file name balance.txt to read file. And since we're now using the same text here, the same file name, of course, in two different functions, I'll actually define it as a globally scoped constant. Account balance file could be the name, so that we can refer to this constant instead of repeating the text. I'm doing that even though this constant name which I chose is longer than this value, because now we have one global place where we can edit this value if we ever want to use a different file name. And we therefore don't have to edit this in multiple places in our code if we decide to use a different file name, which makes our code more maintainable and easier to edit. And here I'll bring back that parentheses, which I accidentally deleted. So read file it is that reads the data from that file, and it then returns these two values. Now here I'm only interested in the data, but I still have to create two variables if I'm getting back two values. So the second value is an error thing, and since we'll get back to this later, for the moment I'll just use an underscore here, which is a special kind of variable name you can use in situations like this when you want to tell Go that you know you're getting a value here, but you don't want to work with it right now. Because otherwise you'll get an error if you have a variable you're not using. With that underscore, Go is fine with you not using it. So with that we have the data, which is this byte collection, and now I of course want to return that data converted to a float. Now again, as often in development, there will be different options, but one simple option is to again use such a balance text helper variable and store data in there, but convert it to a string by wrapping it with the string conversion function. Now float 64 does not work with data. That's why we have to use string, because float 64 doesn't work with such a byte array. String does. And now that we got this balance text, which is of type string, we can convert this to a float. Now we still can't do that by using the float 64 conversion function. This also doesn't work with a string. But we can use another package that's part of the standard library that's called strconf, which stands for string conversion. This package offers some utility functions that help you work with strings. For example, it has a parse float function. And parse float now wants a string as a value. So here we then can pass balance text as a value to parse float. And parse float then actually also wants a second value, a second argument. But here you should simply specify 32 if you want a float 32 value, which is a number value that's less precise than float 64, in which case you would have to specify 64 as a second argument. So here I'll go for 64, which is basically the default float you work with in Go. You would only go for the less precise one if memory management in your application is really important and you want to make sure you're not occupying unnecessary memory, for example. So then this function will again return two values, the converted float and another error thing, which I'm also not interested in here. So I'll get my balance and then another error. And since I'm not interested in the error, we can again use this underscore. And therefore now finally, we can also return this balance. So this converted value. For that to work, we just have to let Go know about our intentions by defining float 64 as a return value type for this function. And with that, we can now call getBalanceFromFile. And the question is, where would we want to call it? And the answer is right when our application starts. Instead of setting the account balance to a hard-coded value like this, I now want to set it to the value I'm getting from my file. So I'll replace this 1000 value here with get balance from file. And that should be it. Of course, this will only work if you have such a file with such a value. If that file wouldn't exist, you would run into an error. And we'll take a look at that error in the next lectures. For the moment, let's make sure we have a file with such a number inside of it. And therefore, you can save the code like this, and then again run this program. And as you see, it starts here without an error, and I can also take a look at my balance. I can withdraw money and deposit money and exit. And if I do all that, we have the updated balance with the updated value. And that's how we can persist data by writing and reading to files. So now that we added this file feature and we're able to write to a file and read from a file, we should also take a look at error handling. Because I did mention that, for example, when it comes to reading from a file, you could get an error. For example, if that file doesn't exist. To show you what I mean, I will delete this file here, this balance.txt file. With that, reading from that file should fail when the app starts because the file doesn't exist. Therefore, if I run the application, it actually works. But if I check the balance, it of course has a value of 0 in there. So the great news is that indeed here the app doesn't crash, because read file, when it doesn't find a file, does indeed generate an error, as you'll see in a second, but it does not crash your application. Instead, in Go, error handling typically works a bit differently than it does in other languages. Because if you've worked with other languages, you might be used to certain actions or problems crashing your code. And in other languages, you can then often use try-catch statement to wrap code that could potentially fail, to catch errors and define code that should run if an error occurs. That is not how it works in Go, though. Instead, in Go, functions are written such, and your functions should be written such, that errors don't crash the application. Instead, read file, for example, will simply return an empty byte collection if it fails to find that file, which is then converted to an empty string, which is converted to the value 0 when parsing it as a float. That's why we see the value 0 here if we check the balance. But that's not all Go does. Instead, for operations that could fail, it is quite common that functions return such an error thing as a second value. And that's the value we can accept and store as a second value here when calling that function. So here I'll store it in a error variable. And what you then typically do in Go is you add a if check, where you check if error is not equal to nil. Now, nil is a special value in Go. It basically stands for the absence of a useful value, you could say. And error, this error thing here, will be nil if we have no error. So here, if we check if it's not nil, that means that we have an error, because error is not nil, which it would be if we had no error. And therefore, we can now use this if statement and its body to define the code that should run if something goes wrong with reading that file, because it maybe wasn't found. For example, here we could then return our default balance, which could be 1000, whatever you want. You can also define any other logic you need. It's totally up to you. But that's how you can handle errors. And we can do the same thing down here for parse float. Because parse float can also yield an error. If converting the string to a float fails, for example, because it contains some text that simply can't be converted to a number. For example, the text hello can't really be converted to a number. So therefore, here we can also accept this error and also check if error is not equal to nil. and define our backup logic here. For example, to again return 1000 as a value, or whatever you want. And with that, we made this code more robust. Now, what we could also do here, instead of just returning such a default value here, is return a default value and also our own custom error object. So that in the place where we call this function, we could handle this error. For example, to output some error message to the user and then still use that default value if we want to. And returning a custom error is quite straightforward and easy to do. First, I'll make Go aware of the fact that I'll return multiple values. And the pattern here is that your second, or in general your last value, will be that error object. And it will have a special type of error. So that's a special type built into Go. And you can then create such an error with help of the built-in errors package. So for that, you need to import the errors package, which is part of the standard library. And with that imported, you can create a new error by calling the new function that's part of that package. As you see, that produces an error value, and you can simply attach an error message to that error. For example, failed to read file, or failed to find balance file, something like this. And then here, for the second error handling if check, we can produce another new error where we say failed to parse stored balance value. So that we have different error messages for different problems. Now here in the success case, where we had no error, we also have to return a second value, and here we should return that special nil value. So comma nil, which means we have no error. Well, and now we can go to the place where we call getBalance from file, and since this now returns such an error value, we should accept a second variable here, error, for example, which we can now also use to check if it's not equal to nil, which, as you learned, means that we have an error. And then here we could, for example, output this extra error message. And output error in a new line, and then below that, the error value. And you can refer to the error value like this, and it will automatically output the attached message. And then below that, to set this apart, I'll output a couple of dashes. And that's how we can add our own error handling, how we can handle the built-in errors and then generate our own errors, and how we can handle those custom errors as well. So with that, if you make sure that you have no balance.txt file, if you run this application, you see I get this error here at the top. Now, of course, if I deposit some money, let's say 500, I'll actually write to the file again, and therefore it will be recreated. And it now contains 1500 because I added 500, and 1000 was that default balance value we returned. So that value still got used because in our error handling code here, we just make sure that we print this message, but we did not block the execution of the rest of this file. Now, when dealing with errors, you of course can have situations where you just can't continue executing the application when a certain problem arises. For example here, if you don't want to continue, if you don't want to use that default value, you could of course exit out of this application by simply returning in that if check here. So that if we have an error, we don't continue with the rest of the application. Therefore, if we delete balance.txt again, and I then run this application, you see I get this error output, and then the application exits. Another more drastic way of exiting out of this application because of an error is to call the built-in panic function. Now, this function indeed has a pretty good name, because indeed it's meant to be used in cases where you just can't continue. It will also end the application execution, but it will also output an error message in addition. For example, the message that's stored here, or some other message like can't continue, sorry. So with panic added here, we'll also stop execution if we make it into this if block. Therefore, again, if I run this, you see now it also exits and it looks more like a crash, which is the idea. We get our panic message here, and in addition, we get some details about which part of the code failed. For example, the line number, 41. At least that's where the error message was generated, where we panicked, so to say. And then we could try to trace back the problem from there. Now here, there is no reason to panic, but of course you should know about this feature as well, just as you should in general know about error handling. So, now that we also explored control structures, it's again time to practice what you learned. And for that, I'm back here in that Profit Calculator app, and I got some tasks for you. Now you find this snapshot of the app, which is basically the last snapshot from the last exercise, just with those extra goals here added. You find that attached to this lecture. And your first task here is to validate this user input we're getting with help of this get user input function. You should check that users are not providing negative or 0 numbers, so that we get only positive numbers. And I want you to actually generate an error and produce an error, you could say, and handle that error if one of these cases here is the case. So if we have a negative or 0 number, and you should then handle these errors here in the main function to show an error message and exit the application if an error occurs. And it's up to you how you want to exit the application. So that's the first task. The second task is to store the calculated results into a file. So we're calculating some results here and we're outputting them here, and somewhere here after they have been calculated, I want you to write these results to a file. So that's the goal. Definitely try it on your own first. In the next lecture, I'll show you my solution. So let's start with the first task, which is to validate the user input and generate and handle an error if we have a negative or 0 number. For that, of course, we should go to the get user input function, because that's where we're fetching that input. And here I actually have the same condition for all 3 inputs. So none of these values should be 0 or a negative value. Therefore, we can add our validation right here inside of get user input. And after getting that input, we can therefore add a if check and check if user input is smaller or equal than 0. And if that's the case, I wanna return an error. Or to be precise, I want to return some default value and an error. So therefore here I'll return 0 as a default value, though that won't really matter since we'll exit out of the application soon anyways. The more important part is the second returned value, which should be an error. And therefore we should let Go know about that. Here, when specifying the return values, it's now no longer just one value that should be returned by get user input, but instead 2. And the second value should be such an error value. Now, as you learn, such an error can be generated with help of another package that's part of the standard library, the errors package. And when you have multiple imports, you might want to organize them by wrapping parentheses around them and then storing one import per line. But it's this errors package that will help us. And with that package imported, we can use it to generate a new error and add an error message to that error. For example, value must be positive, or value must be a positive number. Something like this. Now, of course, since we're returning this error here as a second return value, we also must return one here. But of course, here in this situation, we have no error. That's why, as you learned, we should return nil here. This will then be the value that's used for the error if we have no error. And with that, we finished the work on the getUserInput function, and we can now go to the place where this function gets used. Here we now don't just get one value, but instead two values as return values. We get this error here as well. And we get that from all three inputs. Now with that, we can add our error handling code here and check if error is not equal to nil, which means that we have an error. And if that's the case here, I want to show an error message and exit. So here I can then use the format package to print a new line and output this error value. And as explained, that will then output that message that's connected to that error. Now, to make sure that we don't continue with the rest of the code, I'll then return here by adding a return statement. And as you learned, that will then make sure that the code thereafter does not execute if we have an error and we make it into this if block. And now we can repeat that for all the other getUserInput calls here. And basically just copy and paste this code. Now you could think that one if check here is enough, so that if I remove the other two, this one here is enough. Because it doesn't matter which getUserInput call gives us this error, the only thing that matters is that we have an error at some point and then we want to output it and return, right? Well, if you try that and you run the application, you'll see that if I enter an invalid value for revenue, but valid values for expenses and tax rate, the app does not stop and we don't get the error message. And that's the case because, of course, error here in this if check refers to the latest value that was assigned to it. And that's, of course, the error returned by this getUserInput call. So if we entered a valid tax rate, this is nil and we don't make it in here. So using one if check like this won't work. Now what we could do to avoid writing all this extra code here, which I'll still keep around for reference, but which I won't use here, is to give these errors different names, so that we have multiple different variables instead of reusing the same one all the time. Because whilst it is indeed the default to use a variable named error or error for storing that error, you can of course give it any name you want, like error1, error2, and error3. And then we could edit this condition here and check if error1 is not equal to nil, in which case we want to make it into this block. Or if error2 is not equal to nil, in which case we also want to make it into this block. And I only briefly mentioned this operator, but you can use this operator to combine multiple conditions as alternative conditions, so that you make it into this block if at least one of them is met. And we could also therefore add the third condition, that error3 is not equal to null. So now if we have any error, we'll make it in here, and then, since the error messages will always be the same, we can output any of them. So that would be one way of using just one if statement for handling all these errors. So with that, if I execute this and I have an invalid revenue but valid expenses and tax rate, I still get that error and the application exits. So that's one way of achieving this with one if statement. But of course, we can also instead use multiple if statements, which also often might make more sense because you might want to have different, more specific error messages for the different places where an error can occur. So you might, for example, want to refer to the specific input for which you didn't get a value. So these are simply different options you have here. In addition, besides returning, you can of course also use panic, as you learned, and output the error message like this and crash the program so that it doesn't just stop, but instead it also outputs an error trace, so extra information about where the error occurred and so on, and that would therefore be an alternative. But here I'll stick to return. And that's therefore one solution for this first task. The second task now was to store the calculated results in a file. And for that, I'll add a new function, though you don't have to do that, of course, but I will do it here, and I'll name it store results. And here I expect to get my EBT, my profit, and my ratio as results. And all three parameters should be float64 values. And then we can write to a file with help of another package I showed you earlier, the OS package. You can import it like this. It's part of Go's standard library, and you can then use it here and call os write file, which, as you learned, will create a new file if necessary. So now we can give this file a name, and here I'll name it results.txt. And then we need to convert these values to one single byte collection. That will be fairly trivial here though, because I want to group them together into one string as a first step anyways. So that we have our results here, a new variable, which contains the result of calling fmt sprintf. Now these print functions that start with a s will not print to the console, but instead generate a new string. And sprintf will generate a new string, which gives me some formatting options. Because here I want to output EBT, and then the EBT value, though, since this will be a float, I want to format it such that I only have one decimal place. Then I want to have a new line, which we can add with this line break identifier here. And also output profit, and then also format that in the same way as the EBT. Then add another new line and output the ratio, where I also want to format this, but now with 3 decimal places, let's say. And I then want to add one last new line at the end. And now we just have to pass in all these values that should replace these different placeholders in the order in which they should replace them. So EBT, profit, and ratio in this case. With that, I'll have such a results string, and as you learned, that can now be converted to such a byte collection fairly easily by using this special square brackets byte function here, which is basically the conversion function to create such a byte collection, and passing results to it. Now we just also need to specify the permissions, and here I'll use the same permissions as before in this course. And that should be all. That should now write these results in a formatted way to a file. So now we can call store results, for example here at the end of the main function, and pass EBT, profit, and ratio to that function. And if we now save everything, I have no other files besides gomod and the profit calculator and the gitignore file right now, but if I save this now, and we then run this application, and we enter some valid values here, like this, you see I get my output here, but more importantly, I got this results text file here. And in that file, we now find these results output and formatted in the way I specified in the code. And that's therefore how you can use if statements, errors, and how you can work with files. And that's it for this section here. And of course, this was a huge section. You learned a lot about some of the most important concepts Go has to offer. Because you learned about variables, constants, values, types of values and different types of values, how to convert values from one type to another, how to perform calculations with plus and minus and multiplication. You learned about if checks and conditions. You learned about loops and how you could create such an infinite loop. You learned about the switch block, and you learned how to create custom functions. That in there you can accept parameters, as many as you need, and you can return values. Again, as many as you need. And here towards the end of this section, you now also learned about working with files and how to handle errors. So a really solid foundation on which we'll now build up on. So now that we have a solid Go foundation, it's time to dive a bit deeper into the language. And for that, we'll start by taking a closer look at Go packages and how we can work with those packages. Now, of course, up to this point, we already did work with certain packages, like the FMT package, and we created our main package, for example. But in this section, we'll explore how we can split code across multiple files within a package, how we can then split files across multiple packages, so how we could organize our project into multiple packages, and how we can then import and use such custom packages. Now, to explore this package concept in greater detail, I'm back in this account balance app here we built earlier. And attached you find my snapshot so that you can follow along even if you skipped the previous section. So here in this demo application, we already got quite a bit of code in that file. And in such cases, it's not uncommon that we might want to split that code across multiple files to keep every file on its own a bit more readable and understandable, so that we don't have too much code in a single file, since that can make working with that file unnecessarily complex, because we have to search for the code we want to work on and so on. And thankfully, splitting code into files in Go is pretty straightforward. For example, here in this app, we could start by putting this code here, where we greet the user and show them their options, by putting that into a separate function, and then as a next step into a separate file. But let's start with a function. So we can cut this and then add a new function, for example here, which we could call present options. That sounds like a fitting name. And in there, I then wanna output all these lines. Now we can of course call that function here at the beginning of this for loop. Call present options like this. Now we could also try to outsource more code, but since this section should be about packages, I'll keep it to this one function for now. So this is now in a function, but it's of course still in the same file. But what you can now do is cut that function from this one single file, this one single Go file I have right now, and add another file, which could be called communication.go. So another Go file. And now here we can paste that function into this file, but we'll have to add this file to a package, because every Go file must be part of a package. That's how the different files are then linked together behind the scenes by the Go compiler. So we also must add such a package instruction here. And the really nice thing we can do here is that we can now add this file to the same main package we used in the other file. So we can set this to package main here. Now with that, this function will be part of the main package, and you will be able to call it in any other file that also belongs to the main package without any problems. So in Bank Go, we can still call present options here without any issues, without adding an import or anything like that, because present options belongs to the same package. We now just got some errors here in the communication.go file because this FMT package is not available here in this file. We are importing it here in the bank.go file, but where functions are shared, just like global variables, for example, across multiple files that belong to the same package, imports are not. So if you use another package in this file here, you have to add a new import to it like this, but that's all. And with that, we now split this code across two files, and we can therefore now run this application again, just as before. And in this case, I got an error because I don't have an initial balance file, but we can still continue, deposit some money, check the balance, and then exit. And that all works just as before, even though we split the code across multiple files, because both files belong to the same main package. So splitting code across files and using that code across files is pretty easy, as you saw. Sometimes though, especially in bigger, more complex projects, you might want to split your code not just into multiple files that belong to the same main package, but actually into multiple packages. And that can be especially useful if you, for example, put utility code into a package that could then be used in different projects. For example, code for interacting with the file system. It can also be a useful pattern if you have code that works pretty much standalone, but should also be used in the context of a bigger project. You could put such code into a separate package to have a clearer separation of that code and still use it in one and the same project if you want to. And we'll do that here in that demo application for this get balance from file and write balance to file function. Because these functions in the end do something that could be reused in different parts of the app if it would be a bigger app. Because in the end, these functions simply write a float to a file or read a float from a file. That's all. So we could make them slightly more generic and outsource them and put them into their own package. Now I'll start by making them a bit more generic as a first step. And for that, I'll rename this function here to getFloatFromFile, because it should no longer be focused on just getting a balance, but indeed any float value. Now the function therefore should actually receive the file name that should contain the float, which should be of type string, as an input, so that we don't always have to refer to the account balance file in there, but we can instead use this with any file name. Therefore it is also file name, which I want to use here in read file to read the content of that file. Then I still want to handle my errors here, though the error message should also be more generic and maybe just say failed to find file. The default value that should be returned could be accepted as an additional argument here if we want to make this more generic. So we could return the default value then. But here I'll actually stick to 1000 to keep things simple. This code here should stay the way it is, because we definitely still want to convert that file content to a float value. And here we need a more generic error message again, like failed to parse stored value. And I don't return a balance here necessarily, but instead let's say a value. Therefore here we use value, and that's not balance text but value text, for example, to make this all a bit more generic. And now we can use getFloatFromFile instead of calling getBalanceFromFile, and call this with accountBalanceFile as an argument, which is a constant that contains this file name from which we want to read. And that's already all. The function then still does its job. It now could be used in different parts of the app as well, and it can be used to read any float from any file, not limited to dummy account balances. We can therefore now also update the write to file function and name it write float to file. Here I'll name the parameter value, because again the function should now be usable with any value, not just a value that's used as an account balance. And I'll pass that value to the sprint function here, and we therefore here get a value text then and use that value text here. And I also want to get the file name to which we should write, because again, this should not be hard-coded anymore. Instead here, I want to get the file name, which should be of type string, so that we can use the file name here. And with that, we just have to go to the places where we called write balance to file, and instead call write float to file, and also specify the file name here, which is account balance file in this case. And now we can copy this and use the same code down here. And with that, we got more generic functions, which is the first step. The next step now is to put them into a separate file that's part of a separate package. So let's now move these generic file operation functions here into a separate package. For that, I'll start by adding a new Go file, and we could name it file.go or fileops.go for file operations. Now we can go to bank.go and grab these two, cut them, and move them into this new file. Now this file then also must be part of a package, and we could of course add it to the main package. With that, we could still use get float from file and write float from file in the bank.go file as before. The only thing we'll have to do is add a couple of imports in the fileops.go file, because we need all these packages in here in order to write these files and read the content from a file. That then also means that we can remove these packages from the bank.go file, at least most of them, because we're not using them there anymore. That would work, but the goal of course was to add this to a new package, not to the main package. And therefore we could simply pick a different name here, fileops, for example. But if I try to do that, it breaks. I get an error here. And you can see that the error I get is that I have multiple packages, main and fileops, in the same folder basically. And that's indeed not allowed in Go. Instead, every package must go into its own subfolder in the project. So if I want to have a separate new package here, I also have to add a new folder. And that folder should have the same name as the package. So fileops in this case. This file, by the way, does not need the same name. It could have any name you want. Just as I'm not using main.go here, but some other names with the main package. So therefore here I'll move this fileops.go file into the fileops folder. And with that, the error went away here. So now we can add this to a new standalone package. We'll now just have a problem here in bank.go, because now this function here is not available anymore, because it's now no longer part of the main package. So what can we do to make it available here again? To get access to the functions we define in our own packages, or to the things we define there in general, for example, also global constants or variables, to get access to these things, we'll have to import our own package, just as we already imported packages from the standard library. Now, to import your own package, it's not enough to just add the package name like this. Instead, you have to add the full path, which includes your module path. So in my case, example.com/bank. In your case, whatever you chose as a module path. This is what you should reference here, and then you add another slash, and then point at the package you want to add. And normally the IDE should help you here, just as it shows this suggestion for me here. So that's how you then import this package. And now you can use it just as you use other packages. For example, we're using the FMT package by using FMT and then dot and then something from that package. So here we would use fileops dot and then something from that package. Like this getFloatFromFile function, just that this unfortunately doesn't work. I'm getting an error here, that this is undefined as it seems. So what's the problem here? So here we're getting an error that getFloatFromFile can't be found on our own fileops package, even though I'm importing it here. But it's not found because in Go, only functions or variables or constants that start with an uppercase character, so with an uppercase G, for example, only such functions or variables and so on are available in other packages. That's also why we always used format.print with an uppercase P or scan with an uppercase S, because that's the Go way of exporting something. And you can only import and use something from another package into some package if it's exported there. And it is exported in another package if it starts with an uppercase character. In other languages, like JavaScript, for example, you have a dedicated export keyword, which you can add in front of the thing that should be exported and should be made available in other files. In Go, that's not the case. Instead, there, it's really the casing of the name that defines whether something is available somewhere else or not. And therefore here we should rename this to getFloatFromFile with an uppercase G, and also writeFloatToFile with an uppercase W. And with that done, we can finally go back to bank.go and use fileops.getFloatFromFile with that uppercase G. And of course do the same when writing to the file. Here we have to use fileops dot, and now I'm also getting some suggestions here, and we can use writeFloatToFile, like this. And do the same down here. And with that now, if you save that and you run this application, you see that it works again. And we can deposit something, check the balance, exit this, and this all works without problems. And this file also was updated because we now successfully did split our code across multiple files and packages, and we're exporting and then also importing our own custom package and its functions. So with that, we're pretty much done with this section. But up to this point, we only worked with packages that were either part of the standard library or that we built on our own. And that's not uncommon, especially because Go's standard library really comes with loads of useful features and functionalities built in. So it's definitely possible that the standard library is all you need. But sometimes you need a certain functionality in your application that's not part of the standard library and that you maybe also don't want to build on your own because it takes up too much time, it's too complex, whatever. And in such cases, you can install third-party libraries. Because Go indeed has a very active community and ecosystem, and just as you can build your own packages, there also are people building packages which they share with the world. For example, the Go random data package. You can simply search for Go random data to find it. Now, of course, often you might not know yet which kind of package you need, and therefore you can also use Go's package discovery page to search for packages. For example, let's say I need a package that generates some dummy random data for my Go application. Then I can search on that page, to which you find a link attached, for random data. And here I would indeed then again find that Go random data package I just showed you. Now if you then click on a package, you'll get more details about that package. For example, a link to its repository, its GitHub repository, where you can find the source code, because these packages are open source, so you can take a look at their code, which can, by the way, also be a great inspiration and a great source for learning more about Go. And then on this page, you typically also find the documentation of this package, explaining you how you can use this package. And this package here is a package for generating dummy data. So let's say we want to add some dummy data to this application here to, for example, output some dummy phone number that belongs to the bank. Well, in that case, we could use this package and then there look for a function exposed by that package that does generate a dummy phone number. Now for that though, we first need to install the package. And thankfully, we got some installation instructions here. And you'll find such instructions on basically every package page. And it's also always the same command. It's the go get command followed by the path to the package. And this now is a GitHub path that really leads to the page on GitHub where the source code of this package is stored. So you can simply copy that command, go back to your project, and in there, in your terminal, run go get and then this URL. This will then download this package and add it to your project. And you will not find the source files here, but you will see that the Go mod file was edited. And in there, you will find this extra line. Because this Go mod file does not just serve as a description of your module, for example, containing its path, but instead it's also used to list all the third-party dependencies of your project. So that if you would share your project with someone else, they could quickly get and download all those dependencies. Simply by running go get, by the way. This command, if used without any path, will take a look at your Go mod file and make sure that all the dependencies specified here are fetched and made available for this project. Well, and with that, you can now use this package in your project, just as you can use any other package there. You will just have to add an import path, and here you should again use this full package path. So the same path that also is stored and mentioned in your go.mod file. And with that, you're ready to use this package. For example, if we want to output some dummy phone number below this welcome to Go bank text, we can now easily do that with println and then random data, that's the actual package name under which this package is exposed. And you find out that this is the name if you take a look at the official documentation. And then it turns out that this package does indeed expose a phone number function, which you can call to get a dummy phone number. So we could then add some text in front of that, reach us 24/7, and then thereafter this dummy phone number will be output. And that's how we can use a function from a package that we did not create ourselves, but that's also not part of the standard library. So with that, we can save this, of course, and if we run this application, we can see that here we got that dummy phone number output. And that's therefore now it for this section. Here in this section, you did learn what the core idea behind packages is and how you can create your own packages. How you can organize your code across multiple files and how you can organize your files across multiple packages. You of course also learned how you can then import your own packages into other packages, into the main package for example. And along with that, you learned that the casing is important, because only functions, variables, and other things that start with an uppercase character will be exposed by a package and will be available in other packages. You also learned how you can get and use third-party packages, and therefore you're well prepared to build any application you want with any packages you need. It's time to dive into a very important Go feature, which you also find in some other, but definitely not all other programming languages. And that would be pointers. In this section, we'll explore what exactly pointers are, why this feature exists and which problems it may help solve, and of course, most importantly, how you can work with pointers in Go. So let's start with the most important question. What exactly are pointers? Well, pointers are in the end variables that store value addresses instead of values. And that might sound confusing, so let's take a look at how your code affects your computer's memory. And let's say you have some code where you create and initialize a variable called age, which you set to a value of 32. In that case, that value, 32, is stored in the computer's memory. And that value in memory automatically gets an address. Every space in your computer's memory has an address, and that address is required by the computer to be able to retrieve that value and work with it. But in this case here, this value 32, which in our code is stored in the variable age, is actually also stored in the computer's memory. And every value you use in Go is, at least for a short period of time, stored somewhere in your computer's memory. Now, a pointer then is a variable where you don't store a value, but where you instead use this special ampersand operator, a single ampersand symbol, to get and store the address of a value instead of the value itself. So now age pointer would contain the address as a value. And you might of course now wonder why you would use this feature, what the advantage of pointers is. And there are probably two main advantages of using pointers in Go, at least in certain situations. And the first potential advantage is that when working with pointers, you can avoid unnecessary value copies. And the second advantage I want to emphasize here is that you can use pointers to directly mutate values. But what exactly do I mean with these advantages here? Well, let's start with the first one, the left one, avoiding unnecessary value copies. By default, in Go programs, when you pass a variable to a function so that that function can work with that value, Go creates a copy of the value of that variable in memory and passes that copy to that function. So at least for a certain period of time, until the function execution is done and the copied value will eventually be cleaned up by Go's garbage collector, a process that runs in the background automatically and gets rid of unused values. Until that happens, you have the same value twice in memory. And for very large and complex values, that could be a problem in certain applications because since you have the same value twice, you're of course taking up twice as much space. Now, I'll be totally honest. For numbers and most strings and also most more complex values, about which you'll learn later in the course, that won't really matter too much in most applications. You'll need a very specific application or a use case where this optimization of using a pointer to avoid this copy might actually make a difference. But still, it is an advantage to be aware of, because that can be one reason for using pointers. Because when passing a pointer as an argument to a function, there's no copy being created. Instead, that function receives the address and can use that address to look up the value that's stored under the address, again by using a special syntax, which I'll also show you later, to then work with that value that is stored there. So that's one reason for using pointers. Another advantage of using pointers can be that you can write functions to which you pass a pointer, so an address instead of a value to that function. And that function can then, since it has the address to the original value, directly edit that value. So it doesn't have to calculate a new value based on the input value and then return that value so that that returned value can be used in the place where the function was called. Instead, it can directly manipulate the value if it received such a pointer. And that can of course lead to less code since it allows you to avoid the return statement and so on. But to be clear, it can also lead to less understandable code and unexpected behaviors, because it might come as a surprise that a function called add, for example, does not give you the sum of two numbers, but instead edits the first number by adding the second to it. That can be unexpected. You might instead expect a function that returns a result and leaves the original numbers unchanged. So it comes down to your specific use case, your personal preferences, and of course also the naming of your function, so that you don't surprise yourself or other developers with unexpected behaviors. But that's what pointers are and why you might want to use them. Now let's take a closer look at them in code. Now here I'm in a brand new Go project again, in a brand new Go module, and in there I'll add a new file, pointers.go. And in this file I simply want to introduce you to pointers. We'll build more useful demo applications with pointers and some other features later. Here we'll just get started with pointers. And for that I'll of course add this file to the main package and add this main function, which we always need. And here we can pick up that example from the slide and, for example, add a age variable. So that's now a regular variable, not a pointer, just a normal variable. And this value, 32, now would be stored somewhere in memory, but we don't see its address here and we don't need it. We can now work with that variable, for example, by importing the fmt package and outputting it, so that we say age, and then output the age variable. And we could add some function like get adult years, where we maybe want an age of type int as an input, and where we then return age minus 18, so that we get the number of our adult years. Of course, if we are returning a value here, we also have to add that return type here. And now we could also, of course, output the result of calling getAdultYears. We can do this all in one step here, or alternatively, of course, create a new helper variable, adultYears, which is set equal to the return value of getAdultYears, to which we pass the age, so that we can then output adult years. And this all, of course, is pretty standard Go code. If we run this application, we see our age and then the number of years since we turned 18. But now here we have code where we're passing a variable, the age variable, as an argument to various functions, to the println function and the getAdultYears function. And as mentioned, this will lead to a copy being created. So the age received here in getAdultYears will technically not be exactly the same number as we set up here. Instead, it will be a copy of that number. The same value, of course, still 32, but stored in a different place in memory, so that we have the number 32 stored in memory twice. And once this function is done, so after this line of code here, Go's garbage collector will eventually become active and delete that second 32 in memory. That's how this will work. Now let's take a look at how this changes if we're using pointers. So let's now create a pointer. I'll name it age pointer. Typically, you would not add pointer in the name though. I'm just doing this here so that it's very clear that we'll store a pointer in there. So an address of a value. Typically, you would pick a normal name like user age, for example. But here I'll go for age pointer, And now the value I want to store there is the address of age. And we get that by using the ampersand symbol and then the name of the variable that contains the value of which we want to get the address. In this case, age. This will then create such a pointer, and you can tell that age pointer is a pointer by that special type it has here. It's not just int, instead it's asterisk int. And this kind of type always tells you that you're dealing with a pointer. And of course, this does not just exist for ints, but for all value types. You can have string pointers, Boolean pointers, really everything. Therefore, you could of course also create this not in one step, but in two steps. And create an age pointer variable, which should be of type int pointer, by using asterisk int as a type here, which you assign. And then you initialize it here in this line. Now you don't have to do that, but you can, and with that it becomes very clear that we have this special pointer type here. So now this is the age pointer. And now to understand what this does and how it works, let's output age pointer here instead of age. So here in this line, I'm no longer outputting age, but age pointer. And I'll comment out these two lines so that at the moment, nothing else is being output. If we do that, and we save this code and we run this application, you'll see something like this. And that is that address of that integer value. So that address where that number was stored. Now, of course, that address is not too useful here if you want to output it, but it will later be useful if we, for example, pass it to a function. So that that function can take a look at that address and get the value from there. And then use that value without copying it, what I mentioned before on the slides. Now, if you're in a place where you need the actual value that's stored behind that address, you'll have to do something which is called dereferencing. You have to add an asterisk in front of the pointer. So you use the ampersand in front of a normal variable if you want to get a pointer, so if you want to get the address of that value stored in that variable. And you use the asterisk symbol if you want to do the opposite, if you want to get the value behind a pointer, so the value that's stored under a certain address. And that's what I'm doing here now. With that, if we save this, if I again run this application, you see 32 is being output here. And that's coming from this line of code, because we're dereferencing this pointer here. So now that we know how to create and generally use pointers, how we can dereference them, let's see how we can work with pointers in conjunction with functions. And for that here, in getAdultYears, we could say that we don't want to get an int value itself, but instead a pointer to an int value. Therefore, we should change the type of parameter we're expecting, because we don't want an int, but instead a pointer to an int, which means we have to add an asterisk here. Because that was the same type we used here for creating such a pointer. So with that, we get a pointer instead of an int, and therefore here I'm getting an error. That I can't perform this operation if one type is a pointer essentially, because in Go, unlike in some other programming languages, you can't perform pointer arithmetic. You can't perform calculations on pointers. In some languages you can, and you can run into really nasty problems there, but it can also be a powerful feature. In Go you can't. You can't deduct values from a pointer, so from an address or anything like that. Instead here, if you want to perform this operation we are performing here, we have to dereference the pointer. We have to add this asterisk. So with that, we're getting the address, then we're looking up the value that's stored under that address, and we're deducting 18 from that. And then, just as before, we return that new value. So therefore, we can still create adult years and call getAdultYears, but now here, we should not pass age as a value to get adult years, but instead a pointer to age, which we could again create by using this ampersand operator here, or, since we already have an age pointer, by using that and passing that to get adult years. With that, we want a pointer and we get a pointer. And we should therefore get new adult years, and we should be able to output them. So with that, we can run this again, and we get the same output as before, but now with pointers. And the difference, the important difference now is that now there's no copy of 32 being created. Instead, we create it once, and it gets stored in memory once. Then we create a pointer, so we get the address, but we don't copy the value or anything like that. And we then pass that pointer to that function where we want a pointer, and therefore again, nothing is copied. It's still the one single 32 value. And we use that same original value here in this calculation. Though I also want to be very clear, avoiding a copy of an integer value will not be worth it, because this number is a super small value in memory. So copying it and having all that extra work with creating the pointer and so on is not worth it. It's just an example to show you how this generally works. You should not start avoiding passing integers to functions and replace them with pointers. You should not do that. Now, on that slide I showed you before, avoiding unnecessary value copies was just one advantage. The other advantage was that we can also directly mutate values. And that's what I'll do next. Because here in our code, we're passing this age pointer to get adult years, and therefore in there, we could of course, instead of returning the result of deducting 18 from age, we could instead dereference that pointer to get access to the value and directly deduct 18 from that. Now that alone won't do much, we also have to store that result somewhere. So before we returned it, now instead, we could store it in our pointer. However, not like this, of course. Because keep in mind, age is the pointer, not the value. Here we are dereferencing it to get a new value. If we then want to write that value back into that place in memory where age was stored, we have to dereference it here as well. And with that, we're getting the value, we're deducting 18 from it, and we're then taking the result of this operation and we're putting that result back into this place in memory here. So where 32 was stored before, we're now overriding that 32 value with that new value, without returning or doing anything like that, just by using that pointer which we receive. Therefore, getAdultYears will no longer return anything, and we should therefore remove that return type annotation. Therefore here we no longer need to store that in adult years, because we no longer get a value, and here we should therefore instead output age, or the dereferenced age pointer. And here I'll output the original age variable, so that we see what that gives us. With that, if we save that and we run the app, you'll see something interesting. I first get age 32 and then I get 14 here. Now age 32 is coming from this line here, where we dereference the age pointer and get hold of the value stored under that address, so the 32. The second output here, however, this 14, is coming from this code here. And that's really interesting, because here I'm outputting age. Not my age pointer, not the dereferenced age pointer, but the original age variable. But keep in mind that getAdultYears did edit that place in memory. It overwrote the number stored under that address. And therefore, it overwrote this 32. And that variable just also used that place in memory. So if we change that place in memory, that variable holds that new value that's stored there under that address in memory. That's why we're outputting 14 with this line of code here, because we edited the original value. And that can be an advantage because we don't have to return something here now, but of course it can also be a problem because it might be unexpected that we overwrite the original value. We might not want that. Especially if we have a name like this, get adult years. That does not sound like it edits something. We instead might want to call this edit age to adult years to make it clearer what this function will do. And then call this function to be more descriptive. But that is how you can use a pointer to mutate a value without returning it or anything like that. So we can use pointers to directly edit a value from inside a function, and this is actually a feature we already used in this course without fully understanding it yet. You might recall this scan function, which we used from time to time to get user input. This scan function wants a pointer as an argument, which is why we have this ampersand symbol here. We are creating a pointer here which points at this choice integer, in this case here, in this example. And we pass this pointer to scan because scan then internally dereferences this pointer and overwrites the value that's stored under that address with the value entered by the user. So that's an example for pointers being used, in this case, to mutate a value from inside a function. And that's it for pointers. That's how you can create them, how you can use and dereference them, and how you can pass them around. And why you might want to pass them around, though as mentioned, you should really be careful with that. And you should not overdo it, because in many cases you might not need a pointer. Nonetheless, there are situations where you do need one, where you do want one, and therefore this is an important feature which we will also see and use throughout the rest of this course. Up to this point in the course, we already worked with a lot of basic values. Strings, integers, floats, booleans. But Go also has a couple of more advanced values we can work with. And in this section, we'll explore the first more advanced type of value, a super important type of value. We'll explore structs, or the struct value, which is a data type that allows us to structure data, to group related data together, you could say, into a collection of data. But we'll take a closer look at what exactly structs are and how we can create them, how we can work with that data type in this section. We'll see examples for when we might want to use structs, and we'll also explore how we can not just group data together with structs, but how we can also add methods, functions in the end to structs. Now for this section, I got a brand new starting project, which you find attached. And in that project, you don't just find a Go mod folder, but also a structs.go file, which already includes some code. I'm fetching some user input with help of a getUserData helper function, which takes care of outputting some text and then getting some input value and returning that value. And I'm then gathering a first name, a last name, a birth date. And then, of course, in reality, in a more realistic and bigger app, we would do more. Here, however, this is all I need to introduce you to structs, and therefore all I'm doing here is output that data down here. And that's therefore all this package does, but with that, it does enough to introduce you to structs. So in this demo application, we're collecting a bunch of user data, which we might need for the app we're building. And it's of course not uncommon that different apps need to collect different data, or in general work with different data where, and that's the important part, different parts of that data, different pieces of data might in the end be related. Like here, I'm collecting user data, and at the moment that data gets stored across 3 variables. Now, of course, that works and isn't necessarily a problem, but especially when applications become more complex, you might want to group related data together into one value instead of a couple of individual variables, so that working with that data becomes easier, and so that passing that data around becomes easier. Because let's say we also had another function here, output user details. And the goal here is to do something complex maybe, but here I'll just use this println statement to output the first name, last name, and birth date. If we had such a function that needs all the user data in order to work correctly, we have to pass all that user data to that function. So here we have to add a bunch of parameters that are required, which are of type string. And then we have to call that function, output user details, and pass those arguments to the function. And that's of course a lot of extra work. It's also error prone because we might mess up the order of arguments and parameters, and we accidentally might pass the last name in the place of the first name and pass the first name in the place of the last name. That might happen. And for all those reasons, we might prefer a value type that groups related together into one single value, which we can then use. And that's exactly what structs are. They are structures that allow you to group related together into one single value. So let's create such a struct value then. And that all starts with defining a new custom type. Thus far, we worked with built-in types, like strings and numbers and so on. But you can actually also define your own types in Go, at least to some extent. And you do that with the type keyword, typically outside of functions, since in most cases you might want to use a type in different functions. You could, however, also use it inside of a function if you wanted to. And then after that keyword, you add the name of your custom type. For example, user. Often those names start with uppercase characters, because often you might want to make those types available outside of this package as well. As you learned in Go, it's the casing of the first character of a name that defines whether this thing, in this case this type, is available outside of this file or not. But here, for this first demo, I'll use a lowercase character because this user type is only required inside of this file and this package. So that's the name of my custom type. The last but important piece here now is the type of custom type we want to create. And that's what we'll do here by adding the struct keyword after the name of our custom type. Then you add curly braces, and this now defines your own struct, your own user type, which is a struct type. But that's not all you do when creating a struct. Indeed, the idea behind a struct is that you can group data together into that struct. And therefore, when creating such a struct type, you then add the fields, as they're called, this struct should contain between those curly braces. So for example, here we could say that such a user structure should contain a first name. Therefore, we could add first name here as an identifier between those curly braces, and that would add a field first name to that structure. And you'll see how you can work with those fields soon. Now, every field also needs a type, just as a variable needs a type. And you add that type after the field name, string in this case. Then in a new line, not separated by a comma or semicolon, just in a new line, you can add a second field if you need one. And you can add as many fields to a struct as you want. For example here, the last name field, which is also of type string, and then also the birth date field, let's say, which is also of type string. And you could add more. You could add an age, which might be of type int, so you're not limited to string values, and you can even add nested struct types. To give you an example, I'll import another package from the standard library, the time package, which allows us to work with date and time values. And I'll not use it with the birth date here, even though we could also do something with that. Instead, I'll add another field here, created at could be the name, and set this to type time.time. And time is now actually also a struct type, but one provided by that time package. And it starts with an uppercase character so that we can use it outside of that package. Now you will of course soon see how you can create such a time struct value here, but first let's take a look at our struct here. Because this is the struct I want to use for this application. That's my own custom user type that should include these fields. And the idea behind this struct is now that we can create it, for example here in the main function, and put all the data that makes up a user into that struct so that we can work with one single user value, which is of that type here, and use that in our application and access that internally stored data, so the first name, the last name, and so on, whenever we need to access it. But instead of dealing with 3 variables, we'll just deal with 1. And that's what we'll do in the next lecture. So let's now use our custom struct here and create a value based on it. And you can do that by creating a new variable, which you could name app_user, for example. And the type of that variable should be user. So my own user struct type here. That's how we create a variable of our own custom struct type. And of course we can now assign a value to app_user. And the value should now be a new instance of that struct type. So here we define the blueprint, so to say. Now we have to create a value based on that blueprint. And that blueprint-based value is often called an instance of a struct. And you create such an instance by using your struct name, user in my case, and then by adding curly braces directly after it without a blank. You can add one, but you typically don't. And now you put your values that should go into this struct, so that should be assigned to these fields here, between those curly braces. So for example, if we want to store this first name variable under this first name field in the struct, we would add first name here, and we're getting auto-completion by the IDE, which understands which fields can be added to that struct. So here it's first name. Then you add a colon that separates the field name from the value for the field. And here you could also hard code a value, but in this case, I'll use this first name variable. And since this can be confusing to have first name here and here, even though it's not a problem, I'll actually rename this here to user first name, user last name, and user birth date. So that it's very clear which side is the value, this one here, and which side refers to the field in the struct. Then you add a comma, and then in the next line you can assign the next field to a value. So here last name should use user last name. And then the birth date field in the struct should be set to user birth date. Well, and now we can also set created at, and we can set this to a value created by a function from this time package, and that would be this now function. And then you have to add another comma here, even if that is the last field you're setting. Now this now function from the time package then returns a value of time, which is a struct, just a struct defined by that package. So instead of defining a struct like this, we can also create one by calling a function that produces a struct. And we'll later in this section also add our own custom function that produces a struct. For the moment, we'll just create it like this by instantiating based on this blueprint, this user struct blueprint, like this. Now, in the last lecture, we created our struct instance, so a value based on our type blueprint. And we did this with this struct literal notation, as it's also called. Now, when creating such instances, there are two important things you should know. First, if you are assigning all these key value pairs in the order in which they were defined in the blueprint, so first the first name, then the last name, and so on, just as we're doing it here, then you can actually also omit that key and just specify the values. So that works. But you have to make sure that the order is the same as in the blueprint, because otherwise a value will be assigned to the wrong key. For example, down here, if I swap last name and first name, I'm not getting an error here, but of course now user last name would end up in the first name field. So that's something to be aware of, but you can then use the shorter notation. Here I'll go back to that longer notation though, since that notation makes it very clear which value goes into which field. The other thing you should know is that you can also create an empty struct here, like this, by using the struct literal without any values between these curly braces. This is the null value of this struct type here, and it will create such a user type value, but of course it will essentially be an empty value. There will be no values for first name, last name, and so on, as you can imagine. Therefore here I'll go back to the version with values. You can also omit just some values if you don't have a value that should be stored, for example. In that case, all the other keys will be set, and that one omitted value, the birth date, for example, will be set to the null value of that type you chose for that value. So for birth date, it would be set to an empty string if you omit that down there. And that's therefore how you can create a struct with that struct literal notation. And now let's see how we can work with that struct value. So we are instantiating our struct blueprint, this blueprint. We are instantiating it. We're storing it in this variable, but we're not doing anything with that variable, of course. We just have some data in there, in that user struct, which is nice. But of course, a good next step would be to pass this to this function, for example, which needs all that data. And that's indeed one of the advantages of using a struct. Because here, in this output user details function, instead of accepting all these different parameters, we can now simply accept a user value, which should be of type user. And since this looks a bit weird, I'll use a different name here, maybe just u. So that's the parameter name. That's the value type. And the value type here is user, our own user struct type. So now this function wants such a struct, and if it now wants to output first name, last name, and so on, we can easily do that by using this struct, and then there we can use the dot notation. Just as we use this dot to access functions exposed by a package, we also use this dot on a struct to access the fields of that struct and the values stored in those fields, therefore. So if I want to output the first name here, I can do this by accessing u.firstname. If I want to output the last name, I can use u.lastname. And also u.birthdate, and so on. This is how we can accept one parameter and still access and output all that data. Now, of course, we also have to pass that value to output user details then. And we can do that by simply passing app user here. Because app user is a value of type struct, and that's exactly what output user details wants. And that's therefore how you can pass a struct value around and how you can access the fields in a struct. Therefore, we can now run this application again and enter some user details here. all those details that are required, and I still get the same result as before, but now with help of this struct, which allows us to make this function and especially its parameter list a bit leaner. So we are now passing a struct to this function. And this here would be an example for a use case where you could consider using a pointer instead of accepting the value. Because as you learned at the moment, since I am accepting the value here, this struct here will essentially be copied in memory when we call output user details, and the copy will be received in here. So for a brief moment, we'll have both the original struct here, which is one value in memory, and this received struct, which is a copy of that struct, but which occupies another place in memory. Now, to be honest, this is still a fairly trivial value, so using a pointer here is overkill and not really required. But for practice purposes, we can still change this function, and instead of wanting a value of type user, we can expect a value of type user pointer. So a pointer pointing at a user value in memory. Now, in order to get such a pointer, we then of course have to get the address of app user by adding this ampersand operator here, which, as you learned before in the course, gives us the address of this value in memory. And therefore, with this approach, we are now passing the pointer to this function. Hence, if we run this, we got the same result as before, as you'll see here, but now with pointers. But there's one thing that might look strange to you if you paid close attention in the pointers section. What could be strange in this code here, specifically in this line? Well, in the pointers section, you learned that if you got a pointer and you want to work with the value that's stored for that pointer and not with the address, that you have to dereference it by using *u, for example. That would then give you access to the value stored on that address. Just u, on the other hand, would be the address. So technically, we're trying to access first name, last name, and birth date on the address, not on the value stored at that address. However, this works because that's essentially a shortcut that's allowed by Go. The technically correct way would indeed be to dereference this, but in order to then use the dot on this, you would have to wrap it in parentheses, so that you try to access a field on the result of this dereferencing operation here, and you could then access first name like this. And that would be the technically correct way of accessing a field of a struct pointer. However, you pretty much always use this shorter approach, because it is allowed by Go, and it's shorter and nicer to read. Nonetheless, you should keep in mind that normally you need to dereference, but pointers to structs are simply an exception. So structs are pretty useful for combining data and for grouping related data together. But that's not all you can do with structs. Instead, you can also attach functions to structs. And a function that was attached to a struct then is called a method. For example, here, in this very simple demo app, we could attach this output user details function to a struct. To the user struct, to be precise, since it really only works with that type of data anyways. And since it is a function that only exists to output data for such a user struct. So attaching it to that struct makes sense. For that, we can grab it, though that's technically not required. You could also leave it here, but I'll move it up here right below the struct just so that we have both in the same picture, so to say. But you can store this function anywhere. You do not attach it to a struct by moving it below that struct. Instead, you do attach it to that struct. You do turn it into a method of that struct, as it's called, by adding a pair of parentheses in front of the name of the function, so after the func keyword, but in front of the function name. And here you now specify the type of data, the struct typically, to which that function should be attached. In this case, user, because that is the struct to which I do want to attach it. Now you can also specify a name here, for example, you again. You could also use user, but since user looks a bit weird, I'll use you. And now with that done, you can access the struct to which this function has been attached through that you name here. Which of course means that we can get rid of this parameter here. We don't need it anymore because this function now belongs to that struct and has access to that struct through that user here. And therefore this function here also continues to work because when we access you here, so if we access the user here inside of the function body, we're accessing it through this special reference here, you could say, which gives us access to that user struct because this function has been turned into a method of the user struct by adding this extra code here. And this extra piece of code here is called a receiver argument. So it's a special kind of argument, a special kind of parameter, you could say, which is not specified here in the regular parameter list, but which instead is specified here in front of the function name to, as mentioned, turn this function into a method of that received type here. And with that, we can go down to our code where we call output user details, and we now have to call this function in a different way. Instead of calling it like this as a standalone function, which it isn't anymore, you can't call it like this anymore if you attach it to a struct like this. So instead of doing that, you now use your struct, in my case here app user, and then you again use the dot notation, and here you now don't just find these fields that you added, but also any methods that have been added to this struct. In this case, this one output user details method. And we can now call it like this, and we don't have to pass any argument to this method, to this function anymore, because it doesn't want any. It wants no arguments. And this user struct value here, it will be passed to this function here automatically by Go because we turned this function into a method of this struct and we're calling it on this struct. And therefore, if we save this and we run this code, I can again enter all my details here like this. And as a result, I get the same output as before, but now with help of that method. Now, when adding methods to structs in Go, you're not limited to adding methods that output struct data. Instead, you can also add methods that change data in a struct. So for that here, we could add a new function, which we maybe call clear user name. And this function should be a method of that user struct here. Therefore, in order to attach it, we of course, just as before with output user details, add this receiver argument here, where we point at this user struct and give it a name that can then be used inside of this clear username function body. And here we could now access the first name and, for example, set this to an empty string. And do the same for the last name, where we also access the last name and set this to an empty string to clear the name of the user. So now this here is a function that changes the data in the struct. So therefore, of course, we can go down here into our main function and then maybe below the place where we output the user details for the first time, we use our app user struct and call clear username. And then we can again output the user details, and we should of course now see the data we passed to this application when we output the user details for the first time. But once we then cleared the username, we would expect to get the same details but with an empty username, so an empty first and last name. Therefore, if we save this, we can run this application and fill in our details here as we did so often. And if we hit enter, we get something strange. We can see the data we entered here in the first output, but then we see the same data again in this second output, which comes from this line of code here, and that's of course not expected. So why is that happening? Because in this clear username function, in this method here, we are receiving a value of type user. And what's important to understand is that these receiver arguments work just like regular parameters. And there you learned that for these regular parameters, the values are passed around as copies. So when I call getUserData here, and I pass in this text, for example, this text, as you learned, is copied, and I get a copy of that text inside of getUserData. And the same thing happens here in my methods. Now, when we output the data, that's no problem, except for the extra memory that's occupied. That could be a problem if we have a very complex struct, which we don't have here, but that could be a problem. But it will be a problem if we have a method that should change a struct, because we get a copy here. So we're changing the copy. The original struct is not changed. So when I create a struct here in my main function, and I then call clear username, a copy is created and edited. And therefore, when I then call output user details again on my original struct, a new copy of that unchanged original struct is created, and I output the user details for that, and therefore there nothing changed because the original app user struct never changed because a copy was used here when I called clear username. And therefore, when you define methods that should edit a struct, you should not accept the struct as a value like this, but instead as a pointer by adding this asterisk. You can also do that for methods that only output data like this one, for example, to make sure that no extra memory is occupied because no copy will be created. But it's not mandatory here, but you do need to add it here. Otherwise, you're always editing a copy, and that of course is not helpful. So by making sure that a pointer is received here, the code will work. And you don't need to change anything else. You don't need to dereference the struct down there or anything like that. Instead, Go will make sure that a pointer is passed to clear username. And as you learned, we can use that shortcut on pointers so that we don't have to use this longer, more clunky dereferencing syntax. And hence, this code here will continue to work, but will now edit the original value since we now get the address of that original struct value instead of getting a copy. Therefore, with this change made, we can now run this application again, enter our details here again, and you now see that I get the full output here when the data is output for the first time, but then thereafter I get no name anymore. Instead, I just get the birth date because the name indeed now was cleared with help of this method here, which now does receive a pointer, which is required in order to let this method edit the original struct. So methods are another very important struct-related Go concept. Now, in addition to methods, there also is another special function you can create when working with structs, though that function is really just a pattern that's often used when writing Go code instead of a feature baked into the language as methods are. And the special kind of function I'm talking about is a so-called creation or constructor function, which is simply a utility function that takes care of creating a struct, so that you don't have to create it like this in your code, which you absolutely can do, but that you can instead create it with help of a utility function, such a creation or constructor function. Now, those constructor functions typically start with the word new, but again, that's just a pattern, just a convention, not something you have to do. But here I'll stick to that convention. And then they contain the name of the struct that will be created. In this case, user. Then you add a parameter list and curly braces, and you have a normal function. Because, as mentioned, this is now not some feature built into Go, but really just a pattern, a convention which you'll often see. Now, the job of this function now is to create such a struct. Therefore, we can copy this code, paste it in there, and return that created struct. Now, of course, Go is complaining here because I did not specify a return type, so we should do that and make it clear that this function will return a value of type user, so a user struct value. And of course, this function also doesn't have this data that's required, first name, last name, birth date, and so on. So we should accept this here. First name of type string, last name of type string, and birth date of type string. And of course, since they're all of the same type, we can just put the type at the end. And here I'll therefore rename this to first name, last name, and birth date with a lowercase d. And with that, we have a utility function that creates a struct. We can now go down to our code here, and instead of creating the struct like this, we can call new user, and then pass user first name, user last name, and user birth date as values to this function. And we can now call this function as often as we want anywhere in our program to quickly create a new user. So instead of repeating this code all the time, we can now just call this function. And that's not the only advantage, as you'll soon see. But with that, if we save this and we give this a try and run this code, we can enter these details here. And you see that it works as before. Now, one thing you can do in this creation function here, in this constructor function, is return a pointer to the user struct instead of that user struct itself. You then just also have to edit the return type here and make it clear that a pointer will be returned by adding this asterisk here. Now, by returning a pointer here instead of a value, we again prevent this value from being copied, because if you would return a regular value, a copy would be created. That's not just the case for received arguments, but also for returned values. And therefore, by returning a pointer, we avoid this. Nonetheless, as always, this doesn't really make sense and isn't really important for simple values like this. Nonetheless, you should know about this feature, that you can also return a pointer here. Now, when returning a pointer, you also have to edit this code down here though, because now app user will not store a user object, instead a pointer to a user object. Because that is what new user returns, right? That's important to keep in mind. With that though, you can save this and run this code as before, enter all your details, and get the same result as before. But now with that constructor function that now also uses a pointer as a return value. So you learned about this constructor pattern here, where we create this utility function that builds such a struct value. This can be useful since you now only have to call this function to quickly get such a struct, but it can also offer more advantages than just that. For example, you could now also add validation in there to ensure that any data that ends up in your struct meets certain requirements. And when using such a constructor function, you don't have to repeat those validation steps multiple times in your code every time you create such a struct somewhere, but you instead have them in one central place that's always executed when you create a new user. And for example, here we could add an if check to check if the first name is equal to an empty string maybe, or if the last name is equal to an empty string. And both values are maybe unacceptable in this application, even though we reset it later. But when we create a user, we could require that both values are set. And the same could be true for the birth date, where we also don't want that it's empty. So we could have all these checks here and check if first name, last name, or birth date are empty strings. And if that is the case, we might not want to return this user struct. We might not want to create one in the first place. Instead, we might want to return an error. Therefore, this new user function should now not just return this pointer to a user struct, but instead also an error value. And here inside of this if block, we can therefore, if we have an error, return the nil as a value for this user struct here. So for this user struct pointer in this case. And then as a second value, you can create your error. Here again with the errors package maybe to create a new error with an error message that could say first name, last name, and birth date are required. Something like this. Of course, here where we do return a user, because we do have a first name, last name, and birth date, we now also have to return a second value for that error value here. And therefore we have to add a comma here and return nil as a value for the error. And with that, we added extra validation to this constructor, and we therefore made this constructor even more useful. Now we can go to the place where we create this user and also get this error, and then check if error is not equal to nil, which means that creating this user failed. And here I should now use a colon equal sign, since this error variable was not declared before. Only app user was, but error wasn't. Therefore, we need this assignment operator here to declare error on the go. And then we can check if error is not equal to nil, and then do whatever we need to do. For example, return and exit out of the application, therefore, in this case, since continuing with these steps doesn't make sense if we have no user. I do want to output that error message though, therefore I will print the error. Now, if you try running this, you'll note that entering nothing here is pretty hard, because when you hit enter, nothing happens. It continues to wait for input, and you therefore have to manually stop the application by pressing Ctrl+C. And the reason for that is that scan doesn't automatically stop waiting for input when you enter a new line, so when you hit the enter key. You instead have to use scanln to make sure that hitting that enter key ends the input, so to say, so notifies Go of the fact that you're done entering a value. And with scanln used here, if we now run this again and we enter nothing for the first name, nothing for the last name, and then maybe something for the birth date, we get this error message and the application exits. And that's why this constructor pattern can be very useful, because it does not just allow you to outsource this creation logic, but it also makes it very easy to set up validation logic in a reusable way. So our struct here is taking shape. We got two methods and this constructor function. And therefore, we might want to put all this struct-related logic into a separated file and maybe also package. If we want to put it into a separate package, simply depends on our application and how we plan on using this struct. If we maybe need it in different parts of the application, putting it into a separate package might make sense. Otherwise, a separate file might be enough. But here I will go for a separate package, because there also are some important things you should know about structs when they do live in their own packages. And therefore here, in this project, I'll add a user folder and in there a user.go file, and I'll name my package user. And now we can go back to the structs.go file and grab that user struct and the methods and the constructor function and cut all that code here and move that into user.go, like this. Now we must make sure that we import time and the fmt package here. So we should import fmt and time like this. And we also must import the errors package. So that should also be added here, like this. Now with that, this code here lives in its own package. And in order to use it in the structs.go file, which is part of the main package, we therefore have to import our user package. We can also get rid of the errors and time packages here because we're no longer using them. Now to import our own package, as you learned, you have to use your module path, in my case here example com structs, and add this here. And then here it's the user package I want to import. With that, in our code, we should be able to access the user package and then use the dot notation to access the things it exports. And at the moment, there is nothing that would be exported because, as you learned earlier in the course, only things, types, variables, constants, functions that start with an uppercase character are made available outside of that package. So in order to make the user struct available, for example, it would have to start with an uppercase U. With that, back in structs.go, we could access user.user. And we could now create a user struct here, or in this case, a pointer to a user struct. And I will soon use the constructor function again, but for the moment, I want to start with the user struct. So we can create a new user struct value and then get the address of that value by using user like this. But you'll now notice that when you try to assign values here, for example, if you try to set the first name field to this struct, this doesn't really work. If I set this to max here, like this, I'm getting an error. Now I'm getting a bunch of errors. One problem is that I'm setting up two variables here, and we can get rid of the error for the moment. But the other problem is that I'm trying to access and set the unknown field first name. And why is first name unknown? It is part of the struct after all. Well, because this uppercase starting character rule for exporting something does actually not just apply to the struct type overall, but instead also to all the fields in a struct. You can export a struct and still not export all the fields in that struct, if there, for example, are certain fields that should not be accessible from outside this package. If the first name field, for example, should be accessible, you have to start with the uppercase character there as well. So with this code here, for example, first name would be accessible from outside this package, the other fields would not. Therefore now in structs.go, I can set first name with an uppercase F. And you see I'm now not getting any errors anymore. Here I'm getting an error because the type, of course, now can be found in the user package. So it's user.user. But with that, we're accessing and creating a struct that is defined in the user.go file and that is then exported by that file. So it's really important to understand that the casing matters also for fields inside of a struct. But here for this struct, we created our own new user constructor function anyways. So we shouldn't really need to expose the struct, do we? Well, I do want to expose the struct type, user, so that we can set up the type, for example here, in other packages. but I indeed don't want to expose the fields. Those, in this case here, and that might be different for your applications, but in this example here, these fields should indeed not be accessible from outside this user package. Therefore, I'll make sure that they all start with a lowercase character. And back in structs Go, we therefore can't create this struct like this anymore. Instead, we'll have to use this constructor function. But in order for that to be available outside of this file, it also must start with an uppercase character. Otherwise, we can't call it. Here we now also must update the return value type, because my struct type here now does start with an uppercase U, and therefore we must use an uppercase U here as well, and also here where I create the struct value. Now with that, new user is made available, and therefore back in structs Go, we can go back to this code and access the user package to access new user. And now we can pass user first name to new user, user last name, and user birth date again. Now, since this also potentially returns an error, we have to accept and store this error like this, and therefore all this code here works again. Now, what does not work is this code, though. Calling these methods fails. And that fails because, you might already guess it, these methods start with a lowercase character. And therefore, again, they're not exported. They're only usable from inside this user package. Now, again, that might be what you need for your application, but here in this demo, my idea indeed is that we can't directly interact with the struct fields, but that we instead have to use the methods to, for example, view the user details or to clear the username. And therefore, for this demo app, they should be exposed. They should be exported. Hence, I'll change their names to start with uppercase characters. And we also need to adjust the struct type name here, since it does start with an uppercase U now. And with that, these methods are exported, are made available outside of this package. And back in structs Go, we can therefore now call output user details with an uppercase O, clear username with an uppercase C, and also update this code. And with that, there should be no more errors in the code, and the application should run again. So if I run it here, I am indeed asked for my name, and if I enter something invalid, I get this error message. So we are clearly using that constructor function, and its validation works. And on the other hand, if I enter this and I enter valid values for all fields, I get this output and then the same output without names because they were cleared. And that's how we can put a struct into its own package and then make it available in other packages. Now there's one more thing you should know about this constructor function, because when you have a struct in a separate package, as it's the case here, it's not uncommon to just name this constructor function new, because you have to call it on the user package anyways. So we previously called user.newUser, which is of course not bad, but if we now rename this function to just new, we just have to call user.new, and it's still very clear that we're creating a new user with that, because we're calling it on the user package. So that's also a pattern you'll see in many Go projects, that you have a package that is mostly about one specific struct and all its methods and so on, and that therefore exposes such a constructor function which is just called new, which creates a new instance of that specific struct about which this package is. You, for example, also see that on the built-in errors package, because there we also called errors.new, not new error. This function doesn't exist, but instead .new to create a new error value. So the people working on that errors package also followed this pattern of just using new as a constructor function name. So now with that, we learned a lot about structs. There's just one last related feature that I want to cover here before we'll then practice what we learned in a slightly more realistic application. And that last feature I want to cover here is a feature called struct embedding. And the idea is simply that you build a new struct that builds up on an existing struct. In other programming languages, like Java for example, where you work with classes, you might know this concept under the name inheritance. Now, a struct has no classes and it has no inheritance, but you can still build another struct type that, for example, builds up on that user type and therefore contains all the fields and all the methods of that user type, but also adds its own fields and own methods. And for that here, I'll add an admin struct type, which should be a user, but for this demo here, it should be a user that does not just have all these fields, but also, let's say, an email and a password field. So the admin should have an email of type string and a password of type string. But it then should also contain all the fields of the user struct. And to make sure that the admin struct type has all these fields, you have to embed the user struct into the admin struct. And you do that by simply using the user struct name here in that field list of the admin struct. Now you can give it a name like this, but you can also add it anonymously like this. Now when you create such a struct that embeds another struct, you can still work with that struct just as you do with any other struct. For example, we could add another constructor function here, new admin. So now I have two constructor functions, one for a standard user and one more specific function for creating an admin, where I expect to get an email and a password as a string, and where I then plan on returning an admin value. We could also return a pointer here, but here for the moment I'll just return an admin value like this, and therefore a copy of the admin struct that will be created by this function. Now we could again add validation here and check if email is maybe empty and so on, but here I'll keep it simple since we already learned about this, and I'll instead just create this admin struct here and return it. And now here we can set the email to whichever email we received here, and the password to whichever password we received. And we can now also set all these user fields because we are embedding the user. And the idea is that we have all the user fields as well. Now to set them here in this new admin function, we have to set the user field and set that to a user struct. So to the embedded user struct we want to add here. And then here we can set up first name, last name, and so on. So therefore, of course, this admin function also should accept these values, or we hard code them. For example, here I'll simply hard code the dummy values admin for the first name and also for the last name. And then here for birth date, I'll add dash dash dash, let's say. And for created at, I'll again use time now, like this. And that's how we create such an admin struct that contains a nested user struct. Now, if you would have assigned a name to this embedded struct here, by adding it in front of the type, you would have to use that name when constructing the admin struct. So instead of user with an uppercase U here, you would now have to use whichever name you did assign in your admin struct type definition. And with that, we are creating a new admin. Now we can go to the structs go file and of course create such a new admin, maybe down here. Here we can get our admin by using the user package and calling new admin. And then here we can pass in a dummy email address and a dummy password. This will give us such an admin struct. But at the moment, I can't do anything with that admin struct, because the admin struct has no exposed fields. They're all lowercase, including the nested user struct. So to expose that, we would have to give this a field name of user starting with an uppercase U, or any other field name here, but it must start with an uppercase U. Of course, we then also must target this new field name down here when creating the admin struct instance. Now back in structs go, since I am exposing that, I can access the user struct, and you can see that through that exposed user struct, I can also access the methods that were defined on that struct, like this. And therefore, of course, we can also call clear username and then output the details of the admin again. And now with that, we created the admin struct that embeds the user struct. We created this constructor function for this struct, and we're using it here. Let's now see it in action. For this, if we run the application, I have to enter my name, of course. That didn't change, but this is still for the regular user. But if I now hit enter after entering the birth date, I am getting that admin data here. And you see that the methods I defined on the user struct also work on the admin struct. It outputs the data and it cleared the name of the user. So that all still works. Now it can be a bit annoying to always have to call these methods on this nested user field. And that's why you might prefer anonymous embedding over explicit embedding, where you add such a field name. And therefore here I'll get rid of that field name. The code for creating the instance doesn't change, because if it's anonymous, you still have to repeat the type here as a field name when creating this. But now back in structs.go, this code still works, but now we can actually also call these methods directly on the admin struct itself. Because when using anonymous embedding, you can access the fields and methods of the embedded struct directly on the struct that's embedding the embedded struct. So we can now access all the fields, if they would be exposed, of the user struct and the methods of the user struct directly on the admin struct. And that's what I'm doing here. So with that, this code got a bit more concise. And if we again run the application, it therefore still works as before, as you see here. And that's how you can build structs based on other structs, and how you can then access the nested methods and also fields if they would be exposed, how you can add such a constructor function, and how you can therefore in general write more flexible code. In this section, you of course learned a lot about structs, a custom type you can create to group related fields and functions together into one value, essentially. You learned how you can create structs by creating instances with this notation, and that you can create such constructor functions to outsource the creation and to set it up such that you can create structs in an easily reusable way and even add extra validation or any other logic that should be executed whenever a new struct instance is created. You learned that you can put structs in packages, and that the casing, as always in Go, matters when you want to expose those structs and their fields and methods to other packages. Speaking of that, you did learn about methods as well. And here it's really important to keep in mind that if you have a method that wants to edit a struct, you must make sure that it receives a pointer to that struct as a receiver argument. Otherwise, it'll get a copy and just edit that copy. For outputting, it's not that important, but especially if you have more complex structs, which we arguably don't have here, but if you would have more complex structs, passing them around as pointer might be a good idea. That's also true for the constructor function, of course. Here for the new constructor function, which creates a new user, I am actually returning a pointer to the created user struct. so that we don't copy it and have it twice in memory, but we instead only have it once and we return a pointer to that instance we just created. On the other hand, for the new admin struct, which creates such an admin struct instance, which is this struct type, which embeds the user type to extend it and add extra fields or also methods to it. And this new user constructor function, for example, does not return a pointer, but instead the value and therefore a copy. And as mentioned, that can also be fine, and it can actually also be more efficient than passing around pointers if your values aren't super complex. And structs are a really important feature in Go. We'll use them a lot throughout the rest of this course, as you will see, and you'll in general use them a lot when writing Go code, no matter on which application you are working. Now, before we'll continue working with structs and practice working with structs, there's one kind of related thing I also want to mention here. Because of course, in this section, we created our custom struct type, and that is a very common type you will create. And we, for example, also added methods to that struct. And again, that's typically something you'll do quite a bit when working with Go. But it turns out that in Go, you can use this type keyword not just to create custom struct types, though that's probably how you will use it the most, in conjunction with the interface type, about which you will learn later, but you can also use the type keyword to assign an alias, you could say, to other built-in types. And you'll see why you might want to do this in a couple of minutes and also again later in the course. So let's say we want to create our own version of the default string. So I'll name it custom string, but the name is up to you. So that's the name for my type, but now after this name, I don't add struct because I don't want to define the blueprint for a struct here. Instead, I now use the built-in type, string for example, for which I want to assign an alias. Now in my application, I can use my own custom type here, custom string, instead of the built-in string if I want to create a variable that should be of type string. And that doesn't sound like a good idea. I mean, what do we gain by doing that? Now it's longer than the default string and it's exactly the same type. Well, of course, theoretically, we could have chosen a shorter name, so we would at least save some characters. That's something we could do. But still, this might not make too much sense, because in bigger programs, it might not be obvious that str refers to the built-in string, and we would have to look up what's behind that alias. So just using string would typically be a better idea, because it's clear which kind of value we really want here. Nonetheless, you can create such an alias, and later in this course, once we dive into arrays, slices, maps, and functions as values, you will see better use cases for assigning an alias to a built-in type. So use cases and examples where this makes more sense. Here it doesn't make too much sense like this. But it makes more sense once you know that you can then actually also use your custom type to assign methods to it. So functions that are attached to it, just as we did it with the struct type. Here we could add a log function and then add this receiver argument about which you learned, and then use our own str type here. We, for example, couldn't use the built-in string type. Here I'm getting an error that I can't define new methods on that non-local type string, so on that built-in type string, you could say. But I can add a method to my custom type, even though under the hood that custom type simply refers to the built-in string type. But you could say that Go builds a copy of the built-in string type for you under the name str, and you can then add a method to that. Well, and then here we can also assign a name to that received value, and the received value will be the string on which we then call log. And we could then use the FMT package, for example, to output text here. And now we can use our custom type to create a variable with that type, and then of course also assign a value. And here I don't want to do that in one step, because if I would do it in one step, Go would of course infer that name should be of type string, because this here is a string. Therefore, if I want to force Go to use my own custom type, we have to explicitly set our own custom type and then assign a value. Though we could of course still do that all in one line if we wanted to, but this type assignment here is important. And once we did that, we can use that variable and call this log method, which then would trigger this code here. Therefore, with that, if you now run this application, you see max here in the console, in my case, because of that custom type and that method we created here. And of course, you can assign such a type alias to any built-in type. We could do the same for int or float64 and so on. And as you will see later in the course, as mentioned, you can also create such type aliases, such custom types, as I call it here, for more complex built-in types. But again, I'll get back to that later. Now that we learned a lot about structs, I want to dive into a slightly more realistic demo project so that we can repeat what we learned and practice what we learned. Definitely feel free to pause the videos from time to time to try out the next steps on your own. That will be a great exercise, but definitely also feel free to just follow along. Now, what we'll build is a notes-taking app that will use a struct for storing some note data, but will not just store the note data in a struct in memory whilst the application is running. Instead, we'll also store our note data in a note.json file. So a file that stores data in the JSON format, which looks like this. So that's what we'll build. And for that, I'm in a brand new empty folder, an empty project. And as a first step, I'll run go mod init and give this a path of example.com/note. And with that, we can get started working on that. Now I will get started by adding a main.go file. And of course, as you learned, this does not have to be named main. In most sections thus far, I did not use main as a name here, but it must be part of the main package, because this should be my main entry point for this application. And therefore, of course, we also need that main function, as you learned. Now, my goal with that application is to ask the user for the data that should be stored in a node, and then this data should be written to a file. Therefore, as a first step in this main function, we should get that user input for that node. And I'll write a helper function that helps me get that input, which I'll name getUserInput, where I want to get the prompt that should be shown to the user in the command line as an argument, as a parameter of type string, and where we can then use the format package, which of course must be imported therefore, to output this prompt, and where we then of course also use the format package with the scan method here to get the user input. For that, I'll add a helper variable called value, which will be of type string, and I'll pass a pointer to that variable to scan, and then it's this value which I want to return. For that, of course, we must make it clear that a value will be returned by getUserInput, and I'm doing this by adding this return type. We can actually also get a bit more fancy here and check if value is an empty string, so if the user did not enter anything, and I'll use scanLN instead of just scan, so that the user can theoretically hit enter to confirm an empty input. And if we got an empty value, I want to either return a default value, or we added this function such that it potentially gives us an error, and I'll go for that approach. So we'll return two values where the second value is this potential error. And I'll therefore return an empty string as a value for the input, but more importantly, I'll create and return an error with help of the errors package, which also must be imported if we have an empty input. And here we can use that new function to create such a new error value. And then here I'll say invalid input. And you could of course say whatever you want. Here, if we do have a valid value, I'll return nil as a value for the error. With that, we got this utility function, and back in main, we can now get the user input here. And I want to get two pieces of input for the node that's going to be stored here. I want to get the title of the node and the content that should be stored. So therefore here I'll say node title, and then I'll call get user input again and say node content. And in this application, by the way, we'll only manage a single node because we haven't really learned yet how we could work with a list of nodes, but we will of course learn about list data later in this course. Here it will be a single node which should have a title and a content, and therefore I'll store these values in variables like this, which will later end up in our struct, but of course we could also get an error here. For both inputs, we could get an error if the user entered nothing. Therefore, I also want to check if error is not equal to nil, and if that's the case here, I simply want to return and exit out of this application. I also want to output the error message though with println. So I'll println the error. And then we can repeat that here for the second user input we got. Now, of course, we could also outsource this into a separate function to keep the main function lean. And we could add a function called getNodeData, where I paste in that code I just wrote. And the idea here simply is that getNodeData will take care about this error handling and about calling getUserInput, and will then just return the two string values which we have here, the title and the content, if everything worked. However, we should also return an error here, since this of course could also fail if one of these if checks here becomes active. So we might want to return the error here if we have an error, and return empty string values for the first two return values in that case, and do the same down here. But if we don't make it into one of these if blocks, we can instead return the title and then the content and then nil for the error. And with that, in the main function, we can get the title and the content and potentially an error by simply calling getNodeData. Now, if you want to put this into a separate function or not is entirely up to you. Here, I did it just for demonstration purposes. And now here, I of course want to check if we got some error, in which case I still want to return, and in which case I also still want to output that error. But now I only have one if check here in the main function because I outsourced the other logic into a separate function, therefore keeping my main function a bit leaner. And with that, we are getting the input we need for this application. Now, as a next step, we can start working on that node struct that should store that data. So we're fetching user input. Now it's therefore time to create a struct that will store that data. And I could of course do that here in the main package, but to also practice the usage of packages, I'll create a new package in that project, which I'll name node, where I'll have a node.go file inside of that node folder. And that will now belong to the node package, so a separate package. In there, we can then create a node struct type like this, and I'm using node with an uppercase N so that we can refer to that struct type from outside this file, so that it's being exported. Then, as a next step, we have to define all the fields that should be stored here in that struct. And for this demo application, that will be a title of type string and the content, which is also of type string. Now we could use title and content with uppercase starting characters if these fields should be accessible from outside this package. But here I actually want to keep them contained in that package and not make them available outside of the package, because I'll instead use methods to allow other packages to interact with that struct. I'll also add one more field, created at, where I'll use the time package, which is part of the standard library and must be imported, and there the time type, which is also a struct, just one defined by the Go developers, to store a timestamp for when this node was created. And with that, we got the node struct. Of course, that's not all I want to do here, though. Instead, I also want to create a creation function, a constructor function that builds these node struct instances. That's not a must-do, but a common pattern. I'll name it new, since we're inside of a package called node, and it therefore will be clear that when we call a function called new in that package, we'll create a new node. And this function should of course receive the title and the content, which should both be of type string, and it should return a node. Or a pointer to a node if you want to avoid the copy, but as mentioned, for simple data types like this, it's typically preferable to not use a pointer because of the extra overhead that takes place behind the scenes when working with pointers, and therefore I'll just create a node value like this, and I'll return a node instance created with this code. Of course, now we also must populate all the fields of this node struct blueprint though. So we should set the title to the title we're receiving as an argument. We should set the content to the received content and created at to time.now, calling the now function from the time package. And that's therefore our constructor function. However, we could now actually make it more useful by adding the validation code we added here in the main function into this constructor function. Because ultimately, you could argue that it's this node package that should worry about getting correct data for this node. Therefore, I will actually grab this validation logic from my getUserInput function and cut it from there, and instead add it here in this new function in my node Go file. Now here I want to validate the title and check if it's empty, or if the content is empty, in which case I still want to generate such an error. For this, we just need to import the errors package into this file here. And we must make it clear that we're not always returning a node, but sometimes also an error. Of course, here this also wouldn't be a valid fallback value for the node. Instead, here I want to return an empty node, basically, as a dummy value if we got no valid input. And here, on the other hand, if we do have valid input, I'll return nil for the error. So therefore now we got this finished new constructor function which contains validation, and we can therefore now use this constructor function and therefore implicitly this node struct in the main Go file. So here we should start by importing our own package. In my case, the path for my module is example.com/node. So my import path for the node package here is example.com/node for the module path, and then again /node for this package here. So here, after fetching and validating that user input, we can of course start using it here. Now actually, since we outsourced the validation logic into this new function here, we can get rid of it here in getNodeData. We can simplify that. So we can get rid of that here. And the getUserInput function down here will also no longer potentially return an error. So it will just return a string, and therefore its return value should be adjusted here as well. And that then allows us to go back to getNodeData, get rid of the extra error value which we expected before, and will no longer return an error here therefore, instead just two strings, so that this function is way simpler now. And with that we can now use this node package and create a new node here after getting the node data, without an error though, by using the node package and now calling this new constructor function, which wants a title and the content, and which then potentially does return an error. But we'll deal with that in a second. First, let's pass the title and content that's fetched by getNodeData to this new constructor function. And then let's store the results we get back, which is that created node, or the user node, that could be a name we want to assign, and potentially an error. Now we are handling the error here, so we should keep that around, but after this if check, we'll know that we don't have an error and that we instead do have a node with this title and content inside of it, and therefore now as a next step, we can make sure that we can then do something with that node. Because at the moment, we can just create it and nothing else, and that's not all I want to be able to do with it. Now, one thing that would be nice to do with that node is display it after it was created. Later, we'll also save it to a file, but as a first step, let's simply display it. And to do that, we could of course expose these fields by giving them uppercase starting characters. That would then allow us, in the main package, to access usernode.title, for example, and, for example, output that to the console, but that's not what I'll do here. Instead here, all these fields should not be exposed, and instead I want to add a method that can then be called to interact with that node. And that method could be called display, starting with an uppercase D, so that it can be used from outside this file. And we'll turn it into a method that's attached to this node by adding such a receiver argument here. So this pair of parentheses between func and display here. Here we should then add the node type, so our struct type, as a received argument, and we can give this a name, like node, which can then be used internally inside this function to interact with that received node struct value. So in here, we can then use the format package, which you should therefore import, to output some data about that node. And here I'll output data with help of printf to mix things up and say your node titled, and then a placeholder for a value, has the following content. And then a colon and maybe 2 line breaks, and then another placeholder for a value. And now we have to list all the values that should be used for these placeholders. And for the first placeholder, I of course want to have the title. So since we received a node here through that receiver argument, we can access it and access the title. Here in this file, we can access that without problem because we're in the same package. And then for the second placeholder, it's node content. We could display more information, but here that's all I want to output. And therefore now with that, we added this method, and back in the main Go file, we can then call this method. Here after this if check, to make sure that we have a valid node, there we can call user node display, like this. Well, and with that added, if we execute this, we have to assign a node title, like learn go, and then I'm not getting asked to provide some content value. Instead, it immediately continues and then finishes. And we're getting this strange behavior because of the scanLn function here. Actually, all these scan functions are basically meant to be used for single word input. So previously in the course, when we just entered a single number or something like that, we had no problem with them. But here, where we expect longer text, we can't really use scan. Instead, to get the user input, we'll have to go for a more complex solution. We're facing this problem where we can't enter longer text here because we're using this scan function for getting the user input. And this scan function doesn't really work if you're expecting input that consists of multiple space-separated words. And thus far in the course, we typically only got single words, a single number, or something like this. But here in this demo app, where we want longer text input, we can't really use scan. Instead here, we have to go for an alternative, slightly more complex solution to get the user input. We can use another package, buff.io, which you need to import, which exposes a new reader function. This is essentially a constructor function that will give us a value that will allow us to read user input. Now for that, we must pass an argument to new reader, an argument of type reader, which in the end simply describes to new reader from which source we want to read. And here we of course want to read from the command line, and we can specify that as a source by using the OS package, which you therefore also must add to your imports. And there we must access the stdin, the standard input variable that is exposed by this package. Standard input is simply your command line. So with that, we're creating a reader that listens on the command line. So we should store that reader in a variable, because now as a next step, we can use that reader to read the string that was entered by the user. And read string wants to know at which byte it should stop reading. So at which character it should stop reading, you could say. And here the byte where it should stop reading is this line break identifier here. That is a single character in the end, and that's where it should stop reading. Now what's important here is that you don't use double quotes here, but instead to specify such a single byte, such a single character, you could say, you need single quotes. Because that's actually a special value type in Go. It's a so-called rune, which in the end is a single character. So we could also have an A in there, for example, but here we need that line break. So that's where we want to stop reading. As a result, we'll get back the text that was read and also potentially an error if something goes wrong with reading that. Therefore, we should also add a if check and check if the error is not nil. So if we have an error, in which case here, I will return an empty string as a default value. Otherwise, if we make it past this if check, we have the text, but this text will now still contain that line break. Therefore, we have to remove that line break from that text. We can do that with help of another package, the strings package, which also must be added to your imports. And these packages are all part of the standard library. This strings package exposes some utility functions for working with strings. For example, a trim suffix function, which I need here. This allows us to remove some text from the end of a string. And here I want to pass in my raw text, so this text here, which contains that line break, and I want to remove that. So the new text is the old text without that line break. However, we also need to remove an additional character, which is sometimes, but not always there. We need to remove this special character. Because on Windows, a line break is actually not created with just /n, but instead with /r/n. And therefore we must remove both. And with that, we then finally have the cleaned text which we can return. So that's now the slightly more verbose approach we have to use to read longer text input. But with that, we should be able to save all that and again run the application to enter our title and then the content, like this. And as a result, we should then get this output here where we see the node title, learn Go, and then has the following content, and the content is then output here. And the content is output down there because in NodeGo, in this display method, we have 2 line breaks after content colon, and then we output the content. It might also make sense to have some line breaks after that value, so we can of course also add 2 line breaks here. Now if we run this again, we can say learn go in depth like this, and we got this output. Now I just want to add some spacing here between my prompt and the user input, and we can easily achieve this by going to main Go, where we're getting that user input, and by changing print to printf here, so that the text I want to output is actually this value here, and then an extra white space. With that, we now have this white space here between the user input and the prompt, so that we can enter this like that. Yeah, that works. So with that, we're able to display the node, but of course, ultimately, we want to save it to a file. So that's therefore what we can work on next. And I want to expose this save to file functionality through another method that's added to the struct. Therefore here we can define another function in the NodeGo file and call it save with a capital S so that it can be used outside of this file. Now it should be attached to this node, therefore I'll add this as a receiver argument. Since it doesn't edit the node, we don't need a pointer here, just as we didn't need a pointer here. If we had a method that did edit the node, we would need a pointer though. Otherwise, we would be editing the copy and not the original node. Here, we don't need a pointer, as mentioned, and therefore, in the save method, we can now make sure that we extract all that data and write it to a file. And for this, we can use the OS package, which you must import into this file in order to use it. Because this OS package exposes a write file method that allows us to write some data to a file with a name of our choice. Now here I want to have 1 file per node, and the file name should in the end depend on the title chosen for the node. Therefore we could pass node.title as a value for the file name, but it's worth noting that this title here could actually contain characters that should not end up in a file name. Or put in other words, I want to transform this title into a format that always serves as a nice file name. Therefore here, in the save function, I'll get my file name by using another package built into Go, or part of the Go standard library to be precise, and that's the strings package again, which we already used earlier in this section. And here I'll call the replace all function that's exposed by this package to replace all substrings in a given string with a new string. So to replace a character with another character, for example. And here I want to replace characters in my title, and it's worth noting that this will not edit the original title, but instead produce a new title, a new string that contains all the changes I want to make. And then I want to produce all blanks, so all white space, with underscores, for example. But that's not all I want to do. In addition, I want to make sure that my file name only contains lowercase characters, no uppercase characters, even though the title might. Therefore, I'll again use the strings package to call the toLower function, which will do what the name suggests. It will convert all uppercase characters in a text to lowercase characters. And I'll pass my file name to toLower so that my new file name is the old file name with all its uppercase characters transformed to lowercase characters. Of course, here I'm not creating a new variable though, instead I'm assigning a new value to an existing variable. So we don't need colon equal sign here, but just the equal sign. So that's now my cleaned up file name, which I want to use here, but that's not all the write file needs. Instead, it also needs the data that should be written to this file. And here, I don't want to transform all my data to text, even though we could do that, but instead I want to create a JSON file that contains data in that JSON format, which technically is text, but text stored and formatted in a certain way. And we'll create that JSON format with help of another package. That other package that will allow us to convert our content to JSON data is the encoding/JSON package, which also is part of the standard library. With that imported, we can go down here into our save method, and there we can now get our JSON content, you could say, by calling JSON, so this JSON package we're importing, and then there the Marshall function, which might be a weird name, but in the end, that's a function that will convert data to JSON. Now, it does work with various kinds of data, for example, also with structs. So we can pass the struct as a whole to Marshall, and that will convert this to text in that JSON format, which is quite convenient. Now, Marshall also returns an error if that conversion goes wrong, so we should accept this here. And we then, of course, also should handle it. So here I'll check if error is not nil, and if that's the case, I want to return the error here. So I'll return so that this method doesn't continue executing, and we don't try writing to a file, and I'll return this error so that we can handle this error in the place where we then called this save method. Now, of course, in order to return an error here, we have to set up this return type and make it clear that save will return an error. Now, with that, we're handling the error. We got the converted node now converted to this JSON text, and it's now this JSON text that should be stored in this file. Now, conveniently, this JSON text is actually already such a byte collection, and that's exactly what write file wants, and therefore we can pass it just like this to write file. Now, as a last step, we also need to define the file permissions, and here I'll use this permission set, which assigns read and edit permissions to the owner of the file and only read permissions to any other users that might get access to the file. And with that, we got the code for converting the node to JSON and writing it to a file. Now, of course, this save method now does return an error though, and at the moment I only return one here, but I return nothing if we write to a file, so we might want to return nil here, since everything worked, but actually writing to a file could fail, and write file therefore also returns an error, so it would be better if we simply return this write file operation, and therefore this error that's generated by write file. Because that will be nil if everything works, but it will be an error value if something goes wrong. And that's now therefore the finished save method. Now we can use that method in the main Go file. Here, after displaying the node, we can also call user node save, like this. Now, of course, this will give us an error, at least potentially, and error does already exist, so I don't want to create it here, just reassign it. And we therefore can check if error is not equal to nil, and if that's the case, I want to output a message to the user where I say saving the node failed, and I'll return and exit out of the program. If we make it past this if check, we know that everything worked, and therefore here we could output saving the node succeeded. And that should be it. That should be all the code that's needed here in this main function to save that node with that save method we worked on. And hence, now if we run this application and we choose a title and a content and hit enter, we should get saving the node succeeded. And we should now also have a learn go file in here. Though at the moment, this file lacks a file extension, and in addition, it lacks the content. By the way, it's named learn go because I chose learn go as a title, and due to how we set up this save method, we take that title, replace all whitespace with underscores. So this whitespace here was replaced with this underscore, and we then convert it all to lowercase. That's how this name was created. But as mentioned, this name is lacking a file extension, so we should change this, and what's worse, it's lacking the content. So we'll fix both in the next lecture. Now let's start by making sure that our file name also has an extension. And for that, when I added my file name here and I convert it to lowercase, I'll actually also add .json here at the end. So I use the plus operator here to combine two strings to a longer string. That's the first step. The bigger problem is that there was no content in the file, or almost no content in the file. Definitely not our struct data. And the reason for that is that this JSON package with its Marshal function will actually only extract and convert struct data that's made publicly available. So that's not exclusive to this package. And at the moment, since all these fields start with a lowercase character, they are all exclusive to this package. So we must add a capital case starting character to all these fields to make sure that they do end up in this JSON file. Of course, now we also have to access node.title with an uppercase T here. So here in this save method. And also adjust our code here in the new method and assign a value to title with an uppercase T, content with an uppercase C, and created at with an uppercase C. And then last but not least, here in display, we of course also must make sure that we access title and content with uppercase starting characters. With that, we prepared the struct to hopefully be converted to JSON data, and we can now run this application again. Enter our data, the node was saved, and now we have this learn go JSON file here, so we have this extension, which is an improvement, and in there we now indeed also see data. And what you see here is now this JSON data format, where you have these curly braces and then your keys between double quotes and the values between double quotes. But that's now the data generated and saved by this JSON package. So this application here is basically finished now, but there's one last struct related feature I want to add. Because at the moment, in this learn go JSON file, we get the same titles here, the same keys here in this JSON format that we also defined in our struct. And that's of course probably expected and also fine, but for JSON content, it would be more common to have lowercase keys here. And for example, instead of using created at like this, we might prefer created at like this. So it would be nice to have different keys here in the output JSON than we have here in this struct. And this can be achieved with help of a feature called struct tags, which is a feature built into Go. Struct tags are essentially metadata that you can add to your struct fields. And that metadata can then be picked up by any code or package that cares about it. And it turns out that the JSON package does care about such metadata. If it is defined, it will be considered. So here we can add such metadata to the title, for example, by adding backticks. Opening and closing backticks. Not single quotes, but instead the backtick character on your keyboard. That's how you add a struct tag, and you add struct tags to fields in your struct. So here we're adding one to the title field. Now that struct tag can then be used to assign metadata. For example, here you can add JSON : to add a JSON key here, so set the JSON metadata field onto this title field, and then set this to any string value of your choice, enclosed by double quotes. And there is no fixed set of metadata keys you could target. Instead, you can add any metadata you want here, but it will depend on the code that processes this node, whether that metadata does something or not. And the JSON package here will look for this kind of metadata, which has this format, JSON and then a colon, and it will then use whichever value you specify between the double quotes as a key in that JSON output it generates. So if I, for example, define ABC here as a value for JSON in this struct tag that is assigned to the title, then ABC would be used as a key by this JSON package once it processes the node and stores its title. That's how that works. Now here I don't want to have ABC, but instead simply title with a lowercase t. And we can now add similar struct tags to the content for content and created at, and here I'll use created at like this. So not just lowercase, but instead also with an underscore to separate the words. And that's how you can add such struct tags, so how you can add such metadata. And it's really important to understand that by default this won't do anything if you don't have some code or a package that picks up that metadata and uses it, like the JSON package does. And therefore that's all. If you save that, and you then maybe delete this learn.json.go file and this empty learn.go file we had from earlier, and you then run this application again, and you enter all your data, you get the same output as before, of course, but we now have this learn.go.json file, and in there you now find these new keys. Especially here at the created at key, you can see that the struct tag was picked up and was used by this JSON package. So struct tags is another feature you should be aware of, because certain packages use that feature, like the JSON package does, to change their output or their functionality. Now that we learned a lot about structs, we'll dive into a kind of related topic in this section, because we're going to explore interfaces in Go. And therefore, in this section, you will of course learn what interfaces are, and you will learn how to create and use interfaces in your Go applications. Now, to explore this concept of interfaces, I'm actually back in this structs project we worked on earlier in this course, where we allowed users to create and store nodes. And now let's say that in this overall application that we're building here, we don't just want to allow users to store nodes, but also to-dos. And a to-do should also be a struct, just like node, but unlike node, it should not have a title and not have the created at field here. Instead, it should just have a content, which for a to-do should be named text though. So, a struct with a different structure. It should, however, also have a display method and a save method that saves it to a file. And that's a scenario where interfaces can help us, as you will see. But in order to see how they can help us, I'll start by copying the node folder, and I'll paste it in here and rename it to to-do, so that I have both node and to-do. And then here I'll rename that node.go file in the to-do folder to to-do.go, and of course also rename the package to to-do. And in that to-do.go file, I then want to have my to-do struct, which should have a text field, which when saved as JSON should have a text key. And it should not have a title and not have the created at field. Now it should have a method attached to it, but here of course we'll attach it to the to-do struct and we'll get a to-do, and I simply want to output the to-do here. So I'll just print a new line with my to-do text here. And then of course we need a save method where we also get our to-do, but where I then will simply set the file name to to-do.json. So a hard-coded file name, which of course also means that for this app, we'll keep on overwriting that file. And it's then this to-do that should be converted to JSON and stored in that file. I also want to have my constructor function here, which only needs the content as input now, and which will return a to-do, of course. And therefore only the content will be validated and will return an empty dummy to-do if validation fails, and otherwise will create this to-do instance, which, however, only has a text field, which is set equal to this content here, like this. Therefore, we could of course also name this parameter text, but here I'll keep the name content. So with that, the code in this to-do Go file of course looks fairly similar to what we had in Node Go. And I'm of course doing that on purpose here. Now in the to-do.go file, we now just have to get rid of some packages which we're not using here. But with that, we got our to-do package with the to-do struct. And we can now use that in the main Go file. So here, besides importing the node package, we can also import the to-do package. And we can then start using it. Now with the to-do package imported here, we can use it in the main function. For example, to get some data for that to-do. Now I do have the getNodeData function here. Of course, similarly, we can create a getToDoData function, which will only return a single string, because a to-do only consists of one string value in the end, the text that's stored in the to-do. And therefore here I'll get my to-do text by calling getUserInput and then asking for the to-do text, like this. And then we can return this text. And of course we could therefore also do this all in one step and just return it like this. And therefore we technically don't even need this wrapper function. We can instead just put that code right into the main function and save that extra function. So here we can get the to-do text by calling getUserInput like this. Now that we got that, we can create a to-do. So we can use the to-do package and call the new function to pass our to-do text to it. Now as a result, we'll get back a to-do or an error if things go wrong. And therefore here, I'll then check if error is not equal to nil. So if we have a problem, in which case I wanna output that error and also return and not continue. Alternatively, we could of course also continue and still allow the user to take notes if we wanted to. But here I'll return also, because thereafter, once we have both a to-do and a note, I also want to call to-do display here, and I also want to save the to-do. So we can basically copy this code here, or actually all this code here, because all this code here is dealing with saving a note. And we can paste that here to call save on the to-do and say saving a to-do failed or saving the to-do succeeded. So we have pretty much the same code as we have down here for the note, here for the to-do. If we now save everything, we can run this application, and I'm prompted to enter my note title here, learn Go, in depth, and then to enter my to-do text. I want to learn Go. If I hit enter, all these things are being output. Here, for example, my to-do text, and then it's being saved. And then here my note information is output, and that is then also being saved. And indeed, if we take a look, we of course still have the learn Go JSON file from before, but we also have the to-do JSON file, which contains this to-do information. So it all works as intended. But still, this code can be improved. And it can be improved with help of interfaces. So what's the problem with this code here? The problem is that we have quite some duplication. For example here, where we save the to-do. This is essentially the same code as down here for the note. We're just executing it on a different type of value, on a to-do instead of a note. Still, it would be nice if we could add a function here, save data, could be a generic name, that accepts either a to-do or a node and then essentially executes this code. But without interfaces, we can't write such a function, because the data that we want to save needs a type, and that type can be to-do, so from the to-do package, or it can be node, from the node package. But it can't be both. But we need it for both here because I want to be able to call this one single function no matter if I plan to save a node or a to-do. And that's where an interface can help us. So therefore, I will create a new interface. And you can create it anywhere you want in your code file. Here, I'll do it above the main function, right below the imports. And an interface is created with help of the type keyword. So the same type keyword we already used for creating a struct, we also use it for creating interfaces. Next, after this type keyword, you need to assign a name to your interface. And here I'll choose saver, and I'll get back to why I'm using this name in a second. And here, for the moment, we can actually use a lowercase starting character, since at the moment I only want to use it here. After this name, you add the interface keyword to tell Go that you're creating a type of type interface. Keep in mind that with structs, we used struct after this name. Now it's interface. And an interface in Go and in most programming languages that have this feature is essentially a contract, you could say. A contract that guarantees that a certain value, typically a struct, has a certain method. For example, here in this interface, I could say that I want to guarantee that whichever struct implements this interface, so whichever struct signs this contract, you could say, has a save method with an uppercase S so that we can call it anywhere. A save method which returns an error because things can go wrong. Now this might look a bit strange here because this method or function doesn't have a function body. I'm not adding a function body here because you can't in an interface. Because interfaces are not about defining the logic of a method, but instead they simply define that a certain method exists, that it's there, and what its name is, and what its return values are. In addition, an interface can also define that a method accepts certain types of values as input, as parameters. For example, let's say an int and a string. You don't need to give these inputs here names, though you can, because it's really only the types that matter here. Because this line of code and this overall interface would, for example, say that any struct that signs this contract, that adheres to this interface, must have a save method that takes an int and a string and returns an error. Now, my save method here, on to-do for example, does not take any inputs, but does return an error. Therefore, since I plan on connecting this to-do struct, just like the node struct, with this interface, I'll get rid of these parameters because my structs with their save method won't take any inputs on that save method. And that's therefore the finished interface, the finished contract, which defines which method of which shape, you could say, should exist on a certain type. Now, back to the name here, I chose saver because there is a convention in Go that if you build an interface that defines only one method, and you could have more methods, you can add as many method signatures here as you want. But if you have an interface that requires only one method, then your interface name is that method name plus ER at the end. It's not a must-do, but it is a common convention, and I'm following it here. So that's how we can create an interface. How can we now use it, though? So how can we now use such an interface? Well, an interface even though it contains no logic, is a type. That's really important, because that means that you can use it anywhere where a type is needed. For example, here in our main Go file, we can go to this save data function on which we're working and use this new saver interface as a type for data. So this here is now our interface, and that's now used as a type for data. And that simply means that we guarantee that whatever data will be, whichever concrete type of value it will be of some type that adheres to that saver interface, so that signed that saver interface contract. Whichever type we receive here for data will have signed that contract. Therefore, inside of save data, we can safely call this save method on data. And Go and the IDE won't complain here. That means that we can basically copy all our code here and paste that into save data. I just have to make sure that I'm returning an error here and that we use the := operator now, because now here in this function, that's the first time we're creating this error variable. And we should use data.save instead of user_node_save. And here, if we have an error, I want to return that error. Otherwise, if we make it past this, I'll return nil. So we got all this logic in this new save data function now. And that allows us to go back to the main function and get rid of this code here and instead simply call save data and pass our user node to save data. Now save data returns an error, so we should also handle that and check if we have an error, so if it's not nil, in which case I want to return and end the program. Now here it would have ended after this line of code anyways, so we technically don't need to do this here, but we will need to do this up here, where I can also replace this code for saving the to-do. Now here we can also call save data, but now we pass the to-do to save data. And here I then want to handle the error so that I exit out of the program without trying to save the node, if saving the to-do fails. And that's how we can use this interface. If we run this code again, I can therefore enter all this information again, and everything works as before. I'm getting no errors. Instead, my files here are updated and contain the data I entered. So this all works, but why can I actually provide to-do and user node as input values for save data? Why is Go not complaining about that? After all, I'm expecting a value of type saver here, which is my interface. So why can I pass my struct values here? We can pass to-do and user node as values to save data, which wants a value of type saver, because this interface, the saver interface, simply says that a valid value must have a save method which takes no arguments and returns an error. And unlike in other programming languages, in Go, you don't have to explicitly connect this interface to some other type to force that type to adhere to that interface. Instead, Go simply takes a look at the value you're passing to save data here, which wants such an interface type, and it takes a look at that value and simply checks if that value, that to-do struct in this case, has such a save method that fulfills the requirements of my saver interface. And that's the case, because the requirement is a save method without arguments and an error return type, and that's exactly what we have here. So Go sees that the to-do struct as well as the node struct, that both these structs have this save method and therefore correctly implement this interface. And that's why we can pass those values without any issues to save data. And that's why interfaces can be really useful, because they can help us write more generic and more flexible code, more reusable code. Because we can now use one save data function here to save the data for two different types of values. Now, if we take a look at our code here, there still is some code duplication to be found. Especially here, we are of course still calling essentially the same code for both userNode and todo. Essentially, we're calling the display method and then the save data method. And then of course we handle the potential error. So we could of course try to add another function here that could be called output data, which should call save data and also display, so that we output the data on the screen in the command line with help of display, and we output it on the file system with help of save data. For that, I still want to get some data here, and then in output data, call save data and forward that data to this save data function. But before I do that, I want to call data.display. And of course, at the moment, this doesn't work because I haven't set a type here. Now again, just as before, I don't want to set the type to todo or node because it should work for both. I also can't use the saver interface though, because that only works for the save data function, and hence this error here is gone, but it does not guarantee that there will be a display method. So of course, as a solution, we can build a new interface. Now we could name it displayer and add a display method here, which should take no arguments in this case here, and which shouldn't return any value. So it's really simple and straightforward. And now we could use this displayer interface down here. But if we do that, we get an error here regarding save data. Because of course now Go correctly sees that this data is not guaranteed to have a save method. It's not of type saver, therefore we can't pass it to save data. So in the end, we need the combination of these two interfaces. Now for that, we could build a new interface, which we name outputable. And I'm not using this ER naming convention anymore, because here I want to have a save method and this display method. And if you have more than one method in your interface, you can name this interface whatever you want, though you will often see this convention here where you try to describe the key characteristics of the type you want to enforce with this interface, so that the type should be outputable in this case. And with this new type added, we can use that down here, and voila, it works. But there is a better alternative. Instead of copy and pasting these two methods, we can instead create an embedded interface, just as we could create embedded structs. I'll use the same name, but now instead of using these methods here, I'll use the interface names, saver and displayer. And technically, since we never use the displayer interface standalone, we could also comment this out and instead embed saver and in addition add the display method. So this is also possible. You can create an interface that just embeds other interfaces as we just had it, or you create an interface that contains a method and also embeds some other interface. And again, you can add as many methods with any kind of signatures, so any kind of parameters and return values as you need to this interface. But in addition, you can also embed an existing interface. And that will simply tell Go that any value of this type, of the outputable type, must have all the methods of the saver interface, because we're embedding saver, and in addition, it also must have a display method. And therefore, we can again use outputable down here on output data to tell Go that we'll get some data that has a display method and a save method. Well, and now with that, we can of course simplify our code again. And we can, for example, simply call output data and pass our todo to output data. And to-do does implement the outputable interface because it has the save method, we saw that before, and it has a display method. We can see that here in the todo.go file. And it is a method that takes no input and returns nothing. So it meets this definition. And the same is of course the case for note. There we also have such a display method. And therefore we can of course also call output data here and pass our user node to it. Now, since save data may generate an error, I actually want to return the return value of save data here in output data. And that return value will be an error. So I'll set this as a return value on output data as well. And that of course means that we should also accept this error here and still handle it in the main function so that we can return. Though, as mentioned before here, after calling output data on user node, we don't really need to do that because the program would end thereafter anyways. So here we can just call it like this if we want to. Well, and with that, we were able to outsource a lot of code with help of interfaces. Now, also with help of embedded interfaces. Now, there is one special kind of interface, or a special kind of type in Go, which I also want to show you now that you know about interfaces. And for that, let's say that we have another function here that's simply called print something. We don't need it for this app, but I need it to explain this extra feature. And my idea here is that we use the FMT package to simply output something, some data, or some value that we receive as a parameter here. So that should be output on the screen. However, let's say here we want to accept any kind of value, not just a string, not just a number, but instead truly any kind of value. If you have a situation like this, you can use this special type here. Interface followed by an empty pair of opening and closing curly braces. This might look weird, but this is Go's any value is allowed type, which really means just that. It means that value can be of any type of your choice. And for example, the built-in println function also accepts essentially any kind of value. That's why I can forward this value to println. And that would then allow us, for example here, to call print something with 1, so with an integer, with 1.5, so with a float, and also with a string, and any other kind of value. Now, in most Go apps, you won't have too many functions that should accept any kind of value, because that can also be dangerous, because you might start accepting values which you don't actually want to handle. But sometimes you need this flexibility, and with this special interface curly braces type here, you can get it. Now, as explained in the last lecture, you can use this special type here if you want to accept any type of value. Now, sometimes you want to accept any kind of value, but you still don't want to do something for all possible kinds of values that might be arriving. And that's why Go gives you a special version of the switch statement about which you already learned earlier in the course. Because you can not just use the switch statement, as you did learn it earlier, to take a look at some variable and then execute different code for different values that may be stored in that variable. But instead, in Go, you can also take a look at the type of a value with this special syntax. So you use the dot on the received value, and then in parentheses, you have the word type. Then, like always with switch statements, you add your curly braces, and then you can define different cases for the different types you might want to handle. And here you therefore now don't specify values that could be stored in this variable, but instead you specify different value types. For example, int. And then you would add the code that should execute if you do get a value of type int. For example here, we could then use println and output integer colon value. And then we could also handle the case that it's maybe a float 64. So we could output float and then value. And then also handle the case that it's a string, in which case we maybe just want to output the value. And then we can set up a default case that will be executed for all other types. And here you could then add your fallback logic that should be executed if it is one of those other types. Or you don't specify a default clause and simply don't do anything for any other kind of value. So now, for example here, print something will output something if we got a value of type int, a value of type float 64, or a value of type string. Any other value will be accepted, but nothing will happen in here. So back in our main function, these three print statements should have an effect, since we're providing an int, a float, and a string here. But if I, for example, also try to print my to-do here with print something, I can pass it to that function, because again, any type of value is allowed, but nothing should happen for this line of code. So therefore here, if we clear this and run this, we get this output here from the first three print statements. Then I enter my text here, but then here I only got the output I always got from the display method call. I did not get any output from print something here because we're not handling this to-do type. We can pass it to print something, but nothing will happen there. But it's also worth noting that the application also didn't crash and the Go compiler didn't complain. So we can pass it, but nothing happens. So you can use switch statements to look up the type of a value and then define different cases for different types. There also is an alternative syntax you can use for looking up a value type. You can use that value for which you want to look up the type, and then use the dot on it. And this works no matter if the value is a struct or any other kind of value, because after the dot, I'm now not trying to access any field, like name. That of course would only work if this were a struct with a name field. But instead, we again use these parentheses, just as we did it here. But then we don't type between those parentheses. That indeed only works inside of a type switch statement and not outside of it, as you can tell by this error. But instead we can type a specific type name for which we're looking. For example, int. And if you do that, you will actually get back two values from accessing this special type field here, so to say. You get back the typed value, and you get back a boolean that tells you whether this is of that type you have between those parentheses or not. So OK, or whichever name you want to use here for this second value, will be true if the value is of this type you have between the parentheses, so if it's an int in this case. And typed val will be that value, but at this point here, when we store it in that separate variable, which we create after accessing this special type field, at this point, Go knows that it will be an int. So thereafter, you can work with it as an int. Keep in mind that value can be any type. So for example, if you're trying to use value to add a number to it, you will get an error because we got mismatched types. Because Go essentially complains here that value could be any type and it doesn't know if the plus operator exists for that type. If we on the other hand use typed val here, we'll just get the error that we're not using the result of this calculation, but using the plus operator is fine. And that's the case because typed val will be an int after running this check. Now it might be 0, so the null value of an int, if value turns out not to be of type int and OK holds false. So therefore you wanna check if not OK, which simply means OK holds a false value, and in that case you could do something else. Or you check if OK, so if that type check here indeed does return that value is of type int, and then in there you could safely use that typed value in the way you want to use it, because at this point you know with certainty that this will be an integer and that it's the original value that will be an integer. So then here I could, just as before, output by value, but here I could now also use typed well. Here it doesn't really matter in this specific case because println doesn't care about the type of value, but if you were in a situation where it matters, typed well will be of type int. And now we could of course use that same logic to check for the other types as well. So here I'll actually rename this to intval so that I can use different names for different types. And then we can copy this logic and also return here, so that no other code gets executed thereafter. And then I copy this logic, and thereafter I check if the value is of type float64, for example. And I'll name it floatval. And then I can output float and the float value. And thereafter we can of course also check whether it's a string. So we can check if it's a string val by using string here between those parentheses. And then here we can output string and string val. Now, of course, the switch case statement was more compact, more concise, but it's worth noting about this syntax here, also because we'll use later in the course when we build the REST API, and because it can simply be very useful if you have a situation where you're getting a value that could be of any type and where you're then maybe looking for a very specific type and you want to execute a very specific action for that type. So that's therefore a syntax you should know. Now, interfaces can be very useful in Go. And especially this special interface type that stands for any value can be very useful in certain situations since it allows you to write quite flexible code. But it also has some limitations. And here's an example. Let's say you want to create an add function which should take two input values and return the sum of both. But now here's the special thing. These two values should not be of a fixed type like int or float64. Instead, they should be either an int or a float64 or also a string. So that we either combine two strings or we add two ints or we add two floats. Now, of course, you could now use this special interface type here so that Go accepts any kind of value here as an input. But as you see, I'm getting an error here now, that this plus operator is not defined on such a dynamic value type, because not all values support the plus operator. You can't, for example, add two structs together. So this is a bit too flexible. Now you could make it work by using this special syntax here, where this special syntax is used to check whether a is of type int, and if it is, a is int will hold true and will get a value which we can store in a variable where Go now knows that it will be of type int. And you could do that for both a and b, and then in this if check add them together. Now Go would know that both are of type int, and now its only complaint is that we return too many values because at the moment I haven't set up any return value. But we could work around that by setting the return value to int, of course. However, that's a bit too restrictive because, as I mentioned before, your goal might be that you want to accept more than just ints. So you could copy that and also check if it's a float, so that you extract those values and you check for that here by using float 64 here, like this. And then down here we would check if A is float and B is float, and in that case we would combine A as a float and B as a float. But now, of course, the problem is that the return type, as mentioned, is too restrictive, and therefore we could use this any return type here, so that any value is allowed. That then also would allow us to repeat this process to check whether A is a string, and do the same for B by using string here. And then here also by checking if A and B are strings, and by then using their string versions for combining them. And then past this if check, if we got any other value, we could return nil, for example. So we could do that, but of course that's a lot of code to write, as you can tell. And that's why Go offers another feature. It offers a concept called generics, and we'll take a closer look at that concept in the next lecture. This generics concept, which I'll show you now, will help you solve problems like this. Because the problem we have here in the end is that this type is a bit too wide. Accepting any kind of value is a bit too wide. And in addition, another problem we have here is that the return type also is too unspecific. Therefore, if I call add and I pass two integers to it, Go doesn't understand that result will be an integer. Instead, it thinks it's any kind of value. Therefore, thereafter, working with that result will be rather difficult. Because, for example, if I add 1 to it, Go complains that the types are not the same. So, of course, it would be great if Go would understand that the return value of add will be an integer if the two values we pass to add are an integer. And that's also a kind of problem that will be solved by turning this add function into a generic add function. Which we do in Go by adding square brackets after the function name before this parameter list. And between those square brackets, you can define a type placeholder name. Typically that's T, but you can use any name of your choice. The idea is that it's now this placeholder that is used here instead of this interface type, for example. And you can also use this placeholder here as a return type. But at the moment I'm still getting an error here, because we must tell Go which concrete types are allowed as types for that placeholder when add is being called. And here you can, for example, use this interface type here again, or the shorter form any, which simply means T can be any kind of value. Now, as you see, when doing that here, I'm getting a bunch of errors, but I will deal with them later. What's more important than that is that by making this simple change, if you now hover over result, Go understands that it will be of type int. And it understands this because what we're doing with this generic type placeholder is that we're telling Go that the concrete type of values we're receiving here and we're returning will only be set and known at the point of time where add is called. So in this line of code here, line 4 in my case. It's then here where Go sees that two int values are passed in, so it correctly infers that the concrete type that's being used here must be int, because I'm passing in two int values. Since I'm using exactly the same placeholder here for the return type, it therefore also knows that the return type must be int. And you could set up multiple types here separated by a comma, if you would need multiple placeholders and you, for example, would need a different return value type. But that's not the case here. I'm fine with one type. And that's why this generics feature exists and why it can sometimes, in certain situations, be really useful. Because it allows you to write more reusable, more generic functions where Go nonetheless is able to correctly infer the types of values you're working with. And therefore this code here now doesn't work anymore because it isn't needed anymore. When writing this in a generic way, we can simply return A plus B. At least we can almost do that. I'll get back to it in a second. And we don't need any other checks. However, we'll still have one problem if we do it like this. Since we're saying that the concrete type that's used at the point of time where add is being called can be any type, we're of course back to this error that the plus operator is not necessarily defined for all possible types. But we can work around that by setting the base type or the range of allowed types for T not to any, but instead to a list of predefined types with which we're fine. By simply listing all those types separated with such a pipe symbol. Like this. With that I'm saying that T can be any type as long as it's an int, a float, or a string. And therefore now this all works, and the only complaint is that I'm not using result. But of course we can change this by simply outputting it here, like this. And this code now therefore works and is written in a very generic way by using this generics feature. Now it's worth noting that you might not need this feature here too often, because if you're writing your own programs, you don't often need code that is that generic. But especially if you're working on a library that should be shared with other people, where you don't necessarily know in advance with which kinds of values they might be using your functions, especially in cases like this generics feature here can be really useful. Now in this course, at this point, we did already learn about the struct type. A type that allows you to bundle different pieces of data together into one value. In this section, we'll take a look at a couple of other types that are built into Go that can also help you group related data together. And you will of course also see and learn in this section when you might want to use these types, about which you will learn in this section, and when you might prefer a struct. And therefore, in this section, you will learn about arrays and what arrays are and what their limitations are. You will learn about another Go feature related to arrays called slices and how that works. And we'll indeed take a pretty deep dive into slices and how you can work with them throughout this section. And last but not least, we'll also explore maps, another data type built into Go. And all these data types, as mentioned, can help you with organizing data and with grouping data together. And therefore, let's not waste any time. Let's instead take a look at these value types. Now, as in every course section, I got a brand new project, just created a Go module with the go mod init command. And I want to start with lists of data, with managing lists of data and what I mean with that. And for that, I'll add a lists.go file. And in there, as always, I'll add my main package and then also my main function, because we'll still need that. Now, what do I mean when I say lists of data? Well, let's start in a different way. We did learn about that struct, where we maybe have a product, and hence we have our struct, and in there we then have a title for the product, and maybe an ID, and maybe a price, which is a float. That's what we saw before in the course. The struct concept or feature is a very useful feature because it allows you as a developer to group data together. We group a title, an ID, and a price together into one data package. And organizing data like this is super important because very often in your programs you have more complex pieces of data that you want to express. But in a nutshell, a struct is a data grouping mechanism. And we do group different kinds of data into one piece of data. A title, an ID, and a price are very different data pieces that are grouped together into one data piece. That's how you can think about a struct. Now, in some programs, actually, as it turns out, in a lot of programs, you don't just need such kinds of data groups, but sometimes you also have similar pieces of data that need to be grouped together. And that might sound very abstract, so let me give you an example. What if we would be building a Go application that's dealing with some data analysis? And therefore, as part of this application, we might get various values. For example, some weather data, maybe some product prices, which we want to analyze. Doesn't matter. We get different pieces of data. Let's say different numbers. Now, they all express the same thing. For example, if we get temperature values, every number might express a temperature in Celsius or Fahrenheit. But we, of course, have different values. Now, if we work with such kind of data, where we have many values that describe the same thing but have different values, then a struct won't help us. We could, of course, create some struct temperature data like that, and in there have the temperature of day 1, which holds, let's say, a float. And then we have day 2, which holds a float. But doing it like this, solving this problem like this, would be very annoying. Because we have to know in advance how many days of data we want to have. And even if we do know that, we have to do a lot of typing to describe all those days, to set up all these day keys. So that's very annoying. It would lead to a lot of code and to code that's quite unreadable. And working with that kind of data would then also be a bit annoying throughout the application. That's why for such cases where we describe the same thing and we just have different values, we have a different kind of data structure built into Go. And we have this kind of data structure in basically every programming language out there. It's just a name that's different between all those languages. We have a so-called array. In Python, it would be called a list. In JavaScript, it's also called an array. And an array is a data structure that holds values, potentially different values, that kind of describe the same thing. Now let me show you how we create such an array. For that, I'll create a brand new variable that will hold my array. And let's say we want to work with a bunch of prices here. But of course, it's up to you. Here, I'll just go with some prices. And let's say that should in the end be a list of floating point values. So a list of floating point numbers that we want to store in this prices variable. Now, since it's a brand new variable, we'll use the := operator to create it and set a value immediately. And now we can turn this into an array by using a special syntax. We want to have a list of floating point values, as I said. So I'll type float 32 or 64, doesn't matter. And then in front of that, we add square brackets. This is an important piece of syntax that tells Go that we don't want to create a single floating point value that should be stored in prices, but instead a list of floating point numbers. Now, between those square brackets, we then have to tell Go how many values we want to store. And let's say that's 4. So we want to store 4 floating point values in a list of floating point values inside of prices. Now, it's still not all. When using this syntax here and immediately assigning a concrete value to prices, which is what we do with this operator, we also have to let Go know which values should be stored in this array. And for that, we add opening and closing curly braces here. Now here, between those curly braces, we can now enter the values that should be stored in this list. So something like 10.99, 9.99, 40, 5.99, and let's say 20.00, or just .0. This now creates an array, a list of 4 numbers, 4 floats that's stored in prices. And you can create arrays based on any kinds of values, not just floats. You can create an array of strings, of integers, even arrays of structs and other arrays, so-called nested arrays, are possible. But let's start simple. Let's take a look at what we created here by using the format package and calling the println function, to which I then pass prices. And now we're not using this struct anywhere, so therefore I'll get rid of that since it was only there for demo purposes anyways. Now with that array created, if we open that terminal here, if we run our module, we get that list of data output here. And that's how we can create such a list of data. And the key difference compared to a struct really is that all these values describe the same thing, a price. But of course we describe different prices, and hence we have a list of these different values that describe the same thing. And that's a fundamentally different idea than we had it with a struct. And different scenarios and use cases in your code simply require different solutions. Now let's take a closer look at this array thing and what we can do with it and how we can create it. Because here we only see one way of creating an array. We can also create an array by using the var keyword and then giving the variable any name of our choice. Let's say we have a couple of product names, so I'll choose product names here. And now I don't want to initialize it immediately, I just want to declare this variable and make it clear that it should contain an array as a value. So it's not a string, which would be a single value, but instead an array of strings. Same syntax as down there. Square brackets in front of the type of value that should be stored in that array. Now, when creating such an array, you also typically want to set a length for that array so that it's not an empty array which has no items at all. And you do that by adding that length, so the number of items that should be stored in that array between the square brackets. So we could use 4 again or 3. It really depends on how many items we want to store. Let's go with 4 here. With that, I'm creating this array, and if we now print that without assigning any values, if I print my product names like that, and we then open that terminal again, if we run our code, we see this. It's very important to note that the program doesn't crash or anything like that. Instead, the null value that's now set for product names is now simply an array with 4 empty slots. And that's what this in the end represents. Now, of course, we could set product names equal to an array now by, again, let's say creating an array like that. And then we could pick different names like a book and so on. And you also don't have to set all the names. If I just set one name and I run this program again, you see one name is set and the other slots are still left empty, so that's possible. But you also sometimes have the scenario that you want to set specific values. Let's say the second value in an array. Or you want to read a specific value instead of outputting the entire array. And therefore, that's another key mechanism that you need to know as a Go developer. How you can target individual values in an array so that you don't always have to set or read the entire array as we're currently doing it. Now for that, first of all, to get rid of those yellow squiggly lines, I'll merge this into one line here, like that. And then I want to show you that syntax for accessing individual items. Let's say we want to print the third price in the prices array. So here I want to print prices, but not the entire list, but just the third value. For that, we got a special notation that allows us to access a specific value in an array. We again use square brackets, but now not to create a new array, but instead after a variable name that holds an array to tell Go which specific item we want to access. For a struct, we used the dot notation, but for arrays, that's not available because arrays are not structs. Instead, for arrays, we use square brackets. And now we also don't have key names for those different values. I mean, where would those key names be? But instead, all those values have unique index values, which are automatically assigned. And the logic here is very simple. The index values always start at 0 for the first element. And that can be a gotcha. It's not 1 for the first element, but 0. So if you want to output the first element, you would write prices and then 0 between square brackets. So if you want to output the third element, we need which value here? 2, because we have 0, 1, 2. This has an index of 2. So that's how we get access to the third element. And that's just something to keep in mind. Thankfully, it's the same in most other programming languages that arrays or lists, or however that feature might be called there, start at index 0. So with that, if we save this and open our terminal, if we now run this program again, we see that 45.99 is being output. And that is how we can create arrays and how we can read single values from arrays. We can, of course, now also set single values. For example, if you want to set, let's say, the third product name, we did set the first one thus far. The other slots are left out empty. If we want to set the third one, we can set product names and then again target the third element, which still has an index of 2, and set this to a specific value, like a carpet. Now, on product names, we'll have the first value being set and the third value being set, and the second and fourth values will still be empty. But that's fine, that is something you can do. With that in place, if we run this program again, we output a book, then our empty blank slot, then a carpet, and then another blank slot in this array. That's how that works, and that's how you can work with arrays. But that's far from everything that you need to know about arrays and that you can do with arrays. Arrays are extremely important and useful, and that's why we have more features related to arrays that also are important to understand. Specifically, we have the slice feature. That's a key feature of Go and a feature you'll use a lot. Now, what's a slice? Here we have two arrays, product names and prices. Now, thus far, we learned how we can work with the full array, for example, to output the entire array, or how we can target individual values, like we do it here. Sometimes you also need a subset of an array, so a part of that array, more than one value, but not the entire array. And that's where a slice comes in. Down there, I want to create a slice of my prices. Let's say we want to fetch these two prices, $9.99 and $45.99. So we want to create kind of a new array based on this array that omits the first and last values. That's what a slice can do for us. So let's say our featured prices should be that slice. So that's a brand new variable, which I'll therefore create with the colon equals an operator. And we now can create a slice, so create the value for featured prices based on this prices array, by referring to that prices array, and then again using that square bracket notation. But now instead of targeting a single value, like the second or third value, we can now also use a slightly different notation. We can type 1:3. And that creates a slice from that target array. Which means we'll take a look at that array, and then we'll start at the element with index 1, which as we learned is the second element. And then we take all the elements up to the element with index 3, excluding that element though. So the first value is always included, the second value is excluded. So this notation would start at the element with index 1 and then would go all the way up to the element with index 3, which in this case is 20. That will have an index 3 since it's the fourth item, but will not include that item but exclude it. So that will create a brand new array, though it's technically called a slice, that will only contain these two values in the middle. So if we now again output that, if we print line featured prices, if we run this program, we see this slice being output here. And of course, that is just that middle part of our original array. And slices therefore are another core feature, since in a lot of applications you do need to work with parts of lists. And slices allow you to easily create brand new lists based on other lists of data. Now, slices are extremely useful and versatile, and there is way more you can do with slices, and you should know about slices. For example, regarding that syntax here. We learned that we can start at some index and end at some index, excluding the value at that index. But you can, for example, also omit the starting index and just write colon and then the end index. If we do this and we run our program, then you'll see that what we get is this kind of list. So it's almost the entire original array, just the last value, the 20, is missing. And the reason for that is that this notation tells Go to start at the beginning of the array or slice which we are targeting, and then go all the way up to some element with some index. You can also do the opposite and maybe start at the element with index 1, so not the first element, but the second element as we learned, and then go all the way to the end of the array or slice which we are targeting. If we would run this code here, we get the end of that original array. We get this part here. So these are things we can do. What you can't do here, and what you can do in some other programming languages, is use negative indexes. So you can't start at the last element with a minus or something like that. That works in some other programming languages. It doesn't work here. What you also can't do is pick a higher end index than the original array has. We already get an error here that it's out of bounds. So the highest value you can select here really is the end index plus 1. Plus 1 because the last element by default is excluded. So to give you a way of targeting that last element as well, Go allows you to pick the index of the last element, which would be 3. The last element here has an index of 3, and add 1 to it. That's the highest bound you can use in a slice. But of course, if your goal would be to select everything up to the end, you can do it like this, but you can also just omit it, as I just explained a couple of seconds ago. So that's how you can slice and select different parts of arrays or slices. Now, I actually already mentioned it before, but I haven't shown it to you yet. Slices can be used on arrays, but slices actually also can be created based on other slices. So if we have our prices here and we start at the second element and then go all the way to the end, then we can create yet another slice, the, let's say, highlighted prices, where we just use featured prices, which already is a slice itself. And here we now just want to go all the way up to the third element, or the second element, let's say. And then here I want to output highlighted prices. That's also something we can do in Go. And if we do that and we run this program, that's what we get, 9.99. Now, why do we get 9.99? Because here we select the second element all the way up to the end of the prices array. So we select this part here. That's what we select here with line 16. In line 17, we then take this selection and we select everything from the start of that list all the way up to the second element, excluding that element. And that's then only 9.99. That's how we end up with that result you just saw in the terminal. So being able to build slices on other slices is another useful feature in Go. Now we get started with slices and arrays. Time for a brief look behind the scenes to fully understand the connection between slices and arrays. Slices are like a reference, like a window into an array, a bit like a pointer, though it's a different concept. When we create an array like prices, that array is stored in memory. When we then create a slice based on that array, we get a window into that array, so to say. And therefore, if we would modify an element in a slice, we would also modify the same element in the original array. So for example here, if I use my featured prices slice, which again is this part of the original array, and I added the first item of that slice, which is 9.99, because we start at the second element here when we select that slice, which is 9.99. So the first element of that slice then is that 9.99 value. If I added this and set it to 199.99, then indeed what you'll see is that when we output the prices array, so the original array, which I did not directly edit here, we will still see that 9.99 will have been overwritten by 199.99. So if I run this program, indeed we see that the original array has its second value overwritten by this value, because a slice is just that window into the original array. And that also has one important implication. When you create a slice, you don't copy the original array. So you don't have that copy in memory that occupies extra memory space. Instead, you still only have one array in memory, and your slice is just a tiny reference to a part of that array. And hence, it's a very memory efficient way of selecting parts of arrays, and if you want to do that, of editing parts of an array. Now, Go also saves some metadata for our slices that can be useful to look into. For every slice, we got a length and a capacity. And we can output both here to understand what it is. I'll start with the length. The length of featured prices can be output by using the built-in len function, which is built into Go just like that. You don't need to import any package for that. It's a default Go function. You can also call it on other value types, as you see here in the tooltip, for example on arrays and also on strings, but here we'll just call it on the featured prices slice. And then I want to output a second value, which we get by calling the built-in cap function, which just like len is built into Go. To cap, I'll also pass my featured prices, and that will give us the capacity. Now here, if I run my code, we'll get the same value twice. We'll get free twice for both the length and the capacity. But what are these two values? The length gives us the number of items in a slice or array. So if that slice, featured prices, has 3 elements, which it does, length will give us 3 as a value. The capacity is a bit more complex. It's the same value here, but that would be different if we would output highlighted prices. If we output the length and capacity of highlighted prices, then we'll see a difference. So if we use that other slice we got here. Here, if we output that, we get 1 and 3 as values. Now, why is that? Highlighted prices is based on featured prices, which in turn is based on the prices array. So they share the same array under the hood. But highlighted prices selects everything from the start of featured prices up to the second element of featured prices, excluding that element. That's why we have a length of 1. There is only one element which is part of that highlighted prices slice. But we have a higher capacity because the slice, and therefore the original array on which highlighted prices is based, actually has more items left. In featured prices, where we selected everything from the second item until the end of the original array, we still have this entire subset left. So if in highlighted prices we then select just the first item, we could theoretically still select the other 2 items, and that's why we overall have a capacity of 3. Why not a capacity of 4, since the original array has a length of 4? Well, because, and that's important to understand about slices, you can always select more towards the end of an array, but not towards the start, so towards the left. Since the first slice on which we are based starts at the second element and not at the first element, any other slices based on it can't go further to the left. So we can't go back to that first element which we omit here. That's why the capacity only counts towards the end of the original array, but omits any elements that might have been filtered out before. Can be a bit complex to wrap your head around, but is something you can simply play around with in code as well to get a feeling for it. In the end, it's just important to understand that you can always select more items to the right, but never to the left. And to show you what this means, I'll change highlighted prices. Here, after outputting all of that, I'll use highlighted prices, which is based on featured prices, and I'll set it equal to highlighted prices, so not featured prices, but highlighted prices, and then select a specific index like 3 here. And now, if I repeat this code here, without outputting prices again though, you will see that if you now run this code again, you get that entire featured prices slice. And now the length matches the capacity. Now that is a quite interesting behavior because I did now reslice highlighted prices based on the previous highlighted prices slice. It might have been clear that this works if I would have used featured prices here. But I did not do that. I used highlighted prices here. And highlighted prices before in this code block was just one value, because we sliced it to be only up to the second value. That's what I meant with you can always select more towards the end of an array or slice. Even though highlighted prices originally only had one element, we can reslice based on that one element slice and now suddenly select more than that one element because internally Go always memorized that there is more content available to the right of the selected slice. And that's what this capacity here kind of told us, where we had a difference between capacity and length. There were more elements available and Go memorized that. That's why on this one element slice, we still are able to reslice to pick up more elements, but only to the right, not to the left. There is no way of getting access to this original first value in that prices array. That's gone forever since we started by creating a slice that omitted that value. And that's a lot of deep dive theoretical stuff. I'm fully aware of that. These are just some gotchas and interesting quirks for that slices feature that you should at least have heard about. Because sometimes when you write your own code or you dive into other Go projects, you might suddenly see code snippets like this, where we suddenly select more than was previously stored in a slice, and you might wonder why that works. Well, it works because if you select more to the end of an array, you can't always do that because Go memorizes that original array. But as a special quirk, it kind of only does that for more values to the right of the existing slice, not to the left. So that was a lot of deep dive stuff on slices, and you won't need all of that all the time, but as I mentioned, you should have at least heard about it. Now, slices are not just a useful feature because you can make other people dizzy by diving into slices on slices and stuff like that, but also because with slices you can create dynamic arrays. Because let's come back to that original prices array. One downside of using that array was that we had to define ahead of time how many values we'll have in there. Now, sometimes in the applications you're going to write, you know exactly how many values you'll have in a list of values. For example, if you handle some user input in a form that has exactly 3 form fields, you might have an easy time storing those 3 values in an array because you know ahead of time that you'll get 3 values. But let's say you're loading a list of prices from a database, and the data in that database changes frequently. Then when you write your code, you don't know ahead of time whether you'll need 4 or 5 or 100 prices. So having to set the length of an array in advance in your code can be a restriction that's quite annoying. In other programming languages like JavaScript, you don't have that restriction. There you can create an array and it's automatically dynamic, so you can always add and remove elements just as you want to. For Go arrays, that's not the case. Prices is an array with 4 elements, and you can't just add a 5th element, even if you wanted to do that. Now, since we have that restriction, Go thankfully also has a solution for us, and that solution again is that slices feature. Now, I'll comment out this main function because I want to keep it here for reference, but I don't want to execute it anymore. Instead, I'll write a brand new main function so that we have an empty, cleaned up main function to dive into that slices for dynamic arrays feature. Let's say we again have some prices, but this time it should be a dynamic array where we can add more values whenever we need to. You can create such a dynamic slice with a syntax that's similar to what we saw before, so square bracket, float 64, curly braces, but you may now also omit the length here. If you don't specify the number of items that should be stored in this array between those square brackets, Go will actually automatically create a slice for you, and since a slice always is based on an array, it will also create an array for you behind the scenes, but it will automatically ditch that array and create a new array if your slice grows beyond the bounds of that behind the scenes stored array. But we'll see that in a second. So here we can create an empty slice like this, or maybe even populate it with some starting values. Both is possible. Now we can still work with that as before. We can build slices based on this slice. We can select individual elements. So for example here, I can print prices 1. And if we run that code, unsurprisingly, hopefully, we see $8.99. Now we can also select a slice here if we want to, like this. And if we execute that, we see $10.99. So that's still possible. That all works. Now we can, of course, also assign values like this to override the second value. But what we can't do is assign values to indexes that are not part of the slice. If we would try to do that and we then output prices thereafter, it crashes because the index is out of range. I don't get this error in the IDE, but I get it when I try to execute that code. So we still can't access indexes that don't exist. But I told you that this would be dynamic, right? But not like this. Instead, there now is a built-in function in Go, the append function, which you can execute like that, which, as you see here in the tooltip, wants a slice as a first value, and then a list of elements that should be added to that slice. So here we could refer to prices, which is a slice, as I mentioned. This syntax creates a slice, and Go creates the array that belongs to the slice behind the scenes. And now we can, for example, add 599. And that will now append a new item, but it will actually also return a brand new slice. So it actually does not edit the original slice, but instead what append does is it tells Go that we want to add an item to that slice, and therefore also to the underlying array. Now, of course, an array has a fixed length. So what Go will do in this case is it will create a brand new array and add that element to that brand new array, which is created such that it has the capacity for that new array. So here I got my updated prices, and I can now print my updated prices here if I want to. With that, if we now run this program, we see that we got our updated prices here, which is the original prices, slice, and therefore array, plus the 599. Now, if I would print prices here, as well as updated prices, so if I print the original slice and this new slice, you see that the original slice did not change. This is still just these two values, just 9.99 instead of 8.99, because we overwrite this here. But the original slice in array was not changed by Go. If you wanted to do that, you would have to instead reassign this appended slice to the existing prices slice, instead of creating a new variable. Then, of course, if you do this and you output this prices slice, then you'll see that it changed. And again, Go will manage the arrays for you behind the scenes. And if you reassign an appended slice to an existing slice, it will of course also ditch that original array, which only had 2 elements before, and use that brand new array that holds that extra 3rd element for that slice instead. So memory management is taken care of by Go here. And since we now have that extra flexibility where we can always add new elements if we need to, it's way more common to work with slices right from the start in Go than it is to use arrays. You can still use fixed length arrays if you know for sure that you will never have more than X amounts of elements in a list. But if there is at least a slight chance that you might want to add new elements as your program executes, you should definitely go for this slices approach right from the start instead. Because that allows you to add elements to slices and to let your arrays grow just as they need to. Now, in case you're wondering whether there also is a function to remove elements from a slice, since there is an append function, well, yes, kind of. We can, of course, just create a new slice that removes the element we want to remove. If we want to remove the first element, we simply create a new slice based on the existing slice that starts at the second element and selects everything up to the end. That gives us a brand new slice that omits that first element. So with that, we of course did remove that first element, which was 1099. So that works like this. There is no function for doing that since we already have the built-in mechanism with that feature that allows us to build slices, this slicing syntax here. Working with arrays and slices is actually not that difficult, but we did learn a bunch of very important concepts over the last minutes. And hence it's time to practice what we learned. Attached you find this practice.go file, which contains a pretty empty, Go code file, just with the main function and main package, but which also contains a lot of instructions that allow you to practice what you learned. And as always, you can then go through my solution lecture to compare your solution to mine and see how I solved this. Now, in this exercise here, I want you to start by creating a new array, very important, an array, not a slice, that contains 3 hobbies that you have, any hobbies of your choice. So create such an array with an appropriate length and value types being stored in there, and then output that array in the command line. In task number 2, you should also print the first element and just that element, and then also the second and third element combined as a new list. So you should also output these pieces of information. In task number 3, I then want you to create a slice based on the first element of that array that contains the first and second elements. So start at that first element, but make sure you also contain the second element. Now, very important, I want you to create that slice in 2 different ways. So in the end, you should create 2 slices, though you can comment out one of the 2 approaches so that you're left with 1 new slice in the end. But create it in 2 different ways, because there are different ways of selecting the start or the first element of an array and so on. Also output that new slice once you're done. In task number 4, I then want you to reslice that slice from task number 3 and change it such that it contains the second and last element of the original array. So don't create a slice based on the original array itself, but create a new slice on that existing slice which you got from task number 3, but change it such that it's the second and last element instead of the first and the second element which it was before. And then also print that updated slice. Now in task number 5, you should create a brand new array, but a dynamic array, and therefore it's maybe not really an array. You learned what you'll need. And that should be a dynamic array that contains your goals that you have for this course. You should at least add 2 goals into that dynamic array right from the start. Also output that array thereafter then. In task number 6, I want you to overwrite the second goal in that array which you created in task number 5 and set it to a different goal, and also add a brand new third goal to that dynamic array. So that's what you should do in task number 6, and then output that updated dynamic array. And then I got a bonus task for you. A bonus because you'll need to do something which we haven't done before. I want you to create a product struct. This is something we did before, which has a title ID and price. And then you should use this struct to create a dynamic array, a dynamic list of such products, at least 2 products. And then I want you to add a third product to this existing list of products. Again, that is something we haven't done before, so maybe you find a way of achieving this. Otherwise, I'll show you how that works in my solution. Let's now solve these tasks together. And let's of course start with task number 1. In task number 1, we want to create a new array that contains 3 hobbies. So I'll create that array, and we get various ways of doing that with the var keyword and this slightly more longer syntax, or we use the very concise syntax where I create a hobbies variable and we use the := operator to then create that array. Now here for task number 1, we need a real array. No slice, but a real array as I highlight here, and therefore we wanna define the length of that array. So the number of items that will be stored in it in advance. We also need to define the value type in advance. That's the case both for dynamic arrays, slices, and real arrays. And here, since I want to store some hobbies, so some text in the end, string sounds like a fitting name. And then you learned we need the square brackets in front of that. And since we'll have free hobbies, I'll add a free here. And then curly braces like that. Now we can set our different hobbies by accessing the different indexes and setting it like this. Or we set it all in one go and have something like sports, cooking, and reading as hobbies here maybe. And then of course we don't need a deadline unless we want to overwrite the first element. Now we created that array and we want to output that array, so with help of the format package and the printline function, we can now print hobbies. And that should be task number 1. Now to see it in action, I'll run this module. So now we see sports, cooking, and reading here. This is working. In task number 2, we now want to output more data from that array. The first element standalone, and then the second and third element combined as a new list. So for that here, task number 2 involves some printing. But now I want to access the first element. And you saw the syntax a couple of seconds ago actually. We can access specific elements in an array to read or set them by using square brackets after the variable name that contains the array. And then we use the index of the element that we want to read or write to. Now the index, that's the important thing, starts at 0. So if we want to read the first element, we don't use 1, but we use 0 instead. And this will now output the first element. Now that's not all though. We should also output the second and third element combined, and for that we'll need a slice, because we learned that with a slice we can select a subset of an array and then work with that. So if we want to select the second and third element, then we want to start at the element with index 1, which is the second element, and then select everything up to another index. That index will be excluded though. So if I would write 1:2, we would not select the second and third element, which you might think, since we have the indexes 1 for the second and the index 2 for the third elements. But instead, since that element will be excluded, we would just select the first element. Instead, we need free here, so the index of the last element plus 1 to select that last element and include it in that slice. Or we use the shortcut and just type 1:nothing to select everything up until the end of that array. Now here I'll go for the more explicit syntax, but either of the two approaches is fine. And with that, just to quickly check that, if we run this, we now see sports, which is that first element for line 11, and then cooking and reading, which are the last two elements, so the second and third element for this line of code here. So that's also working. In task number 3, we should now create a slice, another slice, based on the first element, so based on that first array actually that we have here, that contains the first and second elements, instead of the second and third elements which we have here. So in task number 3, I'll add a brand new slice and now also store it in a variable, and I'll name it main hobbies maybe, create a brand new variable, and then use my hobbies array and create a new slice. Now to select the first and second elements, I want to start at the index 0 and then select everything up to index 2, since that will select everything up to the element with index 2, which is the third element, which is then excluded, so it will select the first and second element successfully. Alternatively, here we omit the 0 to start at the beginning of that array on which this slice is based, and then just go up to the third element and exclude that element. Either way, we'll select the first and second element. And with that, I also show you two approaches of making that selection. And then we also want to print that so that we don't get an error, and print main hobbies here. And now if I zoom out a bit so that we have more code on the screen, if I run this code again, we do get sports and cooking here, which indeed are my first two elements. So that is also working just as it should. Now, task number 4 wants us to reslice free and change it such that we contain the second and last element now, instead of the first and the second element. Now that works because behind the scenes, a slice actually just points at a part of an array, and we can always select more from that array as long as we expand our selection towards the end of the array. Towards the beginning, that's not possible. And as a in-between step, we can actually again print the capacity with the cap function of main hobbies. And what we'll see when I do that, and I run this code, is that that capacity is free even though main hobbies only contains 2 elements. It's free because the array on which it's based actually has 1 extra element after that last element that we select here when we build that slice. And again, as I mentioned, extending the selection towards the end after we already have a slice is always possible. So we can reassign a value to main hobbies. Hence, I'm not creating a new variable here. I'm using an existing one. And I actually reassign based on my existing main hobbies slice. And we want to create a slice that gives us the second and last element. Now we are basing this new slice on the existing slice. The existing slice contains the first and second element, but because we have that link to the behind the scenes array and extending towards the end is always possible, we can also expand this slice to get the last element of the existing array. Now I'm not interested in the first element anymore, and therefore I'll start at index 1 to omit that first element, which was still part of that slice before, because we included the first element here when we originally created that slice. Now I want to go all the way to the end, and you could therefore think that you can just use this shortcut, but that would actually not work. If you save it like this, and you then actually print main hobbies like that, if you give this code a try, you'll see that it actually just outputs cooking. So the last element, reading, is not included. The reason for this is that I'm building my new main hobbies slice on the existing slice. And the existing slice does not include the last element here because we only selected up to the last element. So only the first 2 elements. But I mentioned that expanding would be possible, and it is, but if you do expand a slice in the process of reslicing, then you explicitly need to specify the end index. If you leave it open like this, it will use the last value from the existing slice instead. If on the other hand I set this to free, as we did it here in line 12 as well, then we explicitly tell Go that we want to go to the underlying array and give us the element prior to index 3, which is this element which has index 2, and include that in the slice. Can be a bit of a gotcha, but this is how we can now extend our selection here. With this, if we now run this code, we got cooking and reading included. So the second and third element with that reslicing approach. Now in task number 5, we now want to leave that array we worked on thus far and instead create a brand new array that has one special trait. It should be dynamic. So we should be able to add new values to it. And therefore, here I'll add my solution for task number 5. And since it's an array that will contain a bunch of course goals, I will name it course goals. That's my variable name. And to create a dynamic array, we need to create a slice right from the start and let Go create the underlying array behind the scenes for us. The syntax for that is very similar to what we had up there. The only difference is that we don't specify a length ahead of time. The syntax we need here is that we still want to store strings because our goals are still pieces of text. And we still need the square brackets, but we don't give this a fixed length. Instead, we leave the square brackets empty and then add our curly braces to either create this as an empty slice at the beginning or to already store a couple of values. And since we should create at least 2 goals here, I'll start by setting 2 goals, which are learn Go and learn all the basics, something like that. These are my course goals. And that's already task number 5. Now we can also print this to see whether that worked, and hence print course goals. Go run this, and we see our course goals here. So that is working. In task number 6, we now want to change that dynamic array, and we want to set the second goal to a different one and also add a brand new third goal. Now let's start by setting that second goal. For this, in task number 6, I'll first of all access the second goal in course goals by its index with this square bracket notation, and the index here is 1 for the second goal. And we can change this to learn all the details, something like that. Now we should also add a brand new third goal. And for this, we can set course goals equal to the result of calling append. And append, as you learned, is a built-in function that operates on slices and allows us to add brand new values to slices. And here I want to append 2 course goals and append a brand new third goal, which is learn all the basics again, maybe. So we overrode learn all the basics with learn all the details, and then we add learn all the basics again as a third element. And now with that, if we print our course goals here after changing those goals, if we run that code, indeed, we now see we have learn Go, then as a second goal, learn all the details, since we changed that here, and then as a brand new third goal, learn all the basics. And as explained, behind the scenes, Go did create a brand new array for us, basically ditch the old one, and bind this slice to that new array. That all happens behind the scenes for us. We don't have to worry about it. Now in task number 7, I now got a bonus task here that involves a struct, a product struct. And therefore we first of all need to define this struct. So maybe here, right at the beginning of the file, I'll define my product struct as we learned it, give it an ID, which is maybe a string, a title, which might be a string, and then a price, which could be a float. Now we got the product struct. Now I want to create a dynamic array based on that struct. I want to create a dynamic list of products that contains at least 2 products right from the start. And then we want to add a third product to that existing list of products. That might sound overwhelming, but thankfully it's actually not difficult. Here for task number 7, I'll add my products variable. And here I want to contain a dynamic array. So we need a slice. So we need empty square brackets. Then the data type is not string or float or int, but it's product. And I mentioned this before already. You can create arrays that contain structs or even other arrays. You are not limited to the primitive value types of numbers and strings. Storing structs in arrays is absolutely fine, and that's what we'll do here. So this syntax now creates a slice, a dynamic array that contains products. And we can now initialize it with some product data by using the struct literal notation here to add brand new products with an ID of first product maybe. keeping the order defined here when I set up the struct. Alternatively, we can assign values by using the keys again, but here I'll just keep the order, add a comma, and add a first product as a name here, as a title, and then as a price $12.99. Since this can get a bit tricky to read here, we are also allowed to split this across multiple lines as long as we add a comma here at the end, and then even split the struct creation into multiple lines, and also add a comma here in line 44. And now if I reformat this, this is more readable. Now that's one product. We can now copy that and add a second one. So the second product, where I say a second product, and this has a price of $129.99. And that's now my products list, my dynamic list full of product struct instances. Of course, we could have also created those instances in variables ahead of time and then just added those variables into that list, or we do it like we do it here, all in one go, just in time. Either way is fine. And now, of course, we can again print our products like that. Now, when I save that, you'll note that I have some yellow squiggly lines here that tell me that I have some redundant type here. Now, it turns out, and that is something you can't know, but it turns out that when you create such struct literals inside of such an array, which already is defined to only contain these kinds of structs, you can omit the struct name here and just create the structs like that. Since Go already knows with certainty that this list will only contain products, because you clearly define it here. So then you don't need to repeat that type name here when you create the struct instances, even though you are allowed to do it. But it's redundant, so you can shorten the code to look like this. And now with that, we're creating that list of products, we're outputting it, and hence if I run that code, we see our product list down there. Now, since it's a slice here, and hence a dynamic array in the end, we can also solve this last part of the bonus task where we should add a brand new third product. And for this, we could create the product just in time or actually create a new variable that contains it. This is up to you, where I create my product with that struct literal notation. Now we need the struct name again because here it's not clear that we'll have a product struct in this variable because we're just creating the variable. And then here I'll give this an ID of third product as a name and give this a price of $15.99 maybe. Don't forget the comma at the end here to be allowed to structure it across multiple lines. And then we can append this new product and change our product's variable to be equal to the result of calling append on products, where we do append this new product now. And then if we want to, we can also again print this updated products array. With that, if you save everything and you run this, you now find that updated list down there, which contains that third product. And that's now also the bonus task solved. Maybe you also were able to come up with that. Maybe not with that shorter syntax here, but with the rest of this task. And if you did, great. If you didn't, no problem at all. We haven't seen this before, and now you did see it. You now also know that you can store structs in arrays and how that works in detail. Now, before we dive into maps, which is another interesting kind of data structure, there is one special syntax which I want to show you, which is especially interesting when you work with arrays and slices. Specifically also when you work with append. Append actually does not just take one value that is appended. Instead, you can append as many values as you want. So here we could also add a couple of other values here, as many as we want. There is no limit at all. So it's really up to you. Now, that's good to know, But the key syntax that I want to show you is indirectly related to that. Sometimes you have an existing slice and you want to append another slice or array to it. Let's say here we have our discount prices, and that's a brand new list which I create here, a brand new slice, let's say, which I'll copy from up there, which contains totally different prices. Something like that. Now we might want to merge discount prices into this prices slice. Of course, here it's just an example, but it is highly realistic that you will have some applications that need to merge different lists. For example, existing users with a list of brand new users that signed up during the day. And you can use the append function to perform such merges as well. Now, for that we can reassign prices and call append again. And now you could think that you just append discount prices like that. But if you try that, you get an error. And the reason for that is that you now try to add a slice, so a list of floats, in a place where a single float is allowed. Because prices is a list of floats, not a list of lists of floats. And discount prices is a list of floats. So adding the full list as one item into that existing list is not valid. Instead, we have to kind of pull out the existing items. And there is a special operator in Go which you can use for that. You can add 3 dots here after discount prices, exactly 3 dots, to instruct Go to go to this list and take out all the elements in that list, so these 3 prices, and add them as separated, comma separated elements to this append function, so to say. So that is an important syntax that allows you to pull out all the elements of a list and use them as separate elements in a place where separate elements are needed, like here for append. We can add as many values as we want, but they need to be separate elements. And that's what we create here with this operator. And therefore now if we print our updated prices thereafter, after using this special operator, if we run our code file here, you see it's a long list of prices and it includes these prices here at the end. Now we had a very thorough look at arrays and slices. For the moment we're done with that, and I will change the main package here in lists Go to lists instead, so that go run dot no longer executes that, and I'm fine with those yellow squiggly lines here, because now I'll add a maps Go file where we will have a look at another key data structure available in Go. And I'll turn this into my main package and give that main function. And therefore actually I'll move the lists Go file into a lists folder so that we don't have a clash here with multiple top level files using different packages. So now we get this maps Go file, and in here I want to dive into maps. So what are maps in Go? A map is a different kind of data structure which you can also use to group data together. It's a bit like a struct, but different. Now let me show you how a map looks like before we then explore how it's different from a struct. Let's say we want to store a bunch of website URLs here. So we have different companies and those companies have websites. For this we could add a websites variable. And of course now we could create an array or a slice. So maybe a slice of websites where we have something like google.com and then also something like AWS.com for the Amazon Web Services. And then maybe a bunch of other URLs as well. This works, but saving those URLs like this could have a couple of disadvantages. For one, if someone looks at this code, or if we ever want to output this code somewhere, we just see the URLs. For some companies like Google.com, it's clear to which company this URL belongs. But to understand that AWS belongs to the Amazon Web Services, it's important that you heard about that company and its abbreviation before, otherwise this doesn't tell you anything. So having an extra label here could make a lot of sense. Now, in addition to that, if you want to retrieve a URL, let's say you want to find Google's URL, you always need to memorize that Google is the first URL here so that you can retrieve it by index. Possible, but if you have a long list of URLs, this can get very cumbersome if you need to start counting those different URLs to find the right index. That's a problem a map can solve for us. We can create a map by using the special map keyword in Go. And then we have a special syntax here where we need to tell Go which kind of map it is. Because a map, like a struct, is a storage where you have values of a certain type and then keys that identify those values. So labels for those values. You have key value pairs, that's a map, just like a struct. I'll talk about the differences to a struct a little bit later. And since we have these two parts, key and value, we now need to define two parts when we tell Go how our map should look like. Because both the key and the value stored under a certain key can be of various value types. That's why we first of all add square brackets here, and between those square brackets, we let Go know which type of value will be used for our key. Very often that will be a string, but it could be anything. You could use some struct type there, so a pre-created or custom-built struct, or an integer, whichever key makes sense to you. Now here I'll start with a string. And then directly after the square brackets, without any blank or anything like that, you now set the value type. So the data type used for the values stored under certain keys. And here that will again be a string, because my URLs, which I want to store, will be strings. So in this case, both the keys and the values will be of type string, but that's not a must-have. You can have different types, and you can use all kinds of types for the key, and you can use all kinds of types for the value. Now, again, without a blank, you can add curly braces here. And this now finishes the creation of a map, though you can also initialize it with some default key value pairs, but you don't have to. You can also create an empty map, which is what this would do. But you can now also set some key value pairs, typically in a new line for better readability. And now here, since I made it clear that my keys will be strings, we need double quotes here to create such a key string. And that could be Google. And then you add a colon, just as you do it in structs, and you set the value for that key, which in this case could be https://google.com. And then, separated by a comma, I can also add Amazon Web Services and then set my URL here, like that. And add a comma to make it clear that this is part of that overall map, and we have a line break thereafter. And this is now a map with two default key value pairs. Now we can, of course, as always, use the format package to print that map and see what that gives us if we print websites. By the way, as soon as you save, this code gets auto-formatted, and Go ensures that this is lined up such that it's a bit easier to read. Now, if you run that code, you will see that this map is being printed here in one line, but it is this map. Now we do have this map. Now we can, of course, also work with that map. For example, it would be very common that we want to extract one specific URL. And that's why we are using a map in the first place, because now we don't have to memorize its position and use the index, but instead we can extract a value by key. So here, if I want to print the URL of Amazon Web Services, then we access websites. And now again, just as with arrays and slices, we use square brackets, but now between those square brackets, we don't have the ID, but instead the key. So here now I can access Amazon Web Services. Of course, you need to make sure that you don't introduce a typo here, because otherwise, if I just type Amazon Web Service, for example, without the S at the end, we would target a totally different key which simply doesn't exist here. So you must avoid such typos. But with that, again, if I run this, we can extract that URL here. And that's the advantage of maps. We can use specific labels, keys, to extract our values by such keys, and in some scenarios, that is simply easier to memorize than the position and the index of an element. Now, when you work with maps, you are also not stuck to the initial map. You can always add new key value pairs. So unlike with arrays, there is no difference between arrays and slices. A map is a map and it's always dynamic. You can always add new key value pairs. So if you want to add a new website, you just access websites, and then you access a key that doesn't exist yet. For example, here I could access LinkedIn, which is a key that's not part of the original map, and just assign some value here, like linkedin.com. And if we then print our website's map thereafter, if we do this, and we save all that code, and we run our code, then you see that here LinkedIn is part of that map. So adding new items is always possible and super easy. You just target a key that doesn't exist yet and add that value that you want to add. Of course, you can always override a value by targeting an existing key and setting a new value for that key. Sometimes you also want to get rid of keys, and you can do that with the built-in delete function, which is built into Go, just like append was built in, and delete once a map and then the key that should be deleted. So here the map which I want to target is websites, and then the second parameter is the key which I want to delete, and let's say that's Google. So this first key here. And if we target that with this, and I then print websites thereafter, you will see that if you save everything and you then run this code here, this new map here only has Amazon Web Services and LinkedIn, but not Google, because we deleted Google. So adding items, deleting items, overriding items, and reading items, that's all relatively straightforward with maps. Now the big question that you might have is, why maps? We already have structs, which are already key value data storages. Well, there are two main, very important differences. The first important difference is that for maps, you can use anything as a key. Here we are using strings, but you could also create a map that uses integers or even some array or a struct as a key. So any value can be used as a key. And that gives you more flexibility since you're not stuck to just using human readable text as keys, even though that is probably what you'll do very often. But you have more flexibility there. Another key difference is simply that maps solve a different problem. With structs, you have predefined data structures. For example, if I come back to that product struct, which we saw before, then we make it clear that we have an ID, a title, and a price. And that's then our product. Now, once we defined that struct, when we work with it in our code, we can't just add a new key value pair. Instead, this is set in stone, so to say. We also can't delete a key value pair from it. So these things which we can do with maps are not possible for structs. And that's not a disadvantage, instead a struct solves a different problem. It's great whenever you have clearly defined kinds of data that should have exactly this shape. Whenever you instead have a collection of values where you want to have custom labels to identify those values, a map is your choice instead. Like here for the URLs. This could be a super long collection of URLs for tons of companies, and we can expand it and shrink it just as we want with a map. It's a bit like an array. We have the same kinds of values, URLs, but we just don't want to have indexes, but instead custom labels. And that's why we use a map instead of an array. With a struct, we wouldn't have a good way of handling this. We could define a struct websites, but then there we would need to define in advance that we have Google, and that will hold a string value, and AWS, and that would hold a string value, and we wouldn't even be allowed to write Amazon Web Services like this. That would be an invalid struct key. So we would have a bunch of restrictions there, and we would simply use a feature to manage a collection of data that's not meant to be used for this purpose. You don't use structs to manage multiple values of the same kind with different keys, but instead you use structs to describe data entities in your programs. Something like a product or a user or a company or anything like that. And a map, on the other hand, is used if you have a collection of values which probably describe the same thing, though technically not necessarily, but then you can assign your own labels, your own keys, and use any kinds of values for those keys that make sense to you. So I hope I could make that clear what the difference between a struct and a map is, and why we have both, and why both solve different problems. In a nutshell, you can basically think of maps as arrays where you don't use indexes, but instead any labels of your choice. So at this point, we of course learned a lot about arrays, slices, and maps. And we're almost done, but there are two remaining important Go features you should know when working with arrays, slices, or maps. And for that, I created a new main.go file, empty file basically, except for this function, and moved the maps.go file into a maps folder and assigned the maps package so that we got no package clashes. And in here, in this main function, I want to create a new slice. Let's say a username's slice, where I simply want to store a couple of strings. Now, of course, we can create that slice like this, and as you learned, if you don't assign a length here, it's not an array but a slice, and you can therefore dynamically add new elements with the built-in append function. So we can append max as a username here, for example, and save that back into our usernames variable. And then do the same here with manual. And if we then use the format package to print all that, so to output usernames like this, we should see that slice in the console. So if we run this application, we indeed see that here. That's of course something you already know. Now what's worth noting about this code here is that when you're creating such an empty slice as we're doing it here, Go will, behind the scenes, essentially also create an empty array. And then once you start adding items, it will start creating new arrays to fit the new content into those arrays and therefore essentially into your slice. Because as you learned in the end, a slice is just a window into an array, therefore behind the scenes, Go takes care about managing those arrays. Now that's of course great, but if you have a scenario where you know that you're going to add a couple of items to a slice that's initially empty, or at least not as big as it eventually will be, then you can also pre-allocate some space for these to be added elements. And that of course only makes sense if you know roughly how many elements you're going to add. But here, where I'm adding 2 elements, we could make Go aware of the fact that we will add those 2 elements eventually. Because when we do, Go is able to, behind the scenes, create a bigger array right from the start, and it then doesn't have to recreate those arrays all the time, which is a bit more efficient. And you can tell Go that you need a bigger array behind the scenes by using the make function. You can call the built-in make function to create such a slice. This function then needs a couple of arguments, and the first argument is the type of slice it should create. Therefore, you must not use this literal notation with those curly braces, but instead you define just the type, so that you want a slice of strings. Then you must at least pass one extra argument to make. And the first extra argument you can pass to make when using it for creating a slice would define the length of that slice, the initial length of that slice. With that, Go will go ahead and behind the scenes create an array with length 2, where both elements initially will be null, empty slots, so to say, but where you can now assign elements to those slots. The result of this code here might be different than what you maybe expect though. Because if I now run this code, we got this output here, and as you can see, the empty slots are actually in front of Max and Manuel. So the two usernames I assigned here do not occupy these slots. And that on the other hand should make sense, because make like this, as I mentioned, creates an array of length 2, and these two elements then are empty here. When we then append new elements, we of course don't add those for those existing slots, instead we append them to the end. Instead you could now, when using make like this, assign values for these two slots that have been created, like this for example, without make. So if you would not create usernames like this, but instead, as we did before, by using a string literal, you would get an error with that code. Because this creates an empty array behind the scenes, and when you then try to target the first element there, you'll get an error. So if I run this code here, it crashes. So that's one difference of make. You can create an array behind the scenes that already got some slots, which can be helpful if you want to assign values to specific indexes like this. But originally, I talked about a greater efficiency if you let Go know about the intended size of the array you'll eventually need. And that's not yet what we're doing here. Instead, you can pass another argument to make when using it to make a string, and that would be the capacity of the array that should be created behind the scenes. For example, 5. Now keep in mind, the capacity is essentially the maximum number of array items and therefore controls how much memory space will be allocated behind the scenes by Go for this array. So this make function call will make sure that Go allocates enough memory space for a string array that takes 5 items, and it will create an array with 2 empty slots. But now with that pre-allocated memory, appending items here is more efficient because with this code, Go now doesn't have to go to the memory and allocate new space. Instead, it can use the existing space because we already reserved enough space. And only once we go beyond the 5 capacity limit here, it'll have to allocate new space. And therefore, using this make function can be useful if you know in advance that you're soon going to add a fixed number of items, or at least a number where you have a rough estimate how much you're going to add, because that then can make memory management more efficient. Now, I'll also say that in many apps that might not matter at all, but it can be an optimization that can make sense for certain applications. Now, this make function is not just available for slices. Instead, you can also use it to make maps. For example, let's say we create a courses map where I want to have string keys and then float 64 values. because I maybe plan on storing the ratings for different course identifiers. And therefore, of course, we could also name this course ratings. Now, if we want such a map here, we can of course create it by using this map literal notation here with the curly braces at the end. And then that allows us to assign new keys. We can create an empty map initially and then add keys as we need them. For example, here we could add a value for the Go course and set this to 4.7, and then maybe add another rating for the React course and set that to 4.8 or something like this. Now, of course, hopefully unsurprisingly, if we print that to the console and we run the application, we got that map output here. So this works. But we have the same potential problem we had before with this slice. When we create such an empty map here, Go will have to reallocate memory whenever we add new items to that map. And if we know, at least roughly, how many items we're going to add to that map, we can also use the make function here to create such a map. Again, we have to get rid of the curly braces, but then we can make a map like this. Now, if we just call make like this, it would work, but it would essentially give us the same result as using this literal notation does. It would give us an empty map without any pre-allocated memory. Instead, here we can also pass an additional argument to make. But unlike with make for slices, it's now not 2 additional arguments that can be passed here, but instead only 1. Because here we can't set any empty slots. This doesn't really make sense for maps. Instead, we can just define the intended length of that map. So that again, Go can go ahead and pre-allocate memory. For example, we could set this to 3. And now we can add 3 items here, let's say also angular, like this, without Go having to reallocate memory. That would only be the case once we add another item here. Then, since we only defined a capacity of 3 here, Go would have to reallocate memory. But if we know in advance that we only plan on adding 3 items, at least for the moment, we could make this a bit more efficient by using make for creating that map. So the make function can allow you to make your code a bit more efficient. Another feature that can make your code a bit more efficient from a developer's perspective could be a custom type, a type alias. And here I'm now not talking about some performance efficiency, but instead giving you, as a developer, a better development experience. Because, for example, types like this are rather long. A map with string keys and float values, that's quite some text you have to write to define this type. Now, earlier in this course, you learned about type aliases, and here's another scenario where we could use such an alias. We could define it here, and then maybe name it float map. The name, of course, is up to you. But now you can grab this type here, this built-in type, and use that as a type for this type alias, so for your custom type. Now you could also add methods here, as you learned earlier in the course. So for example, we could add an output method by using float map as a receiver and by assigning a name here maybe. And then we could easily output it like this. And that would then allow us to use float map in our code, for example here, to make this map. So make also works with that, because Go understands that behind the scenes, this will be this map here. And the advantage would be that, of course, now we can call our own methods on that type. So instead of printing the course ratings like this, I could call output like this. And if we run that code, that would all still work. But even if you don't plan on adding custom methods, using such a custom type, such a type alias, for longer built-in types like this can make sense, because now we have this more concise, shorter type, which we can use in our code. So that's not something you have to do, and you might prefer the more explicit approach here, where you use the built-in types, but you can also go for such a type alias to save some characters down there and to type less text. And with that, we're almost done for this section. But there's one last very important Go feature you must know when working with arrays, slices, or maps. And that would be the for loop. Now, you did learn about this for loop earlier in the course already. You could use it to create an infinite loop, or you could also use it to have a fixed number of iterations. Now, when working with slices, arrays, or maps, so with collections that store a number of items, you can also use the for loop to go through all these items and perform some operation for every item. Because that indeed is something you'll typically need to do quite a bit when writing Go code. And the syntax for doing that is pretty easy. Let's say we want to go through all our usernames, so all the items of that slice. And it does not matter if the slice was created with make or not, just to be clear. If we want to go through all the usernames, we can use the special range keyword and then thereafter usernames. This will tell Go that we want to go through all the usernames. But in order for this to be useful for us, we have to put something between for and range. And that would be two variables. For example, index and value. Written like this, that would be the final syntax for writing a for loop that goes through all items in usernames. And these two variables here are needed because this range keyword essentially exposes two values related to the usernames slice for every iteration of this for loop. It will give you the index of the item it's currently looking at, and for every iteration that will be a different item, step by step going through the entire slice. And it will give you the item itself, so the value that's stored at that index in usernames. So therefore here, to see what we get, we can simply print index and also value. And of course, these names are up to you. I just named them index and value because that's what we get, but you could also use I and val or whatever you want. So that of course would also work. But here I'll go for index and value, and to be clear what's what, I'll print that like this. And with that added, if we run this application, you see this output here, where I get index 0, value Julie, index 1 and an empty value, index 2, value Max, index 3, value manual. And that's exactly what we store in our usernames slice. We create it with two empty slots, then we store Julie for the first slot. That's why at index 0 we have Julie. We store nothing in the second slot, so at index 1, that's why here we have an empty value. And then we append two users, so Max will have index 2, as you can also see down here, and Manual has index 3. And that's how you can easily go through all these values. And of course in here, you're not limited to printing those values, instead you can do whatever you want. You can call some other function that takes that value as an input and does something with it. You can create structs, you can do whatever you need to do. So everything is possible here. And this for loop does not just exist for slices. You can of course also use it with arrays in the same way you use it for slices, and also for maps. And for maps, it's also still the same syntax. So we still get our index and value, we use the range keyword, and then we just refer to a map. So to course ratings, for example, instead of a slice. Now here we could rename index to key, since that's the better term for this identifier that we have in a map, but of course, as mentioned, this name is up to you. And then here we can also perform any action we want and, for example, output these values. Here, just outputting the key instead of the index. Well, and with that, if we run this, you see that down here, I'm getting my map for loop output, and I'm getting my keys here, as you can see. And I'm then also, of course, getting the values that are stored for these different keys. And therefore, again, this is an important feature because whenever you have some operation that should be performed for every item in a map, this for loop is your friend. Now in this course, you of course learned about functions, that you can write functions to execute code how often you want, when you want, with any input parameters that might be needed, and with any return values that might be needed. In this course section here, we're now going to dive deeper into functions. We'll take a closer look at functions and we'll explore some slightly more advanced function-related Go features. To be precise, in this section, we'll take a look at using functions as values, what that is and what that means and how it works. We'll take a look at anonymous functions and when those might be helpful. We'll explore the important concept of recursion, what that is and which kind of problems can be solved with recursion and how it works. And we're also going to explore variadic functions and how to work with those in your Go apps. Now, as always, I'm in a brand new empty project, an empty Go module that I created, and I want to start with the fact that functions, these things which we have written over and over again, are first-class values in Go and what that means for us. Now for that, briefly, let's recap what a function is. It's a piece of code that we can execute on demand. We give it a name, we can accept parameters, and we can return values, even multiple return values, as we learned. Now, what we did not learn up to this point, but what we can also do with functions in Go, is that we can use functions themselves as parameter values for other functions. And this might sound a bit cryptic and strange, and therefore I want to give you a concrete example. Let's say we have a couple of numbers, a slice of numbers to be precise, and I'll just quickly create it here with the composite literal notation. And I now want to double every number in that slice. Of course, for this we can write a for loop here, and we can go through all the numbers and then perform this operation with that for loop. But let's say in the program we're writing, we might have multiple slices of numbers in different parts of our program, and therefore we want to outsource this loop, this operation, into a separate function. Well, we can do this. We can add a function, double numbers, and there we take our numbers as an input, and that could then be a slice of integers. Or maybe it's also just a pointer at such a slice of integers, and we then loop through our numbers there. For example, with the range keyword, where we get the index and the value, like this. Then we can loop through our numbers, make sure to dereference the numbers, of course, and now we can either edit the numbers in that existing slice. That would easily be possible since we get a pointer to that original slice, or let's say we return a new slice here. So we got our D numbers for doubled numbers here, which is a brand new slice of numbers, which initially is empty. And now for every number through which I'm going here, I will add it to D numbers with append. So here I append to D numbers. And the value which I want to append is the value from the input numbers. So the value, the slice, which will pass to this function when we call it, times 2. And that will return a brand new slice, which I will of course store back into D numbers. I'm not going to use the index, so I'm using that underscore symbol here to signal that I don't care about that value here. And I just return my doubled numbers here in the end. That's how we could write this utility function here. And with that written, in main, if we want to double our numbers, we can add a new variable here, let's say, call double numbers and pass numbers to it. To be precise, since I'm expecting a pointer here, I'm using the ampersand symbol here to get the address of numbers. If I would expect a slice instead, we would pass it like this, without the ampersand, but then a brand new copy is created all the time, and you'll learn about that throughout the course. So I'll accept the pointer here and pass the address, and then I get my doubled numbers, and hence last but not least, we can use the format package, import it, and call println to output the doubled numbers. Now with that, we are just repeating what we already learned, but this is an important first step to then understand what I mean with functions as parameter values for other functions. At the moment, we're not using that feature yet. But with that code here, if we now open the terminal and run this, we of course get our doubled numbers here. But now let's say our goal here is to not have this double numbers function, which only works on slices, but instead we might want a general double function that doubles integers themselves. So not slices of integers, but single integers. For this we could add a function, double, which takes a number, which is an integer, let's say, as an input, and which returns an integer, but it returns the input number times 2. Now I have this double helper function, which I might also be using in different parts of my code. And deliberately I'm keeping this function simple here. Of course, we could also have functions that do more complex things. Now with that double function defined, we could of course use this here instead of doubling this number manually here, and execute double and pass our value to it. So this value, this number which we get by going through all our numbers. Now we have another utility function. But here I'm passing the result of calling that function to append, and that's also not new. We have been using the results of calling functions as parameters for other functions before already. But now comes the interesting part. Let's say we don't just have a double function, but we also have a triple function, which triples the value, just as a dummy example. Now, if we want to have a function that goes through all the numbers in a slice and triples those numbers, we have to write a brand new triple numbers function where we repeat all that code just to then call a different function here inside of that for loop. And that's where this functions are first class values feature can now come in handy. It would be pretty nice if double numbers would be less specific. If instead of double numbers, it would maybe just be a transform numbers function. And the exact transformation is not hard-coded into the function as it currently is, but instead, besides our slice of numbers, or a pointer to that slice, we maybe also accept a second parameter value that describes the to-be-performed transformation. And that's where it's now handy that in Go, we can also pass functions as parameter values, and we can therefore accept functions as parameter values. And that's exactly what I want to do here. Because the second parameter, which I expect here in transform numbers, should be a function that is then to be executed in here. I'll name this function transform, but that's up to us because it's just a parameter value in this function, just as numbers here was up to us. But the type of this parameter value is now interesting because it will be a function type, which we define in Go by again using the func keyword, but now in a place where a type is expected. And then we just add parentheses here, but not to define parameters, because we're not defining a function here. Instead here we are defining the type of a function, and hence here we just define the types of the parameters the function should have that we get here as a transform parameter. And here we want to make it clear that we want a function that is able to handle ints as inputs and that then returns an integer. So with that, we're defining the type of a function instead of the function itself. And we're saying the value that we receive here for this transform parameter should be a function that has one parameter that is of type int, and that then returns one value which is of type int. And the function type can, of course, anything you want. We could also want a function that has two parameters, an int and a string, and that maybe also returns multiple values, a int and a bool. Like this. That would all be possible. But here I just want a function that returns one value, an integer, and that takes one value, an integer. But now with that we get this transform parameter, and we know that in this transform parameter we'll have a function. So here, instead of calling double, I can now call transform, because again this will be a function, hence I can execute it as a function, because we force it to be a function here. And now here where I want to double my numbers, I can now execute transform numbers and pass in that second parameter value, which, and that's important, is now a function. It's not a number, not a slice, not anything like that, but a function. And that's what I meant when I said functions are first-class values. You can pass functions around as values just as you can pass other kinds of values around. So just as we can pass a slice or an integer into this transform numbers function, we can also pass another function into this function. Might sound complex and tricky at first, but it's actually straightforward. Functions are just values in Go in the end. And therefore here, I can now use this double function here and pass double like this into transform numbers. The important thing here is that we don't execute double. If we would execute it here, we would pass the result of executing double into transform numbers. But here we want the function itself, not the result. Hence we don't have parentheses here, and we instead just use the name of the function. Again, just as we use the name of a variable in other places as well. Because again, we're just using the function like a value, because in Go it is just a value in the end. A value you can execute, but also a value you can pass around. So here I'm passing the double function into transform numbers, and this double function will then be executed inside of transform numbers here, because it's received as an extra parameter. And the advantage is that we now can easily also get our tripled numbers here by calling transform numbers with the triple function that I also defined down there, pointing at that triple function by its name. And hence now here I can of course also output tripled. And that's now the advantage of using this feature. It allows us to write more concise code. Because without that feature, we would have to copy this entire transform numbers function here just to write it once with double and another time with triple inside of it. Now that we know that we can pass functions themselves as parameter values, we can save that unnecessary code duplication, we can avoid it, and we can instead just define this generic function once, and then accept the specific transformation function that should be executed inside of it as a function parameter. That's what we're doing here. And therefore now, if I run this program, we see the doubled and tripled numbers here. So that is working. And now that we know about function types, I can also come back to a feature we learned about in the previous course section: custom types. Function types can get rather long. This one isn't, but that's just a function with one parameter value, which type is pretty short, and one return value. Imagine that you want a function here that maybe takes 3 parameter values, and one of these values is a map full of slices or anything like that. Then such a function type definition can be rather long. That's why you can also store function types as custom types. Here I can add a type transform fn maybe for transform function, and simply store this function type in it. And now I can use this custom type down there, just like this, and everything still works. If I save that and I then run this again, we still get the same output as before, but now we have less typing to do here in our code. And as mentioned, that's particularly helpful if you have more complex function types, like another function here, let's say, where you expect an integer and then maybe a slice of strings, and then maybe a map where the keys are strings and the values are maybe slices of integers. And you want to have 2 return values where one of them is a slice of integers and the other one is a string. That's just a made-up complex example, but that's a pretty long function type, and if you would have to repeat that over and over again in your code, that could be pretty annoying and error-prone, hence saving that in a custom type, where you can then just use this custom type in your code instead of this, can definitely also be useful. We don't need it here, we're not using it here, but I hope it's clear why this can be helpful. Now we did learn about function types and about the fact that functions can be passed into other functions as parameter values. Now it's not just that, functions can also return other functions. They cannot just get them as parameter values. Now this will become more useful once we also learn about anonymous functions and closures later, but I still already want to show it to you. For example, we could have a function, getTransformer function, that actually has the job of returning us another function, which we can do by returning double, for example. We now also just have to make it clear that this function will return another function by adding the appropriate return type. For example, my transform function, so my custom type, which I defined up here in line 5, or the longer form, if you prefer that. That would also be fine. Whatever you need. Here I'll go for the custom type with transform function. Now, whenever you execute getTransformer function, you get a function as a return value. Because that's also possible. You cannot just accept functions as parameter values, you can also return them. And here I'm returning double. Please note that again I'm not executing it, because if I would return the result of calling that function, so I would return the return value of double. I just want to return the function itself here though, and hence I don't execute it. And with that I return the function itself as a value. And of course, like this, that's really just some dummy code, not too useful. We could make it a bit more useful by adding some logic to it. And for example, we could say that getTransformer function has the job of picking the right transformer for the data on which we want to perform the transformation. And hence we could expect some numbers here, which might be a slice of integers, or a pointer to such a slice to be precise. And then we could check if numbers 0, so the first number in there, is equal to 1, in which case I want to return double, and we should dereference this here, like that, to make this work. Here we also need parentheses, because unlike with structs, we have no shortcut for slices when getting an address and wanting to access a specific value. So we dereference that to get the slice, and then we access the first value. And if that first value is not 1, then we maybe return triple. So now getTransformer function will return different functions based on the input value here. And again, it's just some dummy code, but it's hopefully clear what it generally does here. And now we can use this getTransformer function in main to get different transformer functions for different numbers. If I have more numbers here, and that's, let's say, is also a slice, but a slice that starts with 5 and then has other values, then for these two different slices, when using this getTransformer function, we should get different transformer functions. Yeah, that's a lot of transformers and functions. But let's see whether it works. I can get my first transformer function here by calling getTransformer function and passing numbers into it. To be precise, the address of numbers, since getTransformer function, the function we just worked on here, wants a pointer to a slice, not the slice itself. And I can get my second transformer function by again calling getTransformer function and passing the address of more numbers. And now transformer fn1 and transformer fn2 will be functions themselves because getTransformer function returns a function. That's the code we wrote a couple of minutes ago. And now I can get my transformed numbers here by again calling transform numbers, so that function we used earlier already, and passing in my numbers here, the address of my numbers, and passing in transformer function 1. So the transformer function I derived here, because that is a function, because that is what getTransformer function returned. And I can get more transformed numbers by calling transform numbers again, but by now passing in more numbers and passing in transformer function 2, for example, the function I got here. And now if I output this as well by printing my transformed numbers and the more transformed numbers, if I execute this code here after saving everything, then you will see that we get doubled and tripled numbers here. The original inputs can be seen here, and we do have the doubled and tripled values here, because I got different transformer functions by calling getTransformer function for these different number slices. Because of the logic we wrote inside of getTransformer function, and because of the fact that this returns a function. Again, this is definitely a made-up case, but the key takeaway is that functions can return other functions, and that can come in handy in certain situations. Again, it will be even more useful as soon as we also learn about anonymous functions and closures. I did again store the code we wrote in the last lectures in a brand new file and package in a subfolder, and I did set up a new main.go file which contains errors though. We're going to continue with that Go file and fix those errors, and hence you find this main.go file attached to this lecture. Now in this main.go file, we have code that looks similar to what we had before, just a bit shorter. I have a transform numbers function, and this function, just as before, takes another function as a second parameter. Here I'm not using a custom function type, instead I wrote the type in the long form, but it's still a function type. Now the logic in the function hasn't changed. I'm still calling this transform function, which I'm getting as a parameter, here inside of that loop. Now we're getting an error because here when I call transform numbers, I'm not passing in a value for this function parameter. And I don't have the double and triple functions from before anymore. Because in this lecture, I want to dive into a new feature which is related to what we learned before. I want to dive into anonymous functions. Now what's that? Well, in programming in general, and therefore also in Go, when you have a case where a function wants another function as a parameter value, or where a function returns a function, then you often can save some effort and time by using anonymous functions, which is a feature that allows you to define a function just in time when you need it instead of in advance. Now before, in the code we wrote before, I defined double and triple in advance. I created them as regular functions with the func keyword and their names. Now nothing wrong with that, but here, if I just want to do that transformation and I need a function here that doubles all my numbers, I might not want to write a brand new double function. Because maybe I only need the double function once, and for the next transformation I need a different function, different logic. In that case, you can write a function here in place of these three question marks. You can write a function with the func keyword here, no name, but instead just the parentheses for the parameters, then your return value, and then the function body with parentheses. And here we could say we want a number, which is an integer, and we will return an integer. And in this function, I will return number times 2. Like this. The logic is up to you though. This is valid. This is a valid way of writing this, with or without the blank here, by the way. That doesn't matter. Now, this here is a so-called anonymous function. It's not a function type, because we're not writing this in a place where a type is expected, but in a place where a value is expected. We are calling another function and we're passing in values for these parameters after all. So this here is not the type of a function, but really the function itself. It's the place where I previously passed double or triple. That's what I passed here as a second parameter before. Now I'm passing in a brand new function that's written just in time. This is an anonymous function because it doesn't have a name. We can't call it anywhere else in our code, therefore, because it doesn't have a name. But if we have a place where a function is needed as a value, we can just create that function in that place, as I'm doing it here. Then, besides the fact that it doesn't have a name, it works just as you learned it. You can take parameters, as many as you want, and you can return values, as many as you want. Of course, we have some restriction though, as this is the value for another function, for the parameter of another function. Of course, the function type defined down here, when we accept this parameter, has to match the type of the function we are creating here. So here I can't start accepting a string as a second parameter. This would be a valid function, but it's not a valid function for this parameter, which wants only one parameter in that function that is received, and that one parameter should be an integer. So this function, which we create here, would not meet the requirements of this parameter. Hence, we have to get rid of that extra parameter in that other function here. But now with that, it would work, and that would be a valid anonymous function. And the advantage is that if you just need to add such a function real quick, and you don't plan on calling it in any other places of your code, then you don't need to define an extra function. Instead, you can define it in the place where you need it, and that can also make your code more readable, because other developers, if they want to see what your function does, don't have to search for your function somewhere in the file, as we have to do it in the example before. I want to find out what double does. If I can't guess it by the name, I have to search for the double function. Here it is. With an anonymous function, I don't have to do that. Of course, if you do plan on performing that same logic in different places of your code, storing it in a named function and referring to that named function here instead would be preferable, since you otherwise have to copy and paste your code a lot. So it's a trade-off and simply depends on your application. But anonymous functions can be useful if it's a one-off task and you don't need to reuse the logic, and then you can write them like this. Now, related to anonymous functions, we have the concept of closures. Closures also use anonymous functions and use a specific aspect of anonymous functions. And here's an example. I'll add another function, not an anonymous function, but instead a regular named function, which I'll name createTransformer. Now, createTransformer has the goal of producing functions. And for this, I will return an anonymous function here, because in all the places where functions are needed, so both in parameter values as well as in return values, you can use anonymous functions. Now, createTransformer should return functions that take integers as inputs and return integers as values. So it should produce functions that look like this. Hence, the function which I return here will take a number as an input, which is of type int, and it will return an integer, this anonymous function. And then in here, we could return number times 2, but that's now the part where createTransformer will become active. The number with which I want to multiply that number should be a parameter of createTransformer now. So here the factor is another integer, and I can now use this factor inside of this anonymous function. Please note that factor is not a parameter of this anonymous function, but of createTransformer. But because of scoping, and because of the fact that we can use variables, and parameters act like variables and are just variables in the end, in lower level nested scopes, means that we can use factor, which belongs to the scope of createTransformer, inside of this anonymous function, which has its own scope, but which is part of the createTransformer function scope. So we can use factor in this inner anonymous function, even though it's not a parameter of this function, because it is a variable or parameter of that outer scope, of this outer function. And now the function which I return takes both its own parameter, number, as well as a parameter of createTransformer. And now we can use createTransformer as a so-called factory function, because createTransformer now is a function that produces other functions with different configurations. And that means that we can now easily create different number transformers. Here in my main function, I can, for example, get a double function by calling createTransformer and passing in 2. I can create a triple function by calling createTransformer and passing in 3. And of course, we can pass any value we want here. And then I can get my transformed numbers not just like this, but I can also get my doubled numbers here by calling transform numbers, passing in the numbers, or the address of the numbers, and passing in the double function, which I created here with help of that factory function. And we can do the same for the tripled function, where we now pass in triple as a second parameter value to transform numbers. And hence we can of course output doubled here and also output tripled at the bottom. And that's how we can use such a factory function here. Now, I did mention though that this lecture would be about closures and not factory functions. Well, factory functions are just a pattern, but we also actually have a closure here. Every anonymous function is a closure, and that simply means that if you use a variable from a scope in which the function is created, so from an outer scope, like factor here, then the value of that outer scope variable or parameter is locked into this created function. So that means that if I call createTransformer with 2 different values, as I do it here with 2 and 3, then the function that is produced will not be changed by those later calls. If I call createTransformer with 2 here, then this function will return me a function that multiplies the input value to this transformer function with 2, because I passed in 2 here. If I then call createTransformer thereafter again with a different value, that will be a totally different scope, a totally different function execution. Just because I call it with 3 here will not change this double function which was produced before, because this anonymous function closed over the variables or parameters of the scope in which it was created. So factor will be available when I then later execute double, which I in the end do in transform numbers when transform is invoked, because I'm passing double as a function to transform numbers. And that double function will work and will double its numbers because, again, that factor and the concrete value of that factor when that function was created will be locked in because it's a closure. That's simply what a closure is. This value will be locked in and will be available at any point in the future when we execute this function. Even if we call createTransformer thereafter, this locked in value won't be changed. And therefore now here, if I run this module again, I get my doubled and tripled numbers here because I locked in these values with help of this anonymous functions feature, with help of this factory function pattern, which we're using here, and with help of that fact that functions are closures in Go, and hence we can lock in values of the outer scope for future function execution. Now again, I stored the code from before in a separate package with a separate file in a subfolder, and now I get an empty main.go file again. Because now I want to dive into a new concept called recursion. What's that? We talk about recursion if a function calls itself. And a great example for this is a function that calculates the factorial of a number. Just to make sure we're on the same page, the factorial of 5 would be 5 times 4 times 3 times 2 times 1. So it would simply be 120, because 5 times 4 is 20, times 3 is 60, times 2 is 120, and times 1 is, of course, still 120. And if we want to derive this, we can write a function for this. The factorial function, for example, which takes a number as an input and returns a number. So it's a standard named function, nothing special about it yet. Now, to derive the factorial here, we could write this all with help of a loop.